Okay, welcome back, and we are on the next lecture, and we are going to build the circuit that we've been talking about, the low-pass filter. So to refresh your memory, all we're going to do here is we're going to have an R, a resistor, and we're going to have a capacitor, and this very simple circuit. So we're going to have an input at one end, and we're going to have an output at the other end, and just basically an R and a C to ground. And be very careful, because if you put the C where the R is and the R where the C is, we're going to have a high pass filter. And we're going to look at that next, of course. But right now we're doing a low pass filter. All right. So we know that our cutoff frequency is this 1 over 2 pi RC. All right. And so let's take a look, if we use some common values, what we think that our cutoff frequency is going to be. We'll calculate it, and then we'll go to the bench, and then that'll give us a frame of reference. So let's say, for example, we do, let's say that R equals to 1K ohms, and let's say that C equals, say 0.1 microfarad. All right, so if we plug those values in, let's go ahead and let's erase some of this dB gain stuff. We don't need this anymore. I like to keep what's up here on the blackboard for each lecture so you can kind of remember things, even though you can just look at it in the video. All right, so now what we're going to do is we're going to plug these values into this formula right here. All right, so F equals 1 over 2 pi. There's always a 2 pi in here. All right, and then R, and what's R? It's 1K. Okay, so 1K ohm. And what's our C value? It is times 0.1 microfarad. All right, so let's go ahead and plug that into our calculator. So we've got 2 times pi times 1K times 0.1 microfarad. All right, and then we're going to take the inverse of that, and then we get to 1591. So it's 1591 and some change, but we're just going to call that 1591 hertz. So this is important. This is in hertz. So this is approximately equal to 1.5 kilohertz, 1.5, 1.6 kilohertz, right? So that's going to be the cutoff. So ironically, I mean, I drew this curve almost exactly correct. So if we put a 1K and a 0.1, this curve right here, let's use this color here, this curve right here that we're showing the response is exactly what we should see. So basically, here's 1.5 kilohertz as drawn, actually. That's where we should see that 70% or that minus 3 dB. All right. Now, as we change these values, as we make R or C different, then this 1.5 kilohertz is either going to go up or go down. All right. Now, since we're dividing, it's 1 over that value. So if we make R bigger, right? So if we make R bigger, this would be smaller. If we make R smaller, this would be bigger. Same thing with C. So once you have a reference point, the 1.5 kilohertz, then we can play with R and we can play with C, and then we can see what happens. All right. Now we're going to not simulate this inside that simulator, but I really want to quickly show you that it's very easy online to find tools to do low pass and high pass filters, so you don't have to build them. Or build a simulation. So if you just go to Google and you type in low pass filter calculator, there's many of these online. People make them in Java. It's when you're learning a program, it's a fun thing to do, is to make a little simulator that just does that calculation. So I went through them, and as a matter of fact, I think I already have this page. Yeah. So here's one on Aqua Electric Design. They've got a low pass and a high pass filter under filter tools. If you go to filter tools, there's RC filters, LR filters, RLC filters, and you just put Salem key. These are active filters. So that's one of my favorite kinds of filters. Lots of filters. So this is a really cool page. So sim.okawa denshi.japan jp/English, and then fkeeson.htm. Anyway, obviously I'll put this up inside of the materials. All right, so what do we want? We want an RC low pass filter. All right, and here's our transfer function. Right, so there's our transfer function. We've seen this before. It looks very similar to ours. It's got an S here though, and S is what's called the S domain, and basically S replaces j omega with this value s, and it's done with a Laplace transform, and that's something we don't need to know about, but it's called the S domain. It's very similar to the frequency domain. But anyway, we don't really care about that. All we care about is there's an R and a C. It looks just like ours. And let's go and put these values in here. So let's go put 1,000 ohms, and we're going to put 0.1 or exact 1 e to the minus 6, 0.1 e to the minus 6. I'm having trouble with this keyboard. All right, there we go. 0.1 e to the minus 6 farads. So be careful, it's in ohms and farads. All right, so we've got 1 kilo ohm and 0.1 microfarads. All right, and this is called a Bode diagram. That's what we want, poles and zeros. We can have it print those out. It can show the transient response. That's all fine. We'll just say calculate. All right, so when we come down here, there's our cutoff frequency of 1591 hertz, just like we calculated. There's the transfer function. And the transfer function, again, if you were to plug all the values in, you would get something that looks like this, except for this S, which is slightly different than the formulation we're using. We're doing G of F, but very similar. All right, and then down here, take a look here. This is cool. So here is the Bode plot, or Bode plot. Is how I've learned to say it. And then you can see here's the magnitude. So here's 0 dB, so that means the gain is 1, right? So it's unity. So it's unity at DC, unity, and then 1E3, that's a kilohertz right there. Now notice this is that logarithmic scale I was talking to you about, right? Logarithmic scale. So here's 0, and then here's this is 100 hertz, and this is 1 kilohertz, 10 kilohertz, and so forth. Anyway, here at 1 kilohertz, right, and so this would be 2 kilohertz and 3 kilohertz and 4 kilohertz and 5 kilohertz and 6 kilohertz. So here at 1 kilohertz, we see it starts cutting in, and you know, if you eyeball it, it's about 1500 hertz right here is where this thing is down about minus 3 dB. And notice that the top scale, the vertical scale, which is the dB magnitude, it is linear. It is not in logarithmic form, as is the horizontal frequency scale. So minus 3 dB is right about here, cut across, and sure enough, cut right down here, and there it is. So 1500. So that's exactly what we predict. So, but this is a cool little program where you can plug values in very quickly and see what the results are, not go through a full simulation. All right, so now we're going to go over to the bench, and we are going to build our circuit. So let's put this back up. So we want an R and a C, a 1K and a 0.1 microfarad. We're going to build it. We're going to excite it with DC running up to whatever frequency, and we're going to watch the response on the oscilloscope. So this is going to be a lot of fun, and this is going to really show you all these different things. So let's go over to the bench, all right? I'll meet you there. Okay, everyone. So we're here at the bench, and we've got our solderless breadboard. And we've got our parts here that I think that we're going to need. And we've got a few different resistors, 100 ohm, K ohm, 10 K ohm. We've got some capacitors, 0.1 microfarad, I think 1 microfarad, and 0.01 microfarad. Got a few little wires, and we've got some posts. And then over here to my right, I've got some multimeters if I need it. And then in front over here, and here, we've got our oscilloscope and signal generator, which we'll bring in as we need. But first, let's build the circuit, all right? So let's go ahead and let's zoom in a little bit so we can see what we're doing here. Get a nice zoom here going for you so you can kind of see as we build this. All right. And now, so again, when we're doing analog electronics, we want to do things as clean as possible so that the circuit works and we don't have a lot of stray capacitance and stray inductance and that kind of thing. So just, you know, be clean. All right, so we have a circuit where we want to bring a signal in. So let's just kind of start there. So put a wire here. And, all right, so I'm thinking I'm going to bring the signal in here. All right, then we need a resistor. We need a 1K resistor. 1K, so that's going to be brown, black, red, brown, black, red. And go over here to the zoom camera. Take a look here. And let me lock that on there for you. So brown, black, red, right? So that would be a 1K if you were to figure out the color code for it. So we're going to put that there. All right, then we need a place to put our capacitor. So we want 10 to the 4th, 104 is 0.1 microfarad. And again, I'll go to the zoom camera, and can you see that? Yep, 104. All right, so 103 would be a 0.1, a 0.01, and 102 would be 0.001 microfarad, and so forth. So anyway, so there's that. So there's our 0.1. So I'm just going to go ahead and I'm going to put that, let's see, can we put it, yeah, let's just put it in across 2 pins here, across 2 different columns here on the solderless breadboard. All right, nice and clean, nice and short leads, you can see that. All right, now that's got to go, so actually, let's, because we want to get the output, so let's do this, we'll put the, there we go, we'll put the resistor there like that. Okay, and then the other end of the capacitor has got to go to ground. All right, so that's going to go to ground. So I'll put in a little ground lead here. Connect this very nice, very clean. All right, so that's what we got now. All right, now we got to be careful. So where do we want our output? So we've got the resistor here, and right here at the node between the resistor and the capacitor, that's the output. All right, so that's the output and the input is here. So we're going to be real careful of that. So in fact, we're going to take a wire and we're going to bring it over here like this so we don't have any confusion. All right, so now we've got our input here, we've got our output here, okay, and we've got our filter right there, 1K and a 0.1 microfarad. Now, let's use some of these posts because we've got to connect signals here. So what we'll do is on the input, we'll put this big post here, and on the output, we'll put this post here. All right, and then let's put some ground posts here, put one there, and we'll put one there, and let's see, we're going to have 2 channels, maybe put 2 of them here, just so we can get these little alligator clips on here. Okay, so now I've got our circuit. So that's it. And then this other stuff here, the capacitors and these wires, and there's an LED over here. I just left this on here. So if we were to power the circuit up, which there is no power, this is a passive filter. But if we were to power it up, then we would have power on both rails, and then this little LED turns on saying, hey, the board has got power. So I kind of tend to do that so I know what's going on. Okay, so now we need our signal generator. So what I'm going to do here is, this is the signal generator leads, and we'll switch over the camera so you can see the signal generator in a moment. But right now, so we're going to put the minus lead here, all right, and then we're going to inject the signal. Matter of fact, let's do it like this. Do it right there, and then we're going to inject the signal here on the input, all right. So that's that end of it. So now that's going to put the signal through into the circuit. So now we'll have a sine wave or whatever we want that we'll be injecting. Now we want to look at that signal. All right, so now I'm going to get an oscilloscope lead here. All right, and try not to take down everything as I do this. Okay, so here's the oscilloscope lead. And so remember, the oscilloscope measures voltage as a function of time. I'm going to make sure that's on 1 times. See this attenuation, 1 times. All right, channel 1 so I can remember what's plugged into what. Okay, so there's the ground. We're just going to connect that up. Connect this to the other ground right here. All right, keep it clean, keep it clean. All right, and then we're going to connect that right there. All right, so that's nice. So now we'll be able to see on the oscilloscope what channel 1 looks like, which is coming from the signal generator, which we're going to show these on the video in just a moment. Okay, now we need another channel. We need to look at the output, right? The output of the filter, or the response of the filter, right? So here's another lead. This is channel 2. Again, I'm going to look at this attenuation, make sure it's on 1 times 1. It is. All right, I'm going to hook up the ground, and then I'm going to hook up the output right here. All right, so there we go. So that's very nice. And let me see if I can zoom into this just a little bit. The camera has trouble once we get too close. Yeah, let me back it out just a little bit. Okay. All right, so that's good. Okay, so there's our circuit again on edge. It looks like that, just like we expect. All right, so now let's go take a look at the signal generator first. Let's go take a look and see what's going on there. Okay, so here is the signal generator, and we've got the output right here of, this is the channel 1 output here, and then here's channel 2, which we're not using. So channel 1 is going into the input here. Channel 1's going into the input, that's this red guy, all right? All right, and right now I've got the signal generator set for 10 hertz and an amplitude of 2 volts peak to peak. So it's a sine wave, peak to peak of 2 volts, all right? And that's it, okay? And it's at 10 hertz. And then what we're going to do is we're going to spin it up. So I'm going to watch as I turn this dial. You can see the frequency here going up, all right? 300, 400, whatever. So we know that this filter is going to start working when we get around 1500, right? So when we get around 1500, and I can go to the tens place here, the hundreds place, right? Around 1500, this filter is going to start really reacting. So I'm going to lower this all down here. I'm going to lower it back down to like 10 hertz, okay? Okay, and the reason why we have the voltage at 1 volt peak to peak is so it's going to go up to 1 volt and down to 1 volt. This will make the math easy. So when it goes up, so from 0, it'll go to positive 1. So when it attenuates, if we get a voltage of 0.707 positive and negative 0.707, that's where we're hitting that 1 over square root of 2, which is that minus 3 dV. So it's real easy to see that. So use 1 volt or 10 volts makes it easy to do the math for you. Okay, so that is our signal generator. Now let's go take a look at our oscilloscope and let's see what's going on with that. Okay, so here is our oscilloscope. And so we've got two channels here. We've got channel 1 and channel 2. So let me get these things both at about the same scale. All right, so remember the scale is the voltage per division. All right, so now I've got them both at 1 volt because we're dealing with, as a matter of fact, let's make them smaller so it scales a little bit. We'll put them at 500 millivolts. So the whole signal would only take up 2 divisions plus and minus, right? Now let me split these signals so we can see them. So there's channel 1, there's channel 2, all right? And right now the sweep is happening at 8 microseconds, so we can change the sweep rate. That's this right here, and that's going to change how fast this sweeps. So we have no signal, so we don't see anything, okay? So, and then what we also are going to be able to do is we're able to press the measure button, and the measure button will then calculate this oscilloscope can do calculations itself, and we'll be able to see things so we don't have to eyeball them. It'll actually print out what these values are. All right, so we got everything going. So let's go back to the circuit. Here's the circuit. Everything's good. Everything's hooked up. So now all I'm going to do is I'm going to turn the signal generator on. I'm going to turn the output on. All right. So now the output is on, and let's see what we got here. So what I'm going to do is I'm changing the frequency because we're sweeping. We need to change the sweep rate here so we can see things. All right, and then sure enough, there we go. So we see our signals, and then again, if you eyeball this, so it's 500 millivolts and 500 millivolts per division for both channel 1, which is yellow, and channel 2, which is blue. This is the input, this is the output. So we're expecting plus and minus 1 volt. Well, if here's 0 right here, right, then there's about 1 volt. And there's about 1 volt, so it's correct. It is what we expect in both cases. And the current frequency on the signal generator is 10 hertz. So this is a low-pass filter. It's passing the 10 hertz untouched. Now, what I want to do now is I want to overlap these two signals so you can see them change in real time in reference to each other, kind of superimposed. All right, so I'm just going to put them right on top of each other, just like that. All right. Okay, so now we did the calculation 1 over 2 pi RC, and we found that with these two values of R and C, 1K and 0.1 microfarad, we expect that the minus 3 dB cutoff is at 1591 kilohertz, right? 1591 kilohertz. All right, so what I'm going to do is I'm going to go over here and I'm going to start changing the frequency of the signal generator. I've only got so many cameras, so you're not going to see that. I'll tell you what I'm doing though, and I want you to keep your eye on this screen, the oscilloscope. All right, 10 hertz, 20 hertz, 50 hertz, 100 hertz. Now, also as we do this, we see we're getting scrunched up here, so we want to change our sweep rate so we get unscrunched. All right. Now notice if you look closely, the blue signal is getting a little bit attenuated, just a teeny tiny bit. All right, just a teeny tiny bit. Now let's go ahead and let's turn on the measurements. So the blue here, if you can see it, yeah, the blue is the peak to peak of the blue signal, that's the output, and the yellow is the peak to peak of the yellow, which is the input. Notice they're both almost identical and they're both about 2 volts, which is what we expect because it's 2 volts peak to peak. So nothing's happening yet. Nothing's happening yet. It's just passing the signal. All right, so here we go. Now I'm going to keep increasing the frequency. Okay, there's 200 hertz, 300 hertz, 400 hertz, 500 hertz, 600 hertz. Now you should start to be seeing the tip of the channel 1 there. is definitely above channel 2. So channel 2 is now getting attenuated, which is the blue channel, but very slightly. Now there's another interesting thing that's going on here, which is you see the blue channel is getting phase shifted. Remember we talked about that phase shift? So the filter not only attenuates, but it shifts phase, right? There's a capacitor in there and there's a phase component. And this can be a big deal if all frequencies are getting phase shifted different amounts. The sound will not sound correct, or the signal will not be correct if you aren't taking that into consideration. Okay, so what I'm going to do is I'm going to start increasing the frequency some more, and we're currently at 700 hertz, and let's see what happens here. All right, so there's 700, 800, 1 kilohertz, 1.1, 1.2, 1.3, and you can see 1.4, 1.5. We're definitely attenuated now. Let's change the sweep rate a little bit. So now if we look at these two signals, we've got the yellow signal, which is our input, and you can see that the peak to peak is still 2 volts, which is what it should be. That's what we're sending out is 2 volts. But the blue signal now has been attenuated quite a bit. And if you just eyeball it, it looks like it's about 70% here. Now, if you take a look at the peak to peak value, it's 1.4 and some change. Well, 0.7, right, times 2 is 1.4. So we've hit the 3 dB, minus 3 dB point, and we're at 1500 hertz roughly. And if I put it, exactly, we could put it 1600 hertz. It's actually 1591 hertz. So 16 is more accurate. So it's 1.6 kilohertz or 1600, and that is the minus 3 dB. So that's it. Now, so that's where this filter starts kicking in. This is the cutoff. So now it's at 70% attenuation, all right? Now, if we keep increasing the frequency here, so now what I'm going to do is I'm going to put it to 2 kilohertz. There's 2 kilohertz, and you can see it's been attenuated even more. And keep your eye on the peak to peak of the blue, right? So now it's 1.24. Now I'm going to go 1 kilohertz at a time, all right? So there's 2 kilohertz, 3 kilohertz, 4 kilohertz, 5, 6, 7, 8, there's 10 kilohertz. And now at this point, you can see we've only got 360 millivolts peak to peak, or 180 millivolts peak. So it's very, very small. And there's 11, 12, 13, 14, 15 kilohertz, 16, 17, 18, 19, 20. And at this point, we have very little. All right, so again, that is exactly what a low-pass filter should do. And now let's bring the frequency back down and bringing it back down, 6 kilohertz. Let's change our sweep rate on the oscilloscope, 5 kilohertz, 4, 3, 2, 1 kilohertz, and then bring it down into the hundreds, bring it down to about 100 hertz. And sure enough, these signals are right on top of each other. Okay, so that's totally cool. That's exactly what we expect. Now, let's go back to the bench here, and let's change some values. All right, so we know that the function is 1 over 2 pi RC. All right, so let's go back to the blackboard and let's do another calculation. All right, so we're over here at the blackboard, and what we're interested in is we've got this F equals 1 over 2 pi RC. All right, so let's go ahead and change some values here. So what if we were to go in and we were to change R equals 10K ohms and leave C at 0.1 microfarads, all right? So it's either the cutoff frequency is either going to go up or it's going to go down, all right? So clearly, if it's in the denominator, that means we're going to have a larger number in the denominator, so it's going to go down, right? And that makes sense because if there's a larger R, the charging is going to be slower. So instead of being 1591 hertz, it'll be 159 hertz, right? So let's just do it just for fun. 2 times pi times 10 k ohms times 0.1 x to the minus 6, and then inverse that. And sure enough, it is 159. So if we have R equals 10K, then this gives us 159 hertz. If we have the above, we have 1,591 hertz. All right. Now, likewise, if we go down to 100 ohms, right? So now if we go down to 100 ohms, then we would expect instead of 1591, we would have what? We would have 15 910 hertz, right? So it'd be 15 kilohertz. All right, so let's give that a try. So let's go ahead and let's shift our frequency of our low pass filter to start its cutoff at 15 kilohertz by changing R to 100 ohms. All right, so we're just going to change R to 100 ohms, then we expect the cutoff to start being at about 15 kilohertz. So let's go back to the bench and do that. Okay, so we're back here on the bench, and what are we doing? We want to replace this 1 k ohm resistor with a 100 ohm resistor. Okay, so the first thing I'm going to do is I'm going to turn off the signal generator so there's no current here, and I'm just going to grab this guy. All right, so I took that out, and then I've got my 100 right here, and no, here's actually a 10. And I believe this is the 100, yep. Let me put it in front of the zoom camera here real quick for you, and I'll get it to zoom on there. Brown, black, brown, right? And then I'll get it to focus back on the oscilloscope for us. Okay. All right, so brown, black, brown. So I'm just going to put that where we had the 1K. All right. Now, something is going to happen here a little bit, and I'm not going to tell you yet. I want to see if you might have an idea of what's going to happen. So remember, we're driving this with a signal generator. So all I'm going to say is this: the signal generator has got finite current drive. It's a voltage device. It's not an amplifier. It's not going to drive amps of current, not even milliamps. It's very, very weak. So whenever you're driving a circuit, right, if you've got a very, very weak signal current-wise, you know, bad things might happen. So I'm not going to tell you anything. I want you to kind of think what might happen as we keep lowering this resistor. Aside from the low pass filter action that we're expecting, is anything else going to potentially happen in the circuit? So just kind of think about that for a second. All right, so everything's good. That's in the circuit now. So now we are going to turn this back on. We'll turn the signal generator back on. Okay, didn't explode, we're good. Let's look at the oscilloscope. So back here on the oscilloscope, it's what you expect. You can see that there's a 100 kilohertz signal coming in. You can see that the peak to peak of the yellow signal is 2 volts and some change as we expect. It's just not perfectly accurate. The blue signal is also tracking the 2 volts as we expect because there's no attenuation yet. We expect to see attenuation out at 15 kilohertz. So I'm at 100 hertz right now, so I'm just going to go up slowly here. 200, 300, 400, 600, now we're at 1,000 hertz, all right, 1,000 hertz. As you can see, I'll open this up. There's no attenuation yet, all right. Now let me go ahead and put it into thousands mode. So every time I click it, it'll go up by 1,000. So there's 1,000 hertz, 2,000 hertz, 3,000 hertz, 3 kilohertz. Now before, the signal would have been dying, right? But it's not. It's almost completely there. There's very little attenuation. You can see we've got our input signal at 2 volts and our output signal is just a little bit less, but you're starting to see the phase shift here, aren't you? See that? There you go. You can see that phase shift is starting to happen. All right, let's keep going. 3 kilohertz, 4 kilohertz, 5 kilohertz, 6 kilohertz, 7 kilohertz, and so on. But I want you to notice something else that's happening. Take a look at the yellow signal and look at its amplitude. If you can keep your eye on the amplitude. So I'm going to keep changing the frequency here. Notice how the yellow signal is also changing its amplitude. Can you see that? The reason why that's happening is the signal generator simply does not have enough drive to drive the 100 ohm resistor. So what's happening is we're getting a voltage decrease here, all right? So we just don't have enough drive to drive that. So when we get up to, here's 10 kilohertz, and then here is our 15 kilohertz. And let me open this up. So now we definitely see that the blue signal is smaller, right? So it's definitely been attenuated, and this is the -3 dB point. But we also notice that look at our yellow signal. Our input is at 1.6 volts. We've lost about 0.4 volts peak to peak. And the reason why is because the resistor is so small, right? Even though the filter action is what we want, we're at 15 kilohertz and we're seeing this -3 dB occur here, but we're losing power on the signal, right? And so we don't want that. We want the voltage on the output and input to do what they should do. We don't want the voltage on the input to change. So what's happening is we don't have enough drive on our signal generator. So what can we do about this? So we still want to have the same 3 dB cutoff point here, right? Minus 3 dB cutoff. Well, we changed the resistor to 100 ohms. Can we change it back to 1 kiloohms and instead change the capacitor? So let's change the capacitor so that we don't change the resistor, and let's see if we can fix it. All right, so I'm gonna basically turn off the signal generator. All right, so let's go back to the circuit here, pull out our resistor. Let's put back our 1K ohm resistor. So what you see me doing here is this is engineering. This is how it's give and take. So you see that you're losing a signal, right? You don't have enough drive. So you say to yourself, can I get the same filtering action by changing some other components so that I'm not using up all my drive on that resistor? Because at 1 volt, right, at 1 volt, plus and 1 volt minus, so at 1 volt, if we take 1 divided by the 100 ohms, so let's do it, right? So V equals I times R, so I equals V divided by R. So 1 volt divided by 100 ohms equals 10 milliamps. So we're dragging 10 milliamps out of this signal generator, and I think this thing can only like drive, it's ridiculously small, 20 milliamps or 100 milliamps it's supposed to, but what happens is the voltage starts getting attenuated out of it. So let's put that resistor back up to 1K. All right, we did that. Now, this is a 0.1 microfarad capacitor. So now what we want to do now is we want to change this capacitor so that we get the same action here. All right, so we want to change the capacitor so we get the same action. So let's go here. And instead of 0.1 microfarad, here is 0.01 microfarad, 0.01 microfarad. All right, so I'm just going to put that in here. All right, and now I'm going to adjust the signal generator back to 1 kilohertz, and I'm going to turn the signal on. All right, so there we go. The signal's on. All right, and it's at 1 kilohertz. All right, so now here's 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, 6 kilohertz, 7 kilohertz, 8 kilohertz, 9 kilohertz, 12 kilohertz we're on. Now let's change the sweep rate a little bit, right? So things are looking good. 13 kilohertz, 14, 15 kilohertz. So, and let's put it to 16 kilohertz. So at 16 kilohertz, we are, look at our yellow signal. Its peak to peak is still 2 volts. We haven't stepped on it. That's good. But now look at our blue signal. It's 1.4 and some change. It's exactly 2 times 0.707. It's exactly. So now we've got the filter action that we want. We've got the voltage in and the voltage out, but we haven't attenuated our input. So if we needed to take this input voltage someplace else and do something with it, we're not stepping on it. We're not modifying it, all right? So we have enough impedance in our filter so that the voltage action is happening, the filtering action is happening, but we aren't stepping on the current so much from the source so that we're modifying the voltage as well. So this is exactly what we want. So this is beautiful. So we have a perfect filter with a cutoff at roughly 16 kilohertz. And we can see here we've got our input, which hasn't been changed. And then we've got our output, which is 0.707 of one peak and 0.707 negative in the other direction, which is minus 3 dB or 70%, which is the cutoff. That's exactly what we want. All right. And again, if we keep going, 16, 17, 18, there's 20 kilohertz, 30 kilohertz, 40 kilohertz, 50 kilohertz, 60 kilohertz, 70, 80, and here's 100 kilohertz. And now notice our input frequency, our input voltage is still the same. We haven't messed with that, but our output voltage is now 400 millivolts, peak to peak, or 200 in each peak direction. And more or less that signal is down to like 20% of the original signal. So it's very, very small. So that is a low pass filter. So the one important thing that we learned here though was when we're engineering these things, sometimes, so what you want to do is you want signal to get through, but you don't want to make your resistor so small that you're going to attenuate your signal because you don't have enough current drive. And because we're using a signal generator, it simply does not have the current drive to drive this circuit, right? We would need an amplifier. So we had to be careful, and we noticed that as the circuit was working, it was like drawing too much current, and we were losing voltage, and we didn't want that. So we said, okay, well, instead of messing with the resistor, let's put that back up high, but then we'll take the capacitor and we'll make it lower, right? And we could now, so now we know 1K is kind of okay. We probably even want that to be 10K, and then we could keep messing with that capacitor, make it smaller and smaller and smaller up into the, high hundreds of kilohertz or megahertz or whatever, and go that way, all right? So that's a low pass filter for you. So let's go ahead and we're gonna go back to the blackboard, and we're gonna work on on the high pass filter very quickly, relatively speaking to how quick is with me. But we're going to do the high pass filter calculation really quick and derive that, and then we're going to come back and we are going to build that. All right, so that's what we're going to do next. All right, so I'll see you in the next lecture. Bye. All right, welcome back. So we just got done doing the bench work with the low pass filter. So now as promised, we're going to do a high pass filter now. And we're going to go through the same kind of derivation that we did with the low pass filter, except we're going to go much faster because there's less material to cover since we kind of already have an understanding now of the transfer functions and you know, what we need to do to get the final result. And then we're going to go to the bench and we're going to build the high pass filter as well and do the same experiment. All right. So low pass, high pass, and then we'll talk a little bit about band pass filters also. So right now let's do the high pass. All right. So let's see here. Let's get a trusty color. Let's go ahead and let's do this first. Let's kind of write down what we're going to be talking about here. So we're going to talk about high pass filters. And so these are filters that pass higher frequencies. And we're going to build it with the same R and C that we did last time. All right, so now just to refresh your memory. So last time we had a resistor like this. And in fact, you know what, we'll put this over here. So here is a low pass, because I want you to remember these constructions. So a low pass looks like this. It's got an R and a C, and here's the output. There's ground, there's the input. So we've got R, we've got C, this is V in, this is V out. That's what a low pass filter looks like. All right, so now what does a high pass filter look like? So the high pass filter looks like this. So we literally swap the capacitor and resistor. It's that easy, which is pretty cool. All right, and there's our resistor, and there's our ground. Okay, here's V out, and here is V in, and this is C, and this is R. So now we know exactly how to do this. We're doing this with complex impedances with Z values. So as far as we're concerned, it's just a voltage divider. And in this case, it's got the R down here instead of the C and the C up here instead of the R. But we're just going to do the calculation as if it's a voltage divider, which is a function which changes as a function of frequency f. We're going to leave f in all the calculations. Okay, so here we go. So let's do the capacitive reactance first. So we're getting pretty good at this. Okay, so what is the capacitive reactance equal to? So let's remember that. So x sub c equals 1 over 2 pi fc, right? And then what does the complex impedance, what's that? So that's z sub c equals 0. And then if you recall, it's minus x sub cj, right? And then remember our couple little, we know that minus j is equivalent to 1 over j, right? So we can write this in different ways. And then what's our complex impedance for R? Well, we're going to call that Z sub R, all right? And that is equal to R plus 0J. It has no imaginary component. So the complex impedance of the capacitor has no real component, and then the complex impedance of the resistor has no imaginary component. All right, so now we want to find V out over V in. Again, it's just a voltage divider, so you know if you want to find the output, right, it's simply the input times R, which is ZR, over ZR plus ZC, right? So that would be what the output equals, right? So that equals V out, all right? And then if we put V in over here, we divide both sides by V in, all right? And again, then we call this thing the transfer function H. So we can say H of F equals Z sub R over Z sub R plus Z sub C, all right? And that's it. We're basically done. So now we can start plugging in these values here and try and simplify this to make it clean. So we've got z sub r. What's z sub r? Just r. So this looks like r over r plus, and then we've got z sub c here. So for now, we'll just write it as minus x sub c times j. Okay, let's clean this up a little bit here. And again, we never know where we're going when we're doing these algebraic simplifications, so we kind of just work with it and see what happens. So we got x sub c sub j, x sub c times j. We got r and we got r. Let's go ahead and let's use this identity right here. All right, so we've got r over r plus x sub c over j. And then let's replace what x sub c equals. It's 1 over 2 pi fc. So let's do that right here. So now we have equals r over r plus 1 over j 2 pi fc. 2 pi fc. And I think that looks pretty correct. Let me move this over here. Okay. All right, and let's see here. Check myself with another reference here. Okay, all right. Okay, so so far so good. All right, now, so let's see. Let's go ahead and we'll multiply. So let's get rid of this j down here in the bottom here. And let's multiply everything by j 2 pi fc. Let's go ahead and do that, j 2 pi fc. All right, so we're going to multiply the top and the bottom by j 2 pi fc. So if I put j 2 pi fc over j 2 pi fc, and we're going to multiply everything. So this and this, we're going to cancel out. We're just going to get that 1. And then we're going to get r times this, right? And then we're going to get r times this. All right, so up top we have j 2 pi frc. And then down on the bottom, this is a 1 here, so we'll put the 1 there, plus, and then again we've got j 2 pi fc, so we've got j 2 pi frc. All right, so that is the transfer function for this. All right, and that looks correct. So that is our h sub f. All right. So now, again, and you can simplify this if in different ways. We could have left it like this if we wanted to. Sometimes you can leave it like that, or you can put it like this. A lot of times, people like to normalize these things and make the numerator a 1. But it's really up to you. Typically, you'll kind of see it in this format right here with the imaginary number j in the top and the bottom like this. Okay, so now let's go ahead and let's find the magnitude. All right, so this whole thing equals this h sub f, which is the transfer function. All right, so now let's find the magnitude of this. All right, and oops, if you have not been paying attention too much, to find the magnitude of this, so remember, all you have to do is, say if you have an imaginary number, we'll just call it z for a second here, and it's got an imaginary part, we'll just call this imaginary part, and then it's, oops, let's do it this way. Let's call it a real part plus an imaginary part times j. If you want the length of this vector, right, it's just the square root of rp squared plus ip squared. That is the length of that vector, or what the magnitude of the complex number. So that's all we got to do here. So up in the top, if we take the square of the square root of this, right, and we compute this, we only have an imaginary part. So up top, the magnitude of this is simply 2 pi frc. Down in the bottom, we're not so lucky. We have a real part and an imaginary part, so let's go ahead and do that. So we have the radical. So 1 squared is 1, plus we need this component right here, squared 2 pi frc. Got to be very careful not to leave out that square. All right, so that's it. So that is the magnitude, 2 pi frc over the square root of 1 plus 2 pi frc squared. All right, and just checking, that looks good, that's correct. All right, and then now the cutoff frequency of the high pass filter is exactly the same, and that makes sense because you would plug in the same value here to get your to get this radical to be equal to a 2. So we'll call this F, and we'll call this, you can call it H, or high pass cutoff, equals 1 over 2 pi RC. All right, and that was the exact same as the cutoff for the low pass. So we could put F of low pass also equals 1 over 2 pi RC. So the thing to remember here is this 2 pi RC, what this has to do with is the charging constant of this circuit. Whenever you have an RC circuit, the RC circuit doesn't care if it's C then R then C. The charging is going to happen the same way. The action of the circuit is going to be different depending on where you take the voltage. So if we take the voltage here in this configuration, we're going to get a high pass filter. But if we take the voltage here in this configuration off this node or off this node, we get a low pass filter, right? Because one of these devices' impedance is changing as a function of frequency. In this case, I want to grab this because this is not changing as a function of frequency right here. And then this one I grab here because this is changing as a function of frequency. So anyway, that's all there is to that. Okay, so there's our low pass filter. Here's our high pass filter. Let's go ahead and kind of circle this or put a square around it. So here is our high pass filter's transfer function, which was pretty easy to get. And then here's our magnitude of that, which basically we just did the formula right here, which is just really just finding the length of a vector in the imaginary plane. Okay, so now we're ready. All right, so now we're ready to actually, build the circuit. So let's take a look here briefly, though, at a couple interesting things here. So now, what does this transfer function look like? So if frequency F is down here and gain is here, all right. So the gain will never be greater than 1, right? Unity. So at 0 hertz, so when we're at 0 hertz, this thing should have a gain of 1, right? So at 0 hertz, it should have a gain of 1. So let's take a look at that. So if we go here, and where's our transfer function? Here's our transfer function. If we go ahead and we put in here's our magnitude of our transfer function. If we go ahead and we put in a 0 for F, the numerator goes to 0, right? So if we put a 0 for F, the numerator goes to 0. And if we put a 0 for F right here, then the denominator goes to square root of 1 plus 0, which is square root of 1, which is 1, which is 0 divided by 1, right? 0 divided by 1, which equals 0. So nothing funky happens there, right? So that's good. So at 0 hertz, the gain is equal to, excuse me. All right, so at 0 hertz, remember, this is a high pass filter, all right? So this is a high pass filter. So at 0 hertz, you could see the gain was just 0. So we actually just caught our own math error. So at 0 hertz, let's do that again. We put in a 0 into F. We get a 0 here, 0 over 1, all right? And in that case, we get 0. So the gain is absolutely 0. So now, at some point, this thing is going to, it's going to do this kind of thing. All right, and at some point, the gain of this, right, is going to get higher and higher and higher, and at some point, it's going to equal 1. Now, here's kind of the tricky part. The gain or the output V out over Vn will actually never reach 1 until infinity. All right, so since it's the opposite of the low pass filter at 0 hertz starts off with a gain of 1, unity, and then starts to attenuate, and then the appreciable attenuation is when we hit the FLP, which is 1 over 2 pi RC, then we'll be down minus 3 dB, or we'll be at 70%. The same thing happens here. So right here, at some point, so if this is a gain of 1 right here, right, at some point, this will be 0.707. That frequency right there is this FHP. So it works. It works in the opposite sense. You got to keep clear of that. Now, it keeps the gain keeps going towards one, going towards one. This curve is never flat. It's approaching this asymptote, which is this one line, right? But it will not reach it until infinity. And so, and we can actually look at that with the with a function here. So basically, as f starts approaching infinity, right? As f approaches infinity, the top and the bottom, right? In both cases, both approach infinity, and then you can do some derivatives or L'Hopital's rule here, and you can figure out this limit properly, and figure out that this limit goes to 1 as f goes to infinity. All right, so the point is, as frequency here goes to infinity, then finally this gain ends up asymptotically at 1, and that's it. So, but for normal use, all we really care about is this FHP, which is the point at which it's 70% of the signal. It's attenuated only 70%, and that's at 1 over 2 pi RC. So they work in these two filters, the low pass and the high pass work exactly the same. They're just in opposite senses. So one starts off at 0 hertz, the low pass, and it's passing. Then at the cutoff frequency, it starts attenuating, and then the high pass starts off at 0, and then it starts going up, and then at infinity, it's 1, but it starts going up, and then it hits 70% at the cutoff frequency, which is 1 over 2 pi RC in both cases. All right. That said, now let's put our values that we use. So if you remember, we had R equals 1K, and we had C equals 0.1 microfarad. All right, and so what is the FHP for that? It's 1 over 2 pi RC, which is 1K, times 0.1 microfarad. And if we do that math, let's go ahead and do it again. So 2 times pi times 1K times 0.1 microfarads. Invert that, and we get 1591 hertz, right? Which is exactly what we would expect. So this equals 1591 hertz, right? Or approximately equal to 1.6 kilohertz. So it's the exact same as the other filter. So interestingly enough, if we were to draw these two filters together, so here's the high pass version of the filter, and then if we were to take and also build the low pass version of the filter, it would look like something like this. All right, and then if you took these two filters and you combine them by putting them in series, they become multiplicative, and the final transfer function looks like this. It looks like that. And this and here, let me fill this in. And this becomes what's called a bandpass filter. Okay? Bandpass filter. So that's how you would filter out just a narrow band of frequencies. You do a bandpass filter. Okay, so that's it. So the high pass filter is exactly identical to the low pass filter, except we switch the position of the capacitor and the resistor, and then we're going to use the same values here. So now when we build this, it's going to be a high pass filter. So at 0 hertz, we're going to have no gain at all, or we're going to have 100% attenuation. Then as we increase the frequency towards the cutoff frequency, right, as we increase it towards the cutoff frequency, here in this diagram, then this filter is going to stop attenuating, and we're going to start seeing our signal out greater and greater and greater, and then it'll start going towards unity, and the output will look like the input. All right, and that's exactly what we want for a high pass filter. So at some frequency, we want it to cut in and start passing. Okay, so let's go ahead and let's go over to the bench and let's build this. All right, so I'll meet you at the bench. Okay, so we're here on the bench, and let's take a look at what I've got here. So I've just kind of gone ahead and put a couple components down, and let's take a look here. So all I did was I just changed, I put this right here. I changed the position of the capacitor and the resistor. Let's see if we can get that to focus a little bit. It's not cooperating with us. Okay, there we go. So I changed the position of the capacitor and the resistor, and I'm taking V out from, that node right there. And so now we've got the capacitor and the resistor. We've got 1K and we've got 0.1 microfarad. So just like we had when we started off with the low pass filter, so this is going to be our high pass filter. Again, we've got our input here, which is going to be on channel 1 yellow on the oscilloscope. And then here's the actual input coming from the signal generator, which you're not seeing right now. And here's channel 2, which is going to be the output, so we can see that. All right. And once again, let's go take a look at the signal generator. If you had skipped the previous episode, so that you can kind of see what's going on here. Here is the signal generator, and we're using the output of channel 1 to drive this. And right now, I've got it set at 100 hertz. And then we've got it for an amplitude of 2 volts peak to peak, and we're putting out a sine wave, 2 volts peak to peak. And so that means it's going to have a positive peak of a volt and a negative peak of -1 volt. And the reason why I like that is it makes the math easy. So we know that the positive half of the sine wave is 1 and the negative half is -1, so we can figure out 0.707 times that is just 0.707. So that makes things nice. So I'm not going to show you this as we are doing the experiment. I'll just talk to you, and all I'm going to do is turn the output on and then adjust the frequency. So here's the frequency adjustment. I'm adjusting it right there, and I'll tell you as I'm going. Okay, so where the real action is going to happen here is on the oscilloscope. So let's take a look at this. So we've got channel 1 is the yellow channel, and channel 2 is the blue channel. And I've got them set. I've got the vertical amplification gain set or per division set at 500 millivolts per division, 500 millivolts per division on both channels. And that's because we know our signal is 2 volts, so that's going to be a total stride of 4 divisions roughly, right? So we'll have a signal that we can see. And then we're just going to start off for our sweep at 4 milliseconds, 2 milliseconds, doesn't really matter. And the second I turn this on, I'll start messing with it. Okay, so we've got everything good to go. So now what I'm going to do is I'm going to turn on the signal generator, which is currently running at 100 hertz. And we can even turn this down if you like to 10 hertz, which is practically 0 hertz. So 10 hertz, 2 volts peak to peak. All right, here we go. We're going to turn that on. All right, the circuit didn't explode. Now, immediately, if you take a look at the oscilloscope here, we can see the signal. All right, so our input signal, which is the yellow signal, is obviously showing up, and there's no attenuation on it. So let's go turn the measurement on here. All right, so if you look at the measurement here, we can see that our yellow signal is 2.06 volts, so it's 2 volts, which is what it should be. And then if we look at the blue signal, it's hovering around, 80 millivolts, 100 millivolts. And remember, high pass and low pass filters, they're never truly completely off or completely on. Only at 0 and at infinity do those two things happen. So everywhere in between, they're slightly on or slightly off, etc. Okay, all right, now let's go ahead and let's start turning the frequency up. So we're at 10 hertz right now. So first let me get this thing to 100 hertz. All right, and we see nothing. All right, so we see nothing big. We see now, look, the signal is getting less attenuated here because this is a high pass filter. So it's starting to pass the signal. And it's passing it at 100 hertz, right? And this is, and again, these filters, these passive filters, are not very accurate. Now, what you would like is at 1591 hertz, the thing just turns on, but that's not the case, right? There's a curve to this. Okay, so there's 100 hertz, 200, 300, 400, 500, and as you can see, now we're starting to see that blue signal. So I'm gonna overlap the signals like I did last time, so you can kind of see this better. All right, there you go. So we're seeing the signals overlap, and we're definitely getting more gain on the blue signal, or less attenuation, however you want to think of it, 600, 700, 800, 900, and 1000. So we're getting there, and we predict at 1591 or roughly 1600, 1.6 kilohertz, we should be at about 0.707. So there it is, 1600 kilohertz. You can see it right there. Excuse me, 1600 hertz or 1.6 kilohertz. And now At that, we should be at minus 3 dB or 0.707 of the signal. The signal is, what is the signal? It is 1 volt peak or 2 volts peak to peak. So we should be seeing about 1.4 volts-ish, and there it is. We're seeing 1.5 volts, which is what we would expect within an error. And now I will bring the frequency up a little bit more, 1.7, and then I'll bring it back down to 1.5. So see that 3 dB is right about there at 1.4. All right, so there's a little, and remember, the capacitor is probably a 20% capacitor, the resistor is a 5% resistor, so this is very, very accurate. This is very good, so we should be very happy with this. Okay, so you can see the frequency here as I change it, even if I don't call it out. So now I'm going to put it to 2 kilohertz. All right, and now you can see we're still not at, even at 2 kilohertz, we're not at 100%. We're not at unity gain, right? The signal is 2.04 and we're at 1.6, but we're getting there. 2 kilohertz, 3, 4, 5, 6, and at 6 we're very, very close. We're at 1.92, 7, 8, 9. At 10 kilohertz, we're pretty much on top of it. Right, so it's 2.02 is the input, and we're getting out 1.96. And now we could go to 20 kilohertz. We could go to 40 kilohertz. We could go to 100 kilohertz. And again, what I want to bring your attention to is the input here. It is 2.06 and 2.04, 2.02 and 2. It's never ever, and we can scale this a little. Let's scale this so we can see this a little bit better. And I'm going to scroll this down. And we want to make sure we got both of these at 200 millivolts, and we want to get these on top of each other. Okay, and get these both on the same scale. So you can see now they look like they're exactly, and within the accuracy of this oscilloscope, they are mimicking each other. But we know that if we were to measure this with very, very accurate equipment, it's not true. Only at infinity will that gain be unity, 1.0. All right, and I bet you, let's see, if we were to put this to 100 millivolts, let's see. It's kind of hard to measure this and kind of line these things up to get this properly. Now, one other fun feature. Let me show you this real quick. This is just a little kind of sidebar. If we take these two signals. Let's line these things up. And again, this is also hard to do, to line these signals up here. And you have to look at this right here. See, it's 40 millivolt, 20 millivolt. Okay, 0. And then this one here, 40, this one, 0, 0. So now they're perfectly lined up. Now what we can do is we can go and to this math menu here, and you see the operation here, C1 plus C2, and the result is this purple, C1 minus C2, and there we go. There's C1 minus C2, C2 minus C, all these different variations, and what this kind of helps you do is let's do a multiplication, so a division of them. All right, and then what's interesting here is if we turn this gain up, you can kind of see, you can't really see it, but you can see these little spikes. So anyway, the math menu is also helpful to do the mathematics to the two waveforms and process them against each other, and then you can get other kind of interesting results to kind of see things. So, all right, so now we're at 100 kilohertz. Let's put the measurement back on. We're at 100 kilohertz here, and so let's go back to our circuit. So here we are back at the circuit here, and we've got our 1K and we've got our 0.1 microfarad here. So if you recall in the last circuit, what we did was we switched this to 100 ohm, and then we found out it was too much attenuation. It drew too much current, and then so we switched the capacitor and made that a smaller capacitor. So let's just skip right to the capacitor part. So I'm going to turn off the signal generator, and I'm going to grab our 0.01 microfarad, and I'm going to replace the 0.1 microfarad. All right. Okay, and then I'm going to go to the signal generator and put it back at 100 hertz, and I'm going to turn this whole thing back on. All right. Now let's go back over to the oscilloscope. Let's put this back to 500 millivolts per division. Let's separate these out. Okay, so there's the input in yellow, there's the output in blue. All right, And let's go ahead and let's turn on the signal generator. All right, so signal generator is on. Okay, so 100 hertz, and what we've got to do here is we've got to change this sweep rate so we can see the signal. All right, there we go. And let's line it up here a little bit so we can see it. You know, and with oscilloscopes, this happens sometimes. You're like, where'd the signal go? And you got to remember, you know, you're looking at it the wrong speed or the wrong amplitude or the wrong this or the wrong that. So you just have to kind of play with these things and get them to work right. Okay, so now let's go ahead and we look at the blue line, and this is the output. So the signal is completely attenuated, and it should be because it's at 100 hertz. Now, if we change that capacitor to 0.01 microfarad, 0.01 microfarad, now we remember that the 3 dB, the minus 3 dB, for either the low pass or the high pass, the formula is the same. It's 1 over 2 pi RC. That's going to go up to 15 kilohertz, right? So 15.9 kilohertz, right? It was 1,591 hertz or 1.5 kilohertz. Now it's going to be 15 kilohertz, right? Or 15.9 kilohertz exactly, all right? So let's just call it kind of 16 kilohertz. So let's increase the frequency. So keep your eye on this right here, even as I call this out, if I miss it, 200, 300, 400, 500. Okay, now we're at 1 kilohertz. And now notice that the filter is starting to turn on a little bit. All right, now let's go to 2 kilohertz. Now before, the filter would have been much more on. It would have been passing much greater, the previous version that had the 0.1 microfarad. But since we have this new version that has the 0.01 microfarad, we've pushed out the 3 dB, minus 3 dB point all the way to almost 16 kilohertz. So let's keep going. 2, 3, 4, 5, 6, 7, 8, 9, 10 kilohertz. All right, so 10 kilohertz, we're almost there. Now I'm going to merge the two signals and put them on top of each other so you can see it a little bit better. So we'll just line these things up close enough. And it's always a little bit of a challenge to get these things lined up. Okay, there we go. All right, and look at our peak-to-peak of the blue. What we're looking for is 1.4-ish. That's when we know we're at that minus 3 dB point. All right, and we shouldn't be there yet because we're at 10 kilohertz. Now we're at 11 kilohertz. We're at 12 kilohertz, 13 kilohertz. We're at 14 kilohertz. We're at 15 kilohertz. Now look at that. Almost perfect. We're at 15 kilohertz. We go to 16 kilohertz, and there it is. We're almost dead on at 0.707 peak or 1.44 peak to peak. And we're at 16 kilohertz on the signal generator. And I could put it to 15.9 with all the decimals if I wanted to. But again, it doesn't matter. Why? Come back to the circuit here. These components, the resistor is only 5% accurate. This is a 5% resistor. And this capacitor, we're lucky if this is a 20% capacitor. I think it's a 10 or 20% capacitor. All right. So your components are going to make you be inaccurate all over the place. And again, this is why we do things in powers of 10. We're not so interested in 5%, 10%, 20% when you're making filters and amplifiers. We're interested in tens and hundreds and thousands, orders of magnitude. So that's why you can tolerate it. And that's why when you design circuits, if they cannot tolerate your component shifting plus or minus 5% or 10% and the circuit breaks, you're a bad designer. So you need to learn to design this better to be more tolerant of the values going plus and minus some amount, and it should work in the whole range, which brings me to an important note. When you do design circuits, you need to test them at the extremes of those cases. So if you design a circuit and just grab some parts, if this thing is on the fence and barely working, right, whatever it is, a filter, this and that, it's going to fail if you take the components to the high error or the low error, the plus 5% or minus 5%. So you want to test that at those extremes and make sure your circuit works and it's robust, okay? All right, so that's the high pass filter. Let's go back to the board and take a look at a couple other things. Okay, so we're back here, and so we've done the low pass filter, we've done the high pass filter, we've talked about the concept of the band pass filter here. So what I'd like you to do is take the design for the low pass filter and take the design for the high pass filter, and then go ahead and try and build something that has a transfer function that looks like this. So what we want is try and do something that out here somewhere passes a signal. All right, and we might call this FC for the center frequency, and just make it anything you want, anything that you want, but push it out there, all right? So anyway, so that's it. So now what we're going to do is we're going to talk about low pass and high pass with inductors, which is identical. Again, we'll go pretty quick, and then we're just going to build one of those versions, because the problem with inductors, you need massive inductor values to do these filters properly. So I believe if we work it out, we're going to do a high pass filter, but we'll look at both low pass and high pass with inductors. So all we're going to do is we're going to replace the C's with L's. The C's with L's, right? So we'll have our little inductor there, and we'll have our little inductor there. And we're just going to do the same calculation. We're going to figure out the transfer functions, and that's what we're going to do next. Okay, so I'll see you in the next lecture. Bye. All right, welcome back, and we're on the next lecture here, and we are going to do, now we're going to do RL circuits, or LR circuits, whichever way you like to say it. So to refresh our memory, last time we did the RC circuit, we did the low pass and high pass filter derivation, and then we actually built both of those filters on the bench. So now what we're going to do is we're going to do the same thing with an RL circuit, except we're just going to go a little bit faster because we kind of know what we're doing here, and we don't have to go over all the other material like decibels and all that. Okay, so let's just jump right into this. And I think now most of you are going to be able to follow along, and you're going to probably get ahead of me as I'm doing this, because you're going to just see where this is going. All right, so what are we doing? We're going to be doing LR filters. All right, and let's start off, we'll do both constructions. So let's start off with this construction here, which is we're going to do a low pass filter. And this is what it looks like. So we come in here, our VN, and then we have our inductor, all right, and out here, and then we have our resistor to ground, and this is going to be V out, and this is going to be VN. And again, we can call that VI, and we call that VO or VN and V out, whatever. And this is going to be L, and this is going to be R. Now, this is a low pass filter. Now, I'll be honest with you. No one, if you're using these every day, you'll have them memorized. For capacitors, I memorize these constructions. But when you use inductors, sometimes you have to think about it, and you might have it flipped around. So a low pass filter with a capacitor, the resistor is here and the capacitor is here, but with a inductor, the inductor is here and the resistor is here. It's flipped, so they're mirrors of each other. So the low pass and high pass with RC is the high pass and low pass with the LR. The components are swapped, and the reason why they're swapped is because when you look at the transfer function or the reactance of the inductor compared to the capacitor, they're inverts of each other, right? So one of them, in this case, we have, let's get another color here. We have X sub L. What does X sub L equals? It equals 2 pi FL. But remember, what does X sub C equals? X sub C equals 1 over 2 pi FC. So because we're using X sub L and X sub C to create this voltage divider action, and they're inverts, right? Of course, one's got an L and one's got a C, but they're inverts of each other relative to the frequency. They act in opposite ways, so we basically flip these components. So the moral of the story is, if you can remember what an RC low-pass filter looks like, from that you can figure out what an RC high-pass filter looks like, and from those you can figure out what the inductive based RL or LR low pass and high pass look like. So if you can just remember one of them, then you can derive all the rest and figure out where to put the components, or you can just do the math. Okay, so that's what X sub L is. Okay, so all we want to do here is we want to figure out what the voltage divider action is, and we want to figure out what the voltage is at that node, or the ratio of the output to the input. We know that the inductive reactance is 2 pi FL, and for the resistor there is no reactance, it's just R. All right, so let's write down the complex impedances. So Z sub L equals 0 plus J X sub L. All right, and then Z sub R equals R plus 0J. All right, and I like to write these out every time, even with the zeros there, to hold places because these are complex numbers. And again, remember, this is the real part of the number, and this is the imaginary part of the number. All right, imaginary part. So always remember that, and they're complex numbers, and if we want to plot them, we could plot them in a complex plane if we want, right? Okay, so there are the two impedances. So now let's just use the voltage divider law, right? So we want to compute V out, all right? So V out equals, what does it equal? It equals V in times what? It equals R, this value here, its impedance, which is ZR, over ZR plus ZL, right? That's it. Okay, so now, and now we want the transfer function here, so we're just going to divide both sides by Vn, or just move this over here, right? Move this over to this side, Vn. So now we have what we're going to be calling H sub f. Let me make that a better F. That is a horrible F. My little handwriting F, there we go, equals ZR over ZR plus ZL. So let's put in the actual values here. So there's just going to be an R up in the numerator, right? You agree with that? And then down in the denominator, we're going to have R plus JXL. JXL. All right, so that's good. Okay. All right. Now, so we're basically done. We could replace x sub c right here if we wanted to right now, right? We could just put 2 pi fl in there, right? We could just put 2 pi fl replace for xc. Now, typically again, when you see these transfer functions, right, they're in certain formats, and they're just algebraic versions of each other. And typically, people like to write things without these r's. They like ones in these positions. So what we can do is we can just divide everything by r. All right. And also, the reason why we divide by r is because we want the math to bear out that the cutoff frequency is a function of R over L or L over R. So when we get done with this, we'll see that if we divide by R. But this is correct. We're done. Right now, this would be just fine. But sometimes you want to do a little bit more math. So let's go ahead and let's divide the top and the bottom by R. Okay. And remember, you have to divide everything by it. All right. We're going to divide by R there. All right. So now let's write this down again. So what do we have? We have 1 over 1 plus, so that we've got our j here still, and now we have our x sub c, which is 2 pi fl now over r. 2 pi fl over r. All right, so now what's nice is you can see that when we did that, we've got these nice ones. Ones are always nice. We like ones. And then we've got this L over R term here. All right, that L over R term. And that's nice because that's going to kind of be a nice way, a compact way to maintain the L and the R in different equations, and then be able to write things in terms of that. So since we've transformed this into this format, it's going to help us down the line. Okay, all right. So now let's see, what are we doing here? All right, so let's write this down. Our final transfer function here, h sub f. And that looks like an E, doesn't it? Let me fix that. Okay. H sub f equals 1 over 1 plus j 2 pi f L over R. All right, let's be careful. Okay, so that's it right there. So now we are done. So that is the transfer function for this filter right here, which I'm telling you is a low-pass filter. Okay, so let's go ahead now. Let's figure out what the magnitude of this is, right? So we want to figure out what the magnitude of this is. So if we were to say, what's the magnitude of this h sub f, right? So that we can figure out what the final voltage is. So what's that? Well, the magnitude of the numerator is just 1. And then down on the bottom, we have the same situation. We're just going to get a square root of, remember, we got to find the length of this vector. Here's the real part, here's the imaginary part. So it's 1 squared, which is just 1, plus, and then remember, we square this component right here, so it's 2 pi f L over R quantity squared. Okay? And let me kind of do that. There we go. So that's it. So that's the magnitude of it. So now we're done. So very quickly we've done what we've been doing with the R and C in short order here. All right. So now let's figure out. So what kinds of things can we figure out? So the first thing let's figure out. Let's take a look at this at DC. All right. So at DC, or when f equals 0 hertz, what's going on here? So if we put in a 0 here for f, right, we put a 0 in for f right there, right? This term then is going to do what? This term is going to go to 0, so we're going to get the square root of 1, right, which is 1. 1 over 1 equals 1. So at f equals 0, right, the gain, this h sub f, equals to 1, all right? So at DC, we've got basically this going on. So if we make our little plot here, where here's f down here, and here's gain right here, all right? And let's use, I never use white color. I like this color. Here's 1.0. There's the gain right there. All right, so we're starting off, and we're saying at DC, so let's go here, and this is 0 hertz, right, which is DC. We're saying that when we start off right there, we've got a gain of 1.0, or there's no attenuation. So we can pretty much tell that this is going to be a low-pass filter, and it's going to look like this, right? And then the other thing that we know about is there's going to be some point right here, right? There's going to be some point here, and we're going to call this, we can call this F, and then we can say that this is the cutoff, right? So this is a low pass filter. So this is, low pass filter cutoff. And at that F right there, we know that the value is going to be down 3 dB, which really means it's approximately equal to 0.707 is the gain over here. So then we kind of come across here and we say that, right here, this would be at 0.707. That means the filter is appreciably working. And that 0.707, what is that equivalent to? That is 1 over the square root of 2. So let's figure out what the cutoff frequency is. So can we derive it from this? Sure we can. All right, so let's grab another color here. All right, so let's just take a look at this. Just look at this guy down here. And remember, so what we need is we need 1 over the square root of 2. All right, so let's do this math slow. And those of you that just don't like math, I want you to like math. Math is not hard. It's a game really, and it's a really fun game that you can never learn all the way. So it's a lot of fun, but you're in school you're pressured to learn it to take tests, which is not what it's supposed to all be about. So let's take our time with it always and see if we can figure things out. All right, so we want 1 plus something here. And so here's that something. So what do we want to make this 1 over square root of 2? We know we want it to equal this because we know that the gain at the minus 3 dB point is 0.707, which is this 1 over square root of 2. So this question mark must equal a 1. Well, what's in that question mark spot? It's this expression right here. This expression right here, we want that to equal to 1. So let's do it. So what's that expression? It's 2 pi f L over R, and this whole thing is squared, equals 1. We want that to equal to 1. All right, so let's take the square root of both sides, right? So if we take the square root of both sides, square root of something squared is just the something, and the square root of 1, of course, is 1. So now we're left back with this. Let's write this up here. So now we have 2 pi f L over R equals 1. All right, so now I've got f here. All right, so I've got f right here. Okay, so now let's just start moving things over to the other side here. All right, so I'm going to take the 2 pi and I'm going to move that over here. So I'll just get rid of that and I'll put the 2 pi over here. All right, and then I'm going to move the L and the R over here. So I'm going to move the R over here and I'll move the L under here. So we'll end up with an R up here and an L down there. All right, so now we are left with F equals R over L 2 pi, all right, or 2 pi L, however you want to write that. So that's it right there. Okay, now Another way that you might see this is in terms of omega, which is angular frequency. So instead of frequency, so remember that what omega equals 2 pi f. All right. So f in terms of omega equals what? F equals omega over 2 pi, right? And so instead of hertz, we're trying to figure something out in radians per second, omega. So now if we replace f with 2 pi, so we get, we're going to take this f and we're going to replace this here, this expression here, w over 2 pi, we're going to plug into that f, right? And now what we're going to end up with is this. We're going to end up with omega over 2 pi equals r over L 2 pi. And then guess what? Those cancel out. So now we're left with omega equals r over L. All right, so omega equals r over L, or a frequency equals r over L times 2 pi. So the point is that this cutoff frequency here is this. So it's r over L 2 pi. All right, r over L 2 pi in hertz. All right, so that's it. So it's r over L 2 pi or 2 pi L, whatever you want to, however you want to write that. So let's see here. I'm trying to find a good spot to write this in. Why don't we, yeah, we'll put it right here again. Let's just put it right here one more time. So I'm going to say F LP, or which is, we're calling this, the cutoff frequency, equals 1 over R over L 2 pi. So it's just, so it's just R over L, and then we can put the 2 pi here if we want, or there, whatever. So it's R over L, and there's a factor of 2 pi. Okay, so now we know everything about this, and we can do some calculations. So let's go ahead and let's erase a little bit something here that we don't need. Why don't we, let's just erase this, okay? I'm going to erase this little omega derivation here. Okay, and let's go ahead and let's do a calculation here with some actual values, okay? So let's go get some values. All right, so let's say that R equals 1K ohm. All right, and let's say that L equals, and I'm going to try and think of values that I actually have for inductors. Let's see, I think I have a nice 330 microhenry. Remember, inductors are measured in henries, microhenry. All right, so now what the question is what's the cutoff frequency for that? So the cutoff frequency is F, LP we're calling it, is equal to R over L 2 pi. So what's R? So we've got 1K ohm here over, we've got our little 2 pi factor there, and then we've got our L, which is 330 microhenries. All right. Okay, so let's get our calculator out here and let's see what we see. So we're going to take 1K and we're going to divide that by 2 times pi times 330 microhenries. All right, and the answer is, take a look here. Let me see here. Can you see that? Yep. All right, so I'm just going to put that into, so this is 482.28 kilohertz. All right, so equals 482.28 kilohertz. All right, is the cutoff. All right, so now let's see if that is correct. So let's use an online tool. So what I'm going to do here is I'm going to grab that tool, remember that we're using, all right, and here we go here. All right, 330 microhenries. Okay, so here is that website again, this sim.okawa.denshi.japan, and we Googled and we found this nice set of filters here online where we can just put values into. So what do we want? We want the LR low pass filter tools, okay? And then here it is here. And then if you look, this is our construction. We've got our L and our R. Let's check. Is that what we've got? Yep, we've got an L and we've got an R, right? And now we want to put in our values here. So let's put in 1,000 ohms. And remember, it's in ohms and henries, so you got to be careful here. And 330 e to the minus 6, all right, microhenries. And then we'll click calculate. All right, and then we look at the value, and it's 482,287 or 482 kilohertz. And so what did we get? 482.28 kilohertz. Check that again. 482.28 kilohertz. So that is correct. So our math is correct. So we did the math correctly, which is always a good thing. And so now we're done. So now if we were to build this circuit right here, we would see that this low pass filter, where's my pen? We would see that this low pass filter, come back over here, we'll get another color here so we can see what I'm drawing. Right here at this point, this thing would start to, cutting in and start attenuating, and what's that point in this case with these two values right here is 482 kilohertz, 482 and some change kilohertz, right, is where that would start happening. So maybe at a couple megahertz, it would be the signal would be pretty attenuated. So you can see here that one thing that starts happening is these frequencies are very high. So you need very large inductors. You need very large inductors to kind of make these filters. Otherwise, if the values are small, because the inductor action, the inductive reactance is a straight multiple, right? It's this instead of 1 over this. So we have to have very large numbers. Otherwise, the frequencies that we start playing with are very high. So the point that I'm telling you this is when you need to make a low pass or a high pass filter, a lot of times it'll be easier to do that and source that with an RC circuit rather than an LR circuit or RL circuit, because the inductor you may need a very large value of the inductor to get the filtering action that you want, and inductors are much more expensive than capacitors are. However, the reason why we like inductors and filters is because they have very high Q. All right. And this is something I don't want to discuss, but the Q is called the quality factor, and there's lots of different things that it means. But in a nutshell, inductors are very pure. In other words, a capacitor has a lot of extraneous components to it. It has resistance to it, it has capacitance, it has inductance, right? An inductor only has inductance and a little bit of resistance, so it's a purer part. So in other words, when you build circuits with inductors, they're more accurate and their models are more simplified. So if you do a design with capacitors, ideally you'd use a real capacitor model, which is a capacitor, a resistor, and an inductor. All right, but with an inductor, it's just a inductor and a resistor. It's much simpler to model and you get much better results, but they're more expensive. Okay, but if you want to do high frequency work, if you're doing RF level work, IF or RF, that means intermediate frequency or radio frequency, up in megahertz or gigahertz or terahertz or whatever hertz you want to use, then inductors you typically use because that's where those frequencies are easy to operate with, and then capacitors at high frequencies, depending on the type of capacitor, don't function properly, or their values vary. So okay, all right. So anyway, so there are that's the low pass filter. Okay, so what I'd like to do now is I'd just like to pause here, and we're going to come back for another video, and we're going to do the high pass filter on the board here briefly, and then we're going to go and we will build both of them on the bench. All right, so that's what we're going to do. So let's stop here. Kind of a short video for what we usually do, and let's come back and we will do the high pass version of this, which is almost identical. All right, so I'll see you there. Bye. Right, welcome back. So we just did the low pass LR or RL filter, and now we're going to do the high pass version of the math and kind of derive it, and then we're going to go to the bench and build both of these. All right, so as you can see, we're getting better at this, and we're able to do this much faster. So before I erase everything here, let's circle a couple things. So what did we find? We found that the cutoff frequency is this expression right here. It's this R over L 2 pi, or it is, where did we have it in omega terms? I think we erased it, but in omega terms, omega cutoff would just simply equal R over L. And that's why people like just using omega instead of frequency. So omega is in radians per second, frequency is hertz, just cycles per second. We get rid of that 2 pi and it's cleaner. It's just R over L. Either way, there it is again. We wrote it up here. So the cutoff is R over 2 pi L. All right, for the low pass, and the low pass again is just like the RC low pass, but we said that the inductive value's got to be very, very high if you want to get lower frequencies. So that's why we typically use RC circuits instead of RL circuits. So we use Ls when we want kind of higher frequencies and purer circuits with better Q, and we talked briefly about that Q. Okay, so take a mental image of this. We're going to erase this, and we're going to do the high pass filter. So let's remember that we had our inductor here, we had a resistor here. We're going to flip that around now. So let's just go ahead and erase this. Okay, so here we go. So what are we going to do now? We're going to do LR, and we're going to do a high pass filter. All right. And again, you can call this LR or RL. It depends. Some people call it one way, some people call it the other way. I guess I should probably call it RL because I call things RC. But I don't know. I like emphasizing the L for some reason. It's just a preference. Okay, so let's draw the circuit. So the high pass filter. What does that look like? The high pass filter looks like this. Now there's a resistor here, and now the inductor is here. All right, so the LR high pass filter looks very similar to the RC low pass filter, right? The reactive component and the resistive component are in the same position, but then they have opposite operation. All right, and here's our L. Okay, and again, we've got V in here. We've got V out here. Again, this is always assumed to be relative to ground. This is always assumed to be relative to ground, right? Okay, so let's do our math here. So what do we know here? What is the inductive reactance? Inductive reactance, X sub L, simply equals 2 pi FL, right? Okay, so we have that, and now let's write our impedances. So let's just come down here and we're going to say ZR is just simply R plus 0J, and then ZL is 0 plus J times X sub L. All right, and here's a little note. Remember, X sub C is minus J. There's a minus, right? Because capacitive reactance and inductive reactance are in opposite directions in that imaginary plane, right? They're exact opposite of each other. Okay, so we have our two impedances. Now let's compute. We want to figure out what the voltage is at that node right there. It's simply a voltage divider. We're going to do it with complex impedances, Z's instead of R's. So it's simply this impedance over the sum of this impedance plus this impedance, right? Okay, so and then this time let's just skip and write V out over V in instead of manipulating it, and that's going to equal this ZL over ZL plus ZR. All right, and of course this whole thing right here is our transfer function. H sub F is this. All right, same thing. All right, Z sub L over Z sub L plus Z sub R. Okay, now at this point, again, we just want to simplify this so we can work with it and so that we can maybe see something in the math that we can relate to something else easily. Moreover, we like things to be normalized. We like things to be in forms of with one, having ones in it or zeros in it, or we want to see the R and the L very cleanly. So we're going to manipulate this again, and there's lots of ways to do it. So, all right, so Z sub L is just J sub X sub L. So let's just start writing these things out here. So up in the numerator, we've got J 2 pi FL. All right, and then down in the denominator, we've got Z sub R plus Z sub L. So we're just basically going to get, let's write it like this. We'll write it R plus J 2 pi FL. All right, so at this point right here, we've got this this imaginary number up in the numerator, and we could leave it there if we wanted to. There's nothing wrong with doing that, but let's see if we can manipulate this a little bit and play with it. And again, there's no right or wrong way to do this. So let's go ahead and let's divide everything. Let's divide everything by j2 pi fl. Let's give that a try. So we're going to divide top and bottom by j2 pi fl. All right, and j2 pi fl and j2 pi fl. So we're going to have a 1 up here. This is going to turn to a 1, and then we're just going to get this expression right here. So let's take a look at that. Let's see what that looks like. We like that. So 1, I'm going to just take this 1 and move it here, plus, and then we're just going to get this r over, we'll put the L here, we'll put the J here, and then we'll put the 2 pi here. Is that okay? So now look at that. So that's interesting. So we've got 1 over 1 plus r over JL 2 pi, right? So there's that r over L that we like again. So we're getting that r over L, and there's that 2 pi. So this is very, very similar to the low pass filter, right? But now we've got this J in this position right here. Okay, so what can we do with that? All right, again, let's remember some of our identities. So J squared equals -1 minus J equals 1 over J. So that's the one we want to use. Minus J equals 1 over J. So we're going to turn this 1 over J here into a minus J. Okay, so let's just write that right down here. So this is 1 over 1 minus J over R L 2 pi. Okay, that is our transfer function. So, all right, so that's it. So that looks really good. So we've got this transfer function here, and it's got 1s in it. We got this minus here. That's fine. All looks good. So now we're done. So now at this point we can go ahead and we can find the magnitude of it. So let's go ahead and let's write it back up here one more time. So h sub f equals 1 over 1 minus r j. We'll put the j up here. R over L 2 pi. Okay. All right. So we've got this right here. And now what we want to do is we want to find the magnitude of that. So we're going to go ahead and compute magnitude here. We'll say the magnitude of h sub f, right? And remember how we do that. It's the square root of the square of the real part and the imaginary part. Up in the numerator, there's only a 1, so the 1 squared square root is 1. Then down here in the denominator, this unfortunately we are stuck with, so we're going to have 1 squared, which is 1, and then we're going to have plus, and then this minus is going to get squared away, so what we're going to be left with is we're going to have r over L 2 pi quantity squared. Okay, so that's it right there. So that is the magnitude of it. So we've got r over L, we've got the 2 pi here. And oops, and also here we lost something here in the shuffle. All right, so I am glad we just caught that. We lost this f in the shuffle. So there's that f right there, and so this is r over L, and then we've got this f here down in the denominator. All right, and then we've got this f here down in the denominator, and then again we've got this f here, 2 pi f, and we can put the 2 pi f down there. Okay, so notice that the f is down here in the denominator. All right. Okay, so all right, so let's make sure here we've got this all right. So we divided this by 2 pi fl, 2 pi fl, and then down here we have r over L. And then we have our f, we've got our 2 pi, we've got our j, we moved our j up, we gave it a minus sign based on this identity right here. And then we've got r over L, we've got f down here, we've got 2 pi over here, down here, so we're all good. Okay, so now the question is, again, we want this term right here, to equal a1. And we want to equal a1 when we're trying to compute the cutoff frequency, because we want 1 over the square root of 2. So I want to make this equal to 1. So let's go ahead and let's do that math. And let's see what we get here. So we've got R over 2 pi FL. That's a nicer way to write that, right? And then we've got this quantity squared, right, equals 1. So why don't we take the square root of both sides and do that, all right? So then we have R over 2 pi FL equals 1. Okay, so why don't I invert both sides of the, there's two ratios, I'll just invert them, right? Is everyone okay with that? So that's a rule you can do, no problem. Equals 1, so I just inverted it. All right, and now I'm going to start moving things over. So I'm going to move this R, let's cross that out, and let's move it over there. There's R. All right, and then we've got our F here, and so I'm going to move the 2 pi and the L. I'm going to just move these over here on this other side. So I've got 2 pi and L, and then just cross those out. So then we're left with F equals R over L, 2 pi, and then that's it. So there again is our cutoff frequency. And you'll notice it's the exact same, F equals R over 2 pi L. And again, if we wanted this, so we can call this, F cutoff, or we can call it F, high pass, or F cutoff. And then we can also say omega cutoff, if we want, is just R over L, because that we lose that 2 pi because omega equals 2 pi F, right? So here it is in another form. So it's either this guy or it's this guy, and 2 pi L. All right, so that's it. So there is your high pass filter using an inductor and a resistor. Now, again, can you mix inductors and capacitors and resistors? Sure, you can do anything you want, and you just have to write these transfer functions and solve them out, compute their magnitude, and then if you want, you would compute their phase angle also, which we have not been doing. That's a little bit advanced. We don't really need it, but anyway, you could surely do that. And there's nothing wrong with doing that, and you can make filters that way as well. And then remember, when you want to mix these filters, I kind of mentioned this as an experiment, but let's say that we have one filter right here, all right, and we have another filter right here, okay, and so let's say that and so I'm going to show you kind of some ideas here. So the filter has 2 ports coming in, and the filter has 2 ports going out. All right, so the 2 ports in our case are ground and ground coming in and out. So this is ground and ground in both cases. All right. And then so inside of here we just have our filters, which could be an RL filter, it could be an RC filter, it could be low pass, could be high pass, doesn't really matter. Whatever it is, say that this is a low pass filter and say that this is another low pass filter, right? Then what would happen is these transfer functions, you would multiply them together. So you'd find the first transfer function, then you multiply it times the second transfer function. That would give you the resulting transfer function of the whole thing. So you can do it in blocks like that. And so you can do it with this kind of a block diagram, and this is called kind of a block flow architecture. You can do things like that because these they'll be multiplicative. So that's why if you take, say, an RC or an RL filter, and you want a steeper, remember we were talking about how steep the attenuation is. So say if you have a low pass filter, it's gonna look like that. What if we wanted it to look like, like this? We want it to be steeper. What we do is we add more of these filters and we put the filters in series, but then their action adds up multiplicatively. So you multiply them. So the typical fall off of a one reactive element filter, high pass or low pass, is minus 20 dB per decade of frequency. But if you put 2 of them together, now it's minus 40 dB and so on. All right, so you just add them together like that. But the problem is because they're lossy and so forth, and the signal starts getting distorted and other things start happening, and that's why this concept of active filters comes up. And we will probably talk a little bit about active filters in this course down the road, but that's getting a bit advanced, and we've got enough on our plate with what we've been learning in this aspect of the analog electronics. Okay, so what's the last thing that we want to do here is why don't we do a quick calculation again? All right, so what can I erase here? Let's go ahead. Why don't we erase this right here? I don't think we need this. Let's erase this, and we'll erase our little Bode plot. Okay. Okay, and so let's come up with a couple of values here. So let's say that R, let's get a better color, it's a little bit brighter. Let's say that R equals 1k ohm, and then let's say that L equals, let's see, I was looking and I think I have a 2.2 millihenry, so that's a big one, that's a big inductor. So if we have these two values, let's go ahead and let's plug it in and let's find the cutoff frequency for that for this high pass filter. So again, what does that mean? That means this. That means that this filter is going to look like this, right? And here is, let's use our white again. I've been kind of liking that. Here is a gain of 1.0, right? So this is gain up here on this axis, right? And then on this axis right here is frequency, all right? And so what we're interested in here is the 3 dB point, and that means when is this signal come down here? This is this cutoff. This is this F, high pass or F cutoff, which is this thing right here. That means when will this be 70% of its full signal? Because we're talking about high pass. We start off from DC and then we run up and then it starts passing it. And again, let's check, is this a high pass filter? So let's go ahead real briefly here and let's look at our magnitude calculation. So if we have our magnitude calculation here, all right, so let's take a look and let's see if this is a high pass filter. So as f approaches 0, right, as f approaches 0, this term approaches infinity. So as f gets smaller and smaller, anything over that small number starts getting very, very large. So the square root of that gets very, very large, and it all approaches infinity, and 1 over that approaches 0. So that's why at DC, we have 0 gain, all right? And again, if you want to be really accurate and robust about this, I'm kind of hand waving here with limits, but obviously if you know calculus, you could compute the limits of this and you could do this properly and prove this, but we can kind of say in general, as the denominator of this goes to 0, then this term here is going to go to infinity, the square root of that is going to go to infinity, 1 over infinity is going to approach 0 as that value approaches infinity. So anyway, at a DC of 0 hertz, we're going to have 0 gain. And then immediately, the second we have even a fraction of a hertz, it's going to start going towards 1, a gain of 1, unity gain. There's no amplification. Remember that. There's no amplification. There's just a lot of attenuation. So we're fully attenuated down here, and then here we're not so fully attenuated. And here at infinity, if we go out and f approaches infinity, then we are not attenuated, and the gain is 1. It's unity gain. But anyway, the f of c, the cutoff frequency is this. It's r over 2 pi l. And for these values right here, let's go ahead and compute that. Let's plug them into our calculator. It's the exact same cutoff as the low pass filter. All right, so what's our r? Our r is 1k divided by 2 pi l. And be careful when you do this with your calculator. So I'm going to do r divided by 2 pi l. I'm going to put parentheses. My calculator has parentheses, 2 pi l. So we'll do 2 times pi times our L, which is 2.2 millihenries, and parenthesize that, and then I'm done. And then I get 72.343 kilohertz, 72.343 kilohertz. All right, so let's go and let's put down our f of c equals 72.343 kilohertz. Okay, so 72.343. All right, so now let's go ahead and let's go to our program that we found online, and let me find that again here, and I'll drag it over to you. Okay, here we go. And I want you to read this RL Wikipedia page. I'll get to that in 1 second. Okay, so here we are here. We've got LR low pass, so let's go and find the high pass. Here we go. There's the high pass. Okay, so what was our R? It was 1,000 ohms. What was our L? It was 2.2 millihenries, 2.2 e to the minus 3. Okay, and let's do our calculate. All right, and it says the cutoff is 72.343, which is 72.343 kilohertz. And let's see what we had. 72.343 kilohertz. So everything is good. And let's go back to that. Let's look at the Bode plot of it. And there's the Bode plot right there. And so you can see it's rising up, and then there is that at that 72 kilohertz, which is roughly around here, is that 3 dB point, which is what we expect. Remember, it's high pass, so it starts off at 0 and then works its way up. This is interesting. So here's the phase, and so if you look here, when we're down here at DC, we've got this phase of like 90 degrees here, and then as we go towards infinity, then the phase goes towards 0. So that phase response is also important. And can be important when you're amplifying, many frequencies. Okay, all right. And then I said that I wanted you to look at this. So if you Wikipedia for RL circuit, this is a really good source here to again, it's very mathematical, and there's just no way to avoid this math, but I've been trying to keep it so that the math makes sense and doesn't get too complicated. But anyway, you could kind of scroll through this a little bit and kind of take a look at it. It's going to look very familiar. They're using what's called S-domain analysis, Laplace transforms. But anyway, kind of just scroll through it and just look at it and just read the text. That's what's important. Then it gets really nasty right here, and a little bit more than what we need to know about. But anyway, just read through that. That'll be helpful. All right. So I think that's it. Again, a short lecture because we're getting really good at this. And so now we are ready to go to the bench, and we're going to build both of these filters. We're going to build a low pass and a high pass just all in one shot. And with these inductors that we have, and I think we have a 330 microfarad, and we're going to use a 2.2 millihenry and a 1K resistor, and then we're going to sweep the frequencies across, and we're going to look at the response and make sure that it makes sense. All right, so that's what we're going to do next. So why don't you stop here, take a pause, take a break, and then meet me in the next lecture, and we'll get back to the bench and do some electronics. All right, bye. All right, welcome back. And in this lecture, we are going to build the low pass and high pass filter that we've been analyzing, the LR filter or RL filter. All right, so back here on the screen, we can see we've got our high pass filter here. So what we're going to do is we're just going to kind of erase a little bit here and kind of draw the two things that we're going to make. So I'm just going to erase some of this stuff here. All right. And let's erase all this. And then what we're going to do is we're going to draw the other filter, the low pass filter right under it. And then just so we have something that we know we're going to make. All right, so let's go ahead and let's draw the low pass filter. So this is the high pass filter. And you can remember it's just got the L here in the going down branch and the branch towards ground. All right, so now let's draw the low pass filter. All right, and the low pass filter looks like this. It's got a resistor to ground, and again, everything is always relative to ground. All right, and then here's our V in, and here's our V out, and we are interested at the voltage at that node, and we've got our L here, and we've got our R here. All right, so this is our low pass filter. So let's go ahead and we'll just put low pass. So we are going to build one of each of these. And then for the values that we picked, let's see if we still have that up here. Yeah, we do. So if we've got an R and an L of 1 kilohertz and 2.2 millihenries, the cutoff frequency was 72.343 kilohertz. So let's bring that down here. So R equals, so we'll say at R equals 1K ohm, comma, L equals 2.2 milli, not to be confused with micro, right? Millihenries. Millihenry. Then the cutoff frequency FC equals 72.343 kilohertz, right? 72.343 kilohertz. And why don't we, let's just erase a little bit of this here so this is not all over the place, ugly. Okay, all right. And now we're going to say we did the other one, and you may not remember the value, but we did, L was, I think we said 330 microhenries this time, and FC was, let's go ahead and let's just calculate it. All right, so let's use which one of our equations right here? So we can use this equation right here, FC equals R over 2 pi L, right? All right, so what's our L? 1K, and then we're going to divide that by 2 times pi times our L, which is going to be 330 microfarads, 330 microfarads. All right, and that is 482.287 kilohertz. So that is 482.287 kilohertz. All right, so that's it. So now what we're going to do is we are just going to go to the bench. We're going to build these two things, and we're going to confirm that they do what they say they're going to do. So, and again, that cutoff frequency will be for either the high pass or the low pass. So we can make one high pass and one low pass. So we'll figure it out at the bench. All right, so I'll meet you there. Let's go. We're on the bench here, and let's see what we have here. We've got our solderless circuit board, and then over here to the right, you've seen this before. This is an LC meter, so it measures inductors and it measures capacitors very accurately. And the reason I have that is to measure these inductors, even though the values are written on them. Let me show you on the zoom camera what they look like here. If you go on the zoom camera here, and let's get that to focus, if it'll cooperate with us. There we go. See that 331? So this means 330 microhenries is this inductor right here. And then the other inductor that we have is this guy, and there it is. So 222, this one means 2.2 millihenries or 2200 microhenries. So anyway, so those are our two values there. But what I like to do is I like to test them. So let's zoom in a little bit to this. And matter of fact, we'll kind of slide it over here so you can kind of see it. And there are, and we've done this before, I think, I'm sure we have. So there's these two probes here with very short probe leads, and we're just going to connect our device that we want to test. So here's the 330 microhenry. We just a sanity check, you know, just a sanity check. All right, so there's our 330. Let's get that on there. And these alligator clips are tight, so they're very hard actually to open up and squeeze. Okay, so there we are right there, and then we press test and we put it on the range. So in this case, this is 330. So we can, if we put it at 20, we'll put it at 2 millihenries. And there we go. So it should be, if we're in the millihenries range, it would be 330 0.330 millihenries or 330 microhenries, and it's showing up as 338, 339. So that's close enough. So this is a 330 millihenries or 330 microhenries or 0.33 millihenries. All right, let's get our other one. And this one is 2.2 millihenries. 2.2 millihenries. All right, so there it is there, and we're on the 2 millihenry scale. Now, if we do that, notice how it comes up and then it disappears. The reason why is because it went out of range, because this only goes to 2 millihenry, so we have to go to the 20 millihenry scale. Now we'll press test, and there it is, 2.25, right, and it should be 2.2. So that's correct. So good. So we know that these two values are what they should be, so we can put those aside, turn the power off, always turn the power off. One little tidbit, one little suggestion is your test equipment, your meters, your digital multimeters and whatnot, they have typically 9-volt batteries in them. I highly suggest that you use 9-volt lithium-ion primary cells, like the Energizer lithium-ion batteries. They'll last a lot longer, and because you tend to leave these things on a lot, so you don't want them dying. All right. So we have our solderless board, and we've got our components as usual. We've got some posts, we've got some resistors, capacitors. We won't be using any of those. We've got our two little inductors there, got some wires, and we're going to basically build the circuits that we just looked at inside of the lecture. So why don't we start off, and we're going to build, let's go ahead and build the high pass filter. So that's first got an R, and then it's got an L to ground. So it's got an R, and then it's got an L to ground, right? So let's go ahead and zoom in. Zoomy, zoomy. All right, there we go, zoomed in. Okay, so let's start off. And again, now because we're dealing with inductors, line length really matters here. So we got to be careful of that because the stray inductance of just these wires can make a difference at high frequencies. All right, so let's start off. And why don't we do the, since we're doing the high pass filter, let's do something kind of fun. Let's use the higher frequency cutoff that we did with the 330 microhenry and the 1K ohm, and that gave us 482 kilohertz. So that's going to be a high pass. So at 482 is where we're going to see it go to unity. And so this might be something that you might have in a very high frequency piece of equipment. So half a megahertz, that is a pretty high frequency in base radio electronics, so that's not bad. So we've got our wire here, and then we're going to put our 330 in here, and it takes up, so we put it in and we see that it takes up 3. So if we pull this out, we can see that it takes up, go look at it on side there, and what I'm just trying to show is it takes up 3 of those little holes, right? So we can kind of plan where the other wire goes, all right? So the other wire that we're going to take out of here is this one, and we're going to put it right here, right? And the next thing that we're going to do is we're going to have a resistor going to ground, and that's going to be our 1K resistor. So that's going to be brown, black, red. That's 1K ohm. Here it is in my hand, brown, black, red. And we could have just done the resistor straight to ground right from there, but I don't want the parts all on top of each other. So, all right, let's get our 330. Here it is here. All right, so there's our 330. Okay, so then our output is going to be at this node, our input is going to be at this node. So let's go ahead and let's get our little posts here so we can connect oscilloscopes and signal generators up. All right, we've got a few grounds already here from the last experiment. Okay, so let's take a look at that on side. So let's make sure everyone's on the same page here. So we're doing the, oh, I'm sorry, let's see, we were doing the high pass filter. We were doing the high pass filter. All right, well, you know what? Sorry, let's make this the low pass filter. All right, let's make this a low pass filter. So in the low pass filter, we've got the inductor here, and then we've got the resistor to ground. All right, so we're going to do the low pass filter. You can see this stuff is confusing where you put these things, and that's why I wrote it up there on the board. So as a matter of fact, let's go take a look again at the board here and make sure we know what we're talking about. Okay, so we're back here and take a look. And so we just built, we were saying we were going to do the high pass filter, but we actually did the low pass filter, and we put the 330 in there. So we put the 330 microhenry in there. So we're doing the low pass filter. So this thing is going to pass all the way up to about half a megahertz, 482. Then it's going to fall off, right? Then we'll go ahead and we'll do the high pass filter with the 72 kilohertz. So we're just, since we did this kind of backwards, we're going to flip around. All right, so we're doing the low pass filter. All right, let's go back to the bench. Okay, so we're back here on the bench doing the low pass filter. So we've got our inductor in that position. We've got our resistor to ground. So here is our VN and here is our V out. There's V in, V out. All right, so let's get our signal generator and let's make sure it's off. It is off. So I'm going to put the input there and I'm going to ground it. All right, then we're going to use channel 1 of the oscilloscope, and we are going to use that to look at what we're putting in here. What are we injecting into the circuit? And we're going to take that and we're going to put that to ground. All right, got our 1K resistor there. That's good. Always double checking as you're wiring things up. You know, think about it. What are you doing? Look at it. Double, triple, quadruple check. You're always going to make mistakes. I make constant mistakes doing this. All right, now let's put it on side. That looks good. All right, so now we've got a low pass filter that should pass until about 482 kilohertz, about half a megahertz, and then it should start falling off. So I'm going to go to my signal generator. I'm going to put it down to 1 kilohertz. All right, we're still at 2 volts peak to peak on the signal generator. Let's just take a quick look at that for those that might just be jumping onto this lecture. All right, so there's our signal generator, and you can see that we've got the 1 kilohertz signal, and then we've got 2 volts peak to peak. All right, and we're just going to take the output from channel 1 here, and then that's what we're pumping into everything. All right, so now let's go over to our oscilloscope. Okay, we've got our trusty oscilloscope here. All right, looks good. Okay, so we've got channel 1, and we're going to set these both at 500 millivolts per division. There's channel 1, the yellow channel, and here is channel 2, the blue channel. And we're just, all I try to do here is so we can see them both simultaneously, and then we kind of overlap them, right? And we're going to leave this measurement control up, and remember the blue is measuring the peak to peak of the blue, which is channel 2, which is the output, and then the yellow peak to peak is measuring channel 1, which is the input. Okay, so we have everything. We've got our circuit. We're good to go. We're only going to put 2 volts peak to peak, and the reason why we're doing that is we like the 1 volt in peak in one direction, the negative in the other direction, and it's very easy to multiply numbers times 1. All right, so here we go. I'm going to turn it on. Okay, and remember this is a low pass filter, so what we're expecting is to be able to, it's going to totally pass the signal, and it is. You can see that the input and output are equal, at least they look like they're equal. So let's go ahead and let's overlap them. All right, we're going to overlap them here and put them right on top of each other. So I'm just aligning channel 1 and channel 2, which is always a little bit of a challenge. I'm sure there's a button on this oscilloscope that does this. All right, so they're perfectly aligned. So the blue is the output. So as we modify the frequency here, which you can see up here, so we're at 1 kilohertz, as we go towards 482 kilohertz, we're going to start to see attenuation because it's going to stop passing the signal. All right, so that is what we are looking for. All right, so here we go. All right, so I'm at 1 kilohertz, 2 kilohertz, 3, 4, 5, 6, 7, 8, 9, 10. All right, now what I'm going to do is I'm going to change the scale so I'm going by 10 kilohertz at a time. Notice there's no attenuation, at least appreciable attenuation. Take a moment to look at these values. So we still got our peak to peak of 2, got our peak to peak of 2 on both channels, which is what we expect. All right, keep your eye on the frequency. 20 kilohertz, here we go. 20, 30, 40, 50, 60, 70, 80, 90, 100 kilohertz. All right, and you can see we are still almost at full unity gain, but if you take a close look, let's kind of change the sweep frequency here. We're definitely attenuating a little bit. You can see the blue channel is a little bit less. You can read it's a little bit less. It's about 40 millivolts less, but you're starting to see that phase shift there. See that phase angle starting to happen? We're at 100 kilohertz right now, 100 kilohertz. All right, so we're a fourth of a way to our cutoff. All right, so now I'm going to go by hundreds of kilohertz. So here's 200 kilohertz. 300 kilohertz. Here comes 400 kilohertz. Now 400 kilohertz, you can see that we're getting pretty close. And remember, when that peak to peak hits 1.44, that means that we're at 1 over the square root of 2, or we're at the minus 3 dB, or the actual cutoff frequency, which we're estimating is, should be mathematically, based on the components, should be at, what is it, 482.287 kilohertz. Of course, the components aren't that accurate, so it's not going to be that accurate. All right, so there's 400. Now what I'm going to do is I'm going to go by tens. So there's 410, 420, 430, 440, 450, 460, 470. There's 480, and pretty close. There's 482. And this signal generator is very, very accurate. So it's at 482, and we're going to put it dead on 287. So we're going to do 2, just for kicks, 87. Let me get it to 482, 240, 250, 260, 270, and 287. Alrighty. So that's cool. So 482.287 kilohertz on the dot. And you can see that the frequency counter here in the oscilloscope is not as accurate, obviously, as the signal generator, because this is averaging and doing the computation. All right. But take a look here. We're we're still not at the 3 dB point. We're at 1.64. So the 3 dB looks like it's a little bit further than this, and that's just because we've got our plus and minus 5 or 10% on our actual values of our inductor and our resistor. All right, so let's go ahead and we'll go to the ones place here. So 42, 43, 44, 46, 47, 490 kilohertz. All right, keep it coming. 495, 500, 512, 520, 540. There we go. 550, 570, 580, and 590. Keep going, maybe 560 kilohertz, 590, 600 kilohertz. So the 3 dB that we calculated was 482, and then we see here as we do it, it's a little bit higher if we want that exact value. So anyway, so that's that. Now let's go up by hundreds of kilohertz again. All right, so there's 8, there's megahertz and some change, and you can see we're losing the signal. And I'm going up here 1.8 megahertz, 2 megahertz, and at 2 megahertz this is gone. So you can see we're getting almost nothing out. The blue line, we're getting nothing out, so that's nice. All right, and that's it. So that works. So there's a high frequency, low pass filter that filters. Starts kicking in, roughly around 42. Mathematically, these components are obviously a little bit different, and this is why stray inductance is very important, because you got to be very careful. If we were to actually take these lines and make them a little bit shorter on the solderless breadboard, we'd actually adjust this slightly. You would see a bit of a difference. It might be at only thousands and thousands of hertz or tens of thousands of hertz. We change the frequency response, but it actually would. All right. Okay, so that's that one. So now let's flip this around. So we are going to replace the inductor with the resistor with the inductor, and we're going to flip the inductor out for the larger inductor, and then that should switch our cutoff frequency to, what was it, 72 kilohertz and some change. So first let's turn off the signal generator. So that's off. All right, so we're going to pull that out. We're going to put the resistor right where the inductor was. Now the problem is it's going to be a little bit hard to get the inductor, and we got to make sure we put the correct one here. Here's the 2.2 millihenry inductor. So what I am going to do now is, I don't want to tear up too many things. All right, so we know that it takes three little slots. So what I'm going to do is I'm going to put this here like this. Then I'm going to get a little ground wire, because we got to get this inductor to ground. All right. Okay. So what I'm going to do is I'm going to put this and move this around here. Okay. So that looks good. Okay. And sometimes these wires are so hard to manipulate with your bare fingers. What I'll do sometimes is get a pair of pliers and push them in real nice, because sometimes they're just hard to get in. All right, there. Okay, so there's our 2.2. We got our 1K. We're taking our output here just like last time. Let's look at it on side, make sure we agree with everything. I'll just pop this out. So all I'm doing is going from here through the inductor to ground. And then we want to make a good connection. These leads are not very long, and let me show you that on the zoomed camera. So they're not that long, so they're having a hard time sticking in the solderless breadboard, but we'll deal with it. All right, so going back here to the breadboard. Okay, so we've got everything the exact same as the previous one. All right, and now, so what are we building here? So now we're building the high pass filter. So it's going to start passing at the cutoff frequency of about 72 kilohertz. All right, and then go from there. So it's going to start passing at about 72 kilohertz. All right, so let's take our frequency generator, and I'm going to just put 100 hertz in it and start it off there. Let's take our sweep and let's put our sweep back down here, and I'm going to put our 2 channels on the oscilloscope. So take a look at our 2 channels and spread those out. All right, so now we've got 100 hertz on the signal generator. We've got 2 volts peak to peak, and let's turn it on. Okay, And let's sweep this out so we can see our input signal, get it down slow enough of a sweep rate so we can see it. We've got nothing on the output channel, the blue channel, so you can see this is a high pass filter now, high pass filter we're doing, right? We've got the inductor going to the ground leg, right? The inductor going to the ground leg, and that makes a high pass filter. Now, let's just, why is this a high pass filter intuitively? This is why. The inductor's resistance goes up. What's the inductive reactance? X sub L equals 2 pi FL. So its reactance goes up proportional to the frequency. So the higher the frequency, the bigger this resistor is. So this is a high pass circuit. Why? Because as we increase the frequency, this impedance goes up. Well, as this impedance goes up, the ratio of this impedance to this resistor right here, the voltage keeps getting higher and higher, dropping over this leg of the voltage divider. So it ends up being a high pass. So the interesting thing is, because we're taking the voltage over this node, we're really taking the voltage drop, which is increasing because the impedance is getting higher. So it's not that it's passing the higher frequency. In fact, it's becoming higher impedance to the higher frequency, but because we're looking at the voltage signal gets larger as the impedance gets larger, thus it's a high pass filter, okay? So you can always kind of work these things out intuitively if you like. All right, so where are we? We're at 100 hertz. Start increasing the frequency. 72 kilohertz we know is the cutoff or cut in, and we should start to see something. We're not seeing anything here. We're at 1 kilohertz. I'm going to open this up a little bit, and you'll see me using these terms like I'm going to open this up a little bit on the oscilloscope. It's just EE speak. Open it up, meaning change the frequency, go to a faster sweep rate, that kind of thing, and you'll just start to hear these words and kind of pick up the lingo over the years. Okay, so we've got 1 kilohertz here, and I'm going to go to the 1 kilohertz modifier on the signal generator and keep going there. So now we're at 3, we're at 4. You can start to see we're starting to get some signal through this thing. So this high pass function is starting to happen. So again, let's change the sweep rate. All right, we got a little bit. So we got 300 millivolts coming out of our 200 of our 2 volts. So we got 300 millivolts, not bad. We're at 8 kilohertz, 9. We're at 10 kilohertz. Now I'm going to go by 10 kilohertz each time. So there's 10, 20, 30, 40. We're at 40 kilohertz. We're about halfway there, a little over halfway there. And a little over halfway there, you can see that now we've got about half that signal. We have a 2 volt peak to peak that we're putting in, and now we're getting a 1 volt peak to peak, right? So we got half of our signal out, and we're more than halfway to our cutoff frequency. So there's 40, 50, 60. There's 70. All right, 70 kilohertz, and our cutoff is, where's our cutoff? It's 72 and some change, so there's 1, 72, and we might as well put exactly 343. So there's 3 and 4, and again, this is not going to be accurate. So there's 72.343 kilohertz, and we take a look at these 2 signals. We're getting a peak-to-peak of 1.5, so that's really nice. So we got 1.5 there. It's almost exactly what we expect of 1.44. And then we can go and overlap these if you want. You can kind of see them. There they are. All right, you can see the phase shift there, right? Let's see what else is interesting here. Okay, so let's continue to sweep the frequency. So there's 72 kilohertz, and there's 73, there's 74, 75, and we keep going. All right, and now at 80, we're at 1.6. So see this cutoff, it's a little bit less in this case. Let's go to about 71. And 71 kilohertz, 69 kilohertz. Yeah, about 69 and some change, maybe 68. Give it a second to adjust. So 67, 66, 65, there we go, about 65. So the calculation of the ideal parts set it at 72, and it's about at 65 with these actual parts, all right, which is within the tolerance of 5–10% error on the inductor and the resistor, and then the stray inductance here and so forth. So that's it. So there's a high pass and a low pass filter. A lot of fun building these and doing this. And like I said, that's all you need. Just keep it clean. Keep these leads short. Keep them flat. The flatter, the shorter, then everything's going to be more accurate. And then again, depending on what the tolerance of these components are, these are in a little box. I got these out of a box. I've had them for years. I can't remember the exact part number. All we have is a value, on the part. all we have is a value on the part, right? So I don't know what the manufacturer is and what its tolerance is and all that. So that's why we bust out the LC meter and measure stuff, right? And just for a sanity check. Okay. So all right, let's go back over to the blackboard and finish up. Okay, so we're back here at the blackboard, and we did our low pass filter, we did our high pass filter after a moment of confusion where we built something and we thought it was the high pass and it was low pass, it was a high pass, but we fixed it up and we did that. So that, that's why you got to just keep checking things and make sure things are correct. And then, like I said, you can go through and then do those sanity checks with intuition and make sure the circuit works, which what we did was, we said, if we have this circuit configuration right here, right, if we've got that circuit configuration right there, we've got the inductor right here. Well, we know the inductor, what's its reactance? It's X sub L equals 2 pi FL. So as the frequency goes up, this impedance is going to go up, this reactance is going to go up. Therefore, this voltage drop here is going to get higher and higher. Well, if that voltage drop gets higher and higher, as a ratio of this voltage drop compared to that voltage drop in a voltage divider action, this should be a high pass filter, and it is. Same thing here, low pass filter. As the frequency goes up, so as the frequency goes up, this impedance goes up, so then the voltage drop over this device becomes much larger than it is over this device, the R. So we get a smaller voltage out here. So as the frequency keeps increasing, then we keep getting a lower voltage. So this is a low pass filter. So again, you can use intuition to figure these things out. So that's about it. We've got the transfer function, remember that again, and then we've got the magnitude of the transfer function, and then we've got our corner frequency, which is the same for both the low pass and the high pass, and in both configurations of the L and the R. And that is about it, I think. All right. So that is going to wrap it up for RC and RL, LR filters, low pass, high pass. We talked about how to add them together and make band pass if we want, or multiply them to add more poles. You just take these filters and you put them in series, input to output, and then the transfer functions will multiply. All right, so that is all we're going to talk about right now of this, and now we're going to use this stuff as we need to down the line as we build other things. So now we're going to switch gears back again, and I believe where we left off, let's take a look here, it's been a while. Let's go back to our document. Okay, yeah, so we were talking about RLC and all that, and we kind of skipped through that, and now we are back on diodes again. So we're going to talk about diodes in the next lecture, and we've already spoke about semiconductor devices, diodes, transistors, and FETs, but now instead of at a semiconductor level, we're going to talk about them more at a practical level and just kind of use them and build circuits with them. Since now we know the fundamentals, and this is where it's, again, this is a lot of fun because we know the fundamentals of it. We don't need to talk about all the physics anymore and holes and charge moving electrons and holes. We don't need to talk about all that. We know how that works. So now we're just going to cover what the kind of primary different kinds of diodes are. We're going to make some circuits and actually see them in action again a lot more than we did last time, and then we're going to build some other cool circuits out of them, power supplies and things like that as we move forward. All right, so I will see you in the next lecture, so take a break, and you got through probably the hardest part of the whole course. I think we're done with. The rest of it is all downhill, and then once we get to digital, super easy. Digital is super easy. So this is the hard stuff. So if you got through it, you know a lot, and frankly, if you can do those calculations that we just did with the filters and compute the transfer function and the transient response of the RC and RL circuits, charging and discharging, that's more than most graduates in electrical engineering can do. That, honestly, they can't do it. So unless they studied, right? So you're on top of stuff, right? So I'll see you in the next lecture. Bye. Okay, welcome back, and we are doing the next lecture, and we are finally out of the weeds and the the bog and the hard stuff. We've done a lot of analog electronics. We've learned about filters and frequency analysis and low pass and high pass, and we know how to use Ohm's law, and we know about Kirchhoff's laws, we know about inductors and capacitors. We've talked about semiconductor theory with diodes and transistors and FETs. All right, so at this point, I'm going to I'm going to release my foot a little bit off of the mathematics pedal here and ease back, and we're going to start going up a little bit higher level. And this is where things are going to start getting fun, because now we know enough so that we can honestly build things and kind of know what we're building. What you don't want to do with electronics is build things and not know about the fundamentals of the components that you're putting together piece by piece, because then you just really don't understand. And you know, internet is replete with examples of designs that are really, really bad for all kinds of things. And then people copy them, and they don't know exactly what's wrong with them design-wise. They sort of work, and then they copy and copy and copy, and that's really, really bad. So it's important that we learned all these fundamentals. And now, when we're looking at a circuit, we can say, you know, what about this? What about the frequency response to that? What about the current? What about the heat? We know about these things now. So this is really good. Okay, so let's get right into it. And what are we going to do? So we are now, we're going to get back to my book here. And let's see, we kind of left off on this diode section here, and we're just loosely following the book, just loosely. It's a study guide for you. You get it free with a course, so just I want you to read the whole thing. But right now we're in chapter 3 roughly, and we're going to talk again about diodes, but we're going to talk about diodes and actually apply them and use them. All right, and now one other thing that I'm trying to do here is I am trying to use this little cursor thing, so it kind of highlights things so you can kind of see me moving around here. It seems to keep turning off, so bear with it, but it shows the clicks here and what the keyboard commands are, which is kind of nice when we get into using the tools. Okay, so what I'd like you to do is I'd like you to read this material yourself very carefully. We're going to kind of skim through it, and then we're going to build some of these experiments and try some other things as well. All right, so let's just dig right in here. All right, so diodes, we've already talked about them. What's a diode? A diode is a device that allows current to flow in one direction. All right, and how that works is there's a p-type material and an n-type material. Usually this creates a semiconductor junction, a depletion zone, and remember, charges accumulate on one side, charges accumulate on the other side. There's a voltage differential, and then we overcome that voltage differential, and then we can push charge through it, and we get current flow. All right, so that was kind of the basis of diodes, if we remember. Looking at this little figure right here, we've got the anode, we've got the cathode, and we apply what's called the bias, positive and negative, when we push current through here. There's all kinds of diodes. Some diodes have PN junctions, some just have one semiconductor junction and a metal, all right? There's all kinds of variations of these. And so we're going to be looking at standard silicon diodes, PN diodes. We're going to be looking at Zener diodes, and these are typically used as voltage regulators. And we're going to be looking at Schottky diodes after William Schottky, and those have very low forward voltages, and because they're only one semiconductor junction, one semiconductor P or N, and a metal. All right, and we've talked about all this before, so this should all sound like review. But now we're going to actually use them to build stuff. Okay, so diodes, again, I want you to just read through this. A standard silicon diode, like a PN diode, one of the more common ones is a 1N4001. All right, and I think I have, yeah. Okay, so here is a 1N4001. Let's see if we can get it so you can see it better. There we go. Get it to zoom in. There we go. All right, 1N4001. Now this is what's called glass passivated, and the passivation, the glass around it, is just to protect the semiconductor junction. But also the glass is more resilient, and it can stand up to higher temperatures than plastic. So let's see if we've got a plastic version here. And let me see what this one is. This one is a 1N4006.
So this is very similar to the 4001, except this can handle, I believe, 800 volts of reverse voltage, where the 4001 is only 50 volts of reverse voltage. And of course, this one's in plastic. All right. And then just as some other examples, just to show you that the diodes look alike. This here is this is a Zener diode. This is an NT5116A. I believe this is a 5.1 volt Zener. And then here is, this is an ST part, and this is a Schottky diode. Try and get the light. So this is an STPS 2L60. So that's what that is, and this is a Schottky. So they all look alike, and that's the point there. So anyway, all right, so let's get back.
Okay, so let's take a look here. And we have this graph here, which is important. And the graph, again, shows you the diode current versus voltage. And that's the kind of whole idea here of a diode. So paying attention what's going on here, over here on the x-axis to the right, this is as we forward bias this diode. So as we forward bias it and put plus to minus in this direction, the diode starts to conduct. It starts to conduct, and then we start getting exponentially more current here until we get to this point right here, which is the forward voltage, this 0.7 roughly for a silicon diode. Then what this means here is that no matter what the current is, so the current can be anything now, right? The voltage will stay the same roughly at 0.7 volts. There's a forward dynamic resistance, so this voltage will slightly change up and down as this current changes, but ideally, once it hits 0.7 and it conducts and the diode turns on, then the beauty of it is it sits at 0.7 volts, and then we can modify, we can change this current and draw more or less current, and we have this fixed voltage. So not only is it a device that steers current in one direction and only flows in one direction, but it's like a current source. It's got a fixed voltage, and we can just take as much current as we want out of here, right? So these diodes can be used for steering, rectification, and they can be used also for regulation, voltage regulation. All right, now, if we go in the opposite direction, now look what happens here. So we apply a voltage in the opposite direction, looking back up top. That would mean we try to put a plus on the right and a minus to the left here. When we go and try and reverse bias the diode, if you recall, we get no current, no current, no current, no current, no current. Then all of a sudden we get to a point called the breakdown, and that just means the electric field is so strong, no matter what, we start pushing charges through the semiconductor junction in the opposite direction. It breaks down very quickly, and then it starts conducting current in the opposite direction. And this typically will damage the diode, right? So we don't want to do that normally. Now, some diodes actually operate in the breakdown region. Zener diodes, for example, they're designed to operate in the opposite direction, and we'll get to that in a second. So anyway, just a little review here of what's going on with the diode and the current and the voltage. All right, so we forward bias the diode, current will flow only in that one direction. The forward voltage drop will hang around 0.7 volts for a silicon diode. For a Schottky diode, which I'll talk about in just a little bit, but we've talked about it before, the Schottky diode is a metal and semiconductor junction, so it's got a much lower forward voltage, about 0.2 or 0.3 volts instead of 0.6 or 0.7 volts as a silicon diode, and it'll start conducting as well. And it basically has some of the same properties. It's got a much smaller reverse breakdown voltage though. All right. Okay, so again, I want you to read through this stuff here. Now, so let's talk about an application of diodes. So let's just for now talk about, say we've got a silicon diode, a 1N4001 to 4006. All right, so again, let's go here. This is a DigiKey, and we'll just type in 1N4001 into DigiKey, and we'll go here and take a look. There's all these different vendors, but we'll just grab one of these devices. And this one, you know what? Micro commercial, not a big fan. Let's look at Fairchild. I like Fairchild parts. Okay, here we go. Fairchild parts. Oh, those are discontinued, so that wasn't too good. How about Vishay? All right, let's see. Vishay, what do we got here? Okay, All right, so if we look at the Vishay part, we see that it's got a reverse voltage of 50 volts. It can flow 1 amp without damaging, and it's got a forward voltage of 1.1 volt at 1 amp. Now, what does that mean? Didn't we say that it's 0.6 or 0.7 volts? Yes, it's 0.6 or 0.7 to turn the diode on, but then as you put more and more current, the diode actually has some small resistance, all right? So as we push current through it, it actually drops more and more voltage. So as that current goes way high, in this case 1 amp, then we drop another, few hundred millivolts and we end up with 1.1 volt. All right, so that's why there are other diodes if you want to have very small forward voltage drops. Anyway, let's click on this. All right, and again, get real comfortable going through data sheets and all that. So I want to look at this data sheet here, and we've done this before, but I want to show it to you again. And so the whole series of 1N4001 to 4007, if you look at them here in the data sheet, we've got all these nice values here. And the big difference between all these, if you look, is here's the reverse voltage, right? And the 4001 can handle 50 volts, then the O2 is 100, the O3 is 200, 400, 600, 800, 1,000 volts. But all of them can only kind of handle an amp in the forward direction, all right? So anyway, if we want a diode that can handle a higher current, 2 amps, 4 amps, 10 amps, 20 amps, we've got to look for a different diode. But the 1 amp is fine in our case, and typically this the 4001 is okay, unless you wanted to rectify something that, say, AC. You wanted to rectify AC, and that AC signal is 110 RMS, or it's 170 volts peak, or 340 peak to peak in the United States. So we would have to go up to, like, if we wanted to be real comfortable with this, a 4003 or a 4004 if we wanted to use that in a pure AC rectifier. Okay, so let's go back and let's talk about what we mean by a rectifier. Okay, all right. So take a look at this circuit right here. And so what we have here, and again, we've lost our little halo. I'm not sure if I'm going to keep messing with this. This is more annoying than anything. I've looked at a lot of these little screen trackers and button indicators, and none of them work right. They're all buggy. All right, so we've got a diode here, and then we've got a load here. And then we're showing an AC signal, not necessarily AC coming from the wall, but just it's an AC signal going positive and negative about ground. Now, here's the interesting thing. So here's what the signal looks like, and we've seen these signals many times, just a sine wave. However, during the, if we have this circuit right here and we want to measure this voltage V, and we want to call this V out, right? So there would be V in, this here, and here would be V out. If we measure that with this actual circuit, we are not going to get the negative half cycles. And the reason why is, so when the voltage starts going positive, the diode starts conducting, and we're going to get a voltage over this resistor, over this load, right? So that the output is going to track the input, like this. However, when we get to the negative half cycle, we're going to reverse bias this diode. This diode is going to be off. Since the diode's off, there's going to be no voltage over this resistor, so we're going to get no voltage, no voltage, no voltage. And then again, once we get to the next positive cycle, again, we're going to get the signal. So this is called half wave rectification, because only half of the wave comes out, right? Now, detail, very, very important detail. This diode will not conduct until about 0.6 or 0.7 volts. So this waveform is not going to exactly look like this waveform. It actually won't turn on until this waveform hits 0.6 or 0.7 volts. Then it'll snap on. So there's a little bit of distortion. All right, let's take a look at that. Let's go to our drawing program, and let's actually take a quick look at that, because that's worth detailing. All right, let's get back to our drawing program here. Okay, so what do we got? Let's just kind of mimic what we had here. So we've got a diode, and we're just talking about a silicon diode here. All right, we've got a load. All right, and then we're going to call this V in, and then we're going to call this point here. Just put it right here. We're going to call this V out. And remember, we're always taking everything relative to ground unless otherwise noted, all right? So here's our R, here's our D, all right? So the input is here, and the output is there. Okay, so let's draw a little waveform here, just like we had. So we'll draw 2. All right, so let's say, and what's this? Let's leave our axes here. All right, so this is time. Time is going this way in both cases, and then up here, this is a voltage. All right, in both cases, it's this voltage. We're just drawing these on top of each other. All right. All right, so now let's say that our input looks like something like this. All right, and let's use nice orange here. All right, so orange, okay, and then let's say that this peak value here and this peak value here, let's say that this is plus 5 volts, and down here we'll say this is minus 5 volts, right? So it's a symmetrical sine wave, plus or minus 5 volts. The frequency doesn't matter. Frequency doesn't matter in this case for this analysis, but just for kicks, let's say that f equals 1 kilohertz. Okay, frequency equals 1 kilohertz of the sine wave. Doesn't really matter though. Okay, so now let's draw what the input looks like. So here's the input on this graph right here. So this one's going to be V in right there. That one will be V in, and we'll make this this red one. We'll call this V out. All right. So here's V in, and it looks like that, right? So we just got a standard sine wave. Okay, close enough. All right, so now let's see what happens here. So now on the positive first cycle, so let's go ahead and let's draw some let's kind of draw some little tick marks here. Let me try to keep straight lines, so we can kind of track each one of these cycles. Now remember, these are should be perfectly symmetrical and all that, aside from my chicken scratch drawing. Okay. All right, so we've got that right there. Now, and remember, what is this? What are these peaks? These peaks are at 5 volts, right? So this right here is plus 5 volts, and of course this right here is minus 5 volts, right? So that's our transitioning. So that's how far we're going up and down each time, is plus to minus 5 volts. All right, now here's where the fun part comes. So we got this diode. So now let's talk about this first positive half cycle. There's our first positive half cycle, okay? So when that's happening, we're going to get a positive voltage here, all right? And then, so there's a negative here, all right, ground, because here's ground here. So we're going to start turning on this diode, right? We're going to start turning on the diode. As we turn on the diode, then what's going to happen is, now remember, here's time. So we're going to turn on the diode, turn on the diode, turn on the diode, all right? And then at some point, the diode is going to turn on, and now we're going to kind of jump up, and we're going to start tracking this signal, all right? So we're going to start tracking this signal, and then it's going to turn off again. So the point is this little region down here, instead of tracking this, it's not going to track it because the output here, there's no current because we haven't turned on this diode. So what happens is this output signal here is always going to be a little bit smaller. So if we go and we look at what this peak is here, right? So if we drop 0.7 volts over this junction, then the highest that the voltage on this output is going to be 5 minus 0.7, or 4.3. See, so this is going to be 4.3 volts. All right. Now, moving on, once we come down here, and again, we're going to stop conducting at some point, even down in this range, and this is going to flatten out real quick. Now what's going to happen is this thing is going to start being reverse biased. Now we're in this half cycle, this negative half cycle. So now we're getting a negative voltage going towards minus 5 volts. So now what's going to happen? Well, nothing's going to happen. The diode is now not forward biased. All right. So now we're just going to get nothing there. So we're going to get nothing out of there. All right. So there's no current. So there's no voltage drop over here. So we're just going to get ground. We're just going to get ground. All right. So that's that. And again, now the next positive half cycle, we're going to get that again. Oops. Draw that semi-sinusoidal. And then again, we're going to have that negative, which is just going to be flat. All right. And then again, it would continue on. All right, so as you can see, we're only getting half of those waves out, right? So what we would like to do is there a way that we could get these negative half cycles? We'd like to get those and turn those up and reflect those up, all right? So this whole thing here, this is called half wave rectification. Rectification. All right, half wave rectification. So with just one diode, you turn an AC signal into this DC, well not DC, but into this varying DC, because it's not going in the negative direction. It's always positive at least, but it's going up and down, up and down, up and down, up and down. All right, so that's half wave rectification. We're going to talk about full wave in just a moment. All right, so let's go back to the document. Okay, so that's what we did there. So that's half wave rectification. Now, the next step would be we want to do full wave rectification. So now what we want to do is we want to take our signal in, all right, and then these are applications of diodes for, say, power supplies and other things. We want to turn AC to DC. So now what we can do is we can use 4 diodes, and we can steer the signal around so that when it's positive, it always comes out this pin right here. When it's negative, it always comes out this pin. So now what we end up with is this. We end up with this, all right? So we're going to actually draw this and work through it. Now, there's one other thing you see here is this filter cap, all right? So now we get this lobing DC coming out of here, right? So, and then typically right here at this plus to minus, this is where we would put a load, a resistor, device, whatever. Well, this is not going to work for DC. This is hardly, steady DC. This is lobing DC. This is not very good. So what we do is we put a really big filter cap there, all right? And if you read through this material right here, all right, right after this figure, I want you to read through this material right here. It talks about the calculation of this filter cap so that we would get stable, not perfectly DC, but semi-stable DC. So this goes through the math and explains it. The bottom line is that if we're talking about a 60 hertz AC line in the United States, that means 120 hertz. So if the full sine wave is 60 hertz, that means when you flip the negative half going sign, these are happening at 120 hertz. All right, so that's the frequency. So that's the ripple frequency. And then you can use this math that I show you, and then you can compute, given a load, how much capacitance you would need to make that stable to keep the ripple within some small amount. So this is why we need what's called voltage regulation, and we're going to get to that, and that's what diodes are useful for and voltage regulators are useful for. But you can do this calculation, you come up with a really big number here. It says 8,333 microfarads. So that's pretty big, and let's see here. I think, what's this one? Now this is a small capacitor, so this capacitor right here, this is a 330, but this is a very high voltage capacitor. But let me see if I have a big 2200 someplace. Yeah, hold on. Okay, so here is a 4700 microfarad. Maybe hopefully you can see that. If not, it's 4700. You can see it's pretty big in my hand. So we could use 2 of these if we wanted to get our 8300 roughly. All right. So anyway, that's one use of a full wave rectifier, and then we have to put this ripple capacitor on. All right. So what I'd like to do now is let's draw this and kind of run through it a little bit. All right. So I'm going to move that over here so I can see this circuit and draw it in the same way. Okay. All right. So let's go ahead and so that's half wave rectification up here. All right, so now we're going to do full wave rectification. So let's just draw it in the same space here so we have both circuits up here. Okay. All right, so I want to try and draw this as it is here. And so the trick is to draw these things. These are not the easiest things to do. You kind of draw them like this. Trick is you draw kind of a diamond, and then you put the diodes in here, and then you got to be careful you put them all in the right directions. So just put these diodes in here, and then these two go this way. All right, fill that in. Okay, and then this one, yep, should go up like this. Okay, all right. And then, if I recall, this is going to be where we're going to put our input. Yep, yep, yep. This will be our input here, like this. And so these four diodes would just be on your circuit board, obviously. And then this jumps over this, right? So that's how I'll show that. So that's connected there. And then this is connected here. And then this comes out here. All right, and let's do the same labels here. So we'll call this node 1, all right, and we're going to call this node 2, and why don't I call this, we'll call this node 3, we'll call this node 4. Let me make those a different color. How about we'll make them blue. See those a little bit there, so make those blue. All right, now the outputs here are always going to be positive and negative. So this is the plus output. So we're going to get plus here always. And this is the minus output. So we're going to get minus out here always. All right, so this is where we're going to put V in. And this is where we're going to put our AC signal in. So this is AC. This is going from plus to minus AC. We've got our diodes right here. Now let's actually label these also the same way that it's labeled inside of the book, just for kicks. So this one is D1, this one is D2, this one is D3, and this one is D4. Okay, so that's how I did everything. All right, now let's put our other component in here. So we've got this ripple capacitor, we're calling it, okay, C, and I'll call this CR for ripple. All right, and then we've got our output right here, and then typically this is where we would connect our load, right? So we would come here, and this would be our load, whatever our load might be, right? And we'll just model it as a resistor, our load, okay? But this could be anything. This is just a black box, right? This is a black box. Okay, so now the question is how does this work? All right, so let's go ahead and let's draw a similar kind of graph. As a matter of fact, we don't have too much room over here, so let's. I'm going to erase this graph up here. So let's just erase this one, and then we're going to redraw for the full wave rectification up here. Okay. All right. So here we go. So we got our two inputs here, and I'm going to put that one there and put this one here. All right, so what is this? This is time going in this direction, time going in this direction. This is voltage going in this direction. This is V, okay? And then in both cases, so what I'm going to do is I'm going to call this 0 volts here. I'm going to call this 0 volts here, all right? So now let's draw our V in, all right? So this is a positive and negative going waveform like this. All right, and again, we can say anything we want, but since the example in the book uses this as 60 hertz, we'll just call it 60 hertz, but we're just going to call this plus and minus 5 volts. All right, we're going to call it plus and minus 5 volts. So there's plus 5 volts, and then here's minus 5 volts here. Okay, so that's what our waveform looks like. All right, now the question is, what is our output? What does this look like? Okay, all right, so let's go grab another bright color, okay. All right, so now let's go through this step by step, and let's not worry about the capacitor, the load right now. Let's just talk about these diodes and what's going on, all right? So bear with me, and this is you know, if you're a computer programmer and there was some point in your life that you learned about recursion, and recursion is one of those things that's very difficult for people to pick up the first time, and you have to run through examples. You have to run through the stack step by step until you just completely understand it. And rectifiers are the same way. You just got to step through this step by step until you understand it, and then later you can just kind of draw these things and connect them and use them. But I want to make sure we get this. All right. So what are we doing here? What are we doing? We are going to run this waveform through here, and we're going to see what turns on and what turns off. Okay. So here we go. So as we have this AC waveform come into this V in right here, the first half cycle, so here we go. So this is this first cycle right here. So let's talk about this one. So this is positive, all right? All right, so this is positive going. All right, so here comes the positive going cycle right here. And we apply positive here, so therefore this is negative here. So 1 is positive and 2 is negative. So this is positive. So the question is, which diode do we potentially turn on? All right, so we've got a positive here. So there's a positive there. All right, so and then we've got a negative here. All right, so we've got positive here, we've got negative here. So here's positive, here's negative. All right, so D1 is going to potentially get turned on because we've got a positive here. All right, D3 is going to get turned off because we're putting something positive here, and that's in the reverse bias direction. So we're going to turn D1 on. So D1 is going to get turned on. All right, now, so there's D1 getting turned on. Okay, now let's talk about what's happening at this other node right here. So now what's happening is we've got a negative here. All right, so we've got a negative here, and so that means that, so we've got to have a place, a direction for current to flow. So here comes current through D1, all right, and now we're going to have to use a different color here. So here comes current. So current's going to flow through D1, all right, and forget about the capacitor for now, right? So something's going to happen there, but current is going to flow through this load, all right, and it's going to keep flowing through here. All right, and again, something's going to happen to this capacitor. We know that. All right, and then current's got to come back this direction. All right, and now the question is, which way is this current going to flow? So now we've got this current flowing this way. Now, is the current going to flow up through D3? No, it is not. The reason why is because this is very positive here. So this is very positive. And now this current, right, the voltage here is very, very negative. The voltage dropped over this load. So this is a very negative voltage here. So since this is a very negative voltage here, all right, relatively speaking, and now what is this? This is completely at ground here on D2. So what's going to happen is this current is not going to want to go up D3. It's going to go down D2. All right, so here's the direction. And then it's going to go back to the source like that. So that's the current path during the positive half cycle. So during the positive half cycle, we're going to forward bias D1. All right, we're also going to forward bias D2. We're going to reverse bias D3 and D4, and then here is the current path. All right, and it goes around this little loop, and it goes like that. Now, the capacitor, we're going to get back, we're going to swing back to what the capacitor is doing, but as this current flows here and as this voltage develops, what happens to the capacitor? Well, as the positive voltage develops, right, we're going to get a positive to negative on that capacitor, right? So this capacitor is going to reflect this positive voltage, meaning what's going to happen is the first time this thing works, the capacitor is going to charge, right? And it's going to sit there at whatever this voltage is. Oh, what's that voltage? It's going to sit there at 5 volts, all right? So this is going to be 5 volts. It's going to be on this capacitor. So now the capacitor is charged to 5 volts after this first cycle. As it goes a negative, it's not going to do anything to the capacitor. The capacitor is going to keep that 5 volts on it because it already has 5 volts on it, all right? Now, let's go and now let's do the other half cycle. Let's do the negative half cycle, all right? So let's do the negative half cycle. All right, so now, okay, and let's draw this. So what do we get? We get our signal here. So we get a copy of that first cycle. But what do we not get? We know that the amplitude of this is slightly less, right? We know that the amplitude of this is, what is it? It's going to be 4.3 volts approximately, because we have to overcome the forward voltage drop of this diode, all right? Okay. Moreover, we also have to overcome the forward voltage drop of this diode as well. So the voltage is not going to be as high as the source voltage because of these diodes, because they're not ideal. So that capacitor really isn't going to get 5 volts, is it? It's going to get more, approximately 5 volts, but it's really going to get more like 4.3 volts on it. Okay, so let's do the next half cycle. All right, so I've got to erase these, unfortunately. So as a matter of fact, yeah, so let's just we'll do this in a, so let's do this. All right, this is going to get a little bit messy. So here's the first half cycle, which is red, okay? And now let's use, we'll use this, this blue color here. Cyan is going to be the negative cycle. Okay, so now during the negative cycle, we've got negative here and we've got positive here. Okay, so we got negative here and we got positive here. So now this is where things get interesting. So now in this case, so now we've got positive here, so we got positive here. So what ends up happening, we reverse bias D2 this time, but we forward bias D4. So now we're going to get a current going through this direction. Now the current can't go through D1, that would be in the wrong direction, so current goes out this way. All right, so it goes out this way, and again, it's going to go through this load. All right, again, something's going to happen to that capacitor. We're going to dump charge on that if we need to. So again, the capacitor is part of the circuit. We're going to dump charge on that. Now the current's going to flow through here. And again, we've got that capacitor there. All right, we're going to keep going, keep going, keep going. All right, now here we go. Now here's where it gets interesting. Here comes this current. Now, the current, which direction does this current want to go? So here was the positive. So this current wants to go back to the negative of the circuit. All right, and so here is negative of the circuit, right? And so we've got this current here is slightly positive, all right, but it's definitely not going to want to go in this direction because that would be going back to the positive. So it's not going to go down D2. This is going to be reverse bias. It's going to go through D3, which is forward bias because this end of D3 is absolutely at ground. So any positive voltage on this side of D3 is going to forward bias it, all right? So we're going to go through here. This is now forward biased, and then we're going to end up back here at negative. All right. So this is what a full wave rectifier does. All right. So you can talk about during each cycle which diodes are forward biased, which are reverse, which are conducting, which are not conducting, and it's this kind of messy analysis. All right. Now let's go ahead and let's draw. So what's going to happen is we're always getting a positive out of here. So now it looks like this. So there it is, right? And on the next cycle, so this one's this guy, this one's this guy, and again, this one is going to come down here, and we're going to get this one again here, all right? And then, you know, aside from my horrible drawing here, and then we're going to get this one here, all right? So each time, basically, we're rectifying the signal, and this would all be exactly perfect, right? I'm just this is not easy to draw this. So this is a full wave rectification. So every time we get one of these cycles, positive and negative, they all get flipped around to positive. Okay, now here's where it gets interesting with the capacitor. Let's talk about that. All right. So now what the capacitor does for us, let's do this in white. So we have our load right here. So say there's a load and there's some resistance, right? Say it's 100 ohms, all right, or 1K ohm. So we've got this voltage here, which is rippling up and down like this, right? And so if we put it over that 100 ohm, we're going to get current that looks like that also. But if we dump this charge into this capacitor is going to charge up to 5 volts each time. So here's that situation. It's charging up to 5 volts, right? And now it would just sit there, right? It's charged up at 5 volts, but wait a minute, we put a load on it. Because we put a load on it, so what is this going to end up looking like, right? It's going to start dipping back down again because we're pulling charge off of it through this load, right? So it's going to dip back down. But wait a minute, here comes another cycle, right? Each one of these cycles, and it recharges it again. And then it starts dipping back down again, recharges it again, dips it back down again. So this thing ultimately looks like, let me draw it right here. So the voltage over our load as a function of time really looks like this. It goes up with our exponential charge. It goes like this. It gets charged again. Goes like this. Okay, that is, make it a little bit better here to make it a little bit more correct. There we go. All right, and then it charges again, and then it goes down, charges again, then it goes down. All right, and then it just keeps going on. To infinity. So this level right here, right? So this level right here is kind of this ripple, and this is whatever you can tolerate. So say that this point right here, say that stayed at 4.5 volts, and then we have this 500 millivolts, right? 500 millivolts of ripple in this little region right here because of our capacitor. And so if this is enough regulation just like this, then we're done. Then the circuit would work if we could tolerate that. But this is really gross and ugly. So what we typically want to do is we want to add a voltage regulator, a Zener diode or a full voltage regulator of some kind to clean that up. And we're going to get to power supplies in a little bit, but we want to keep talking about diodes right now. Okay, so that's another use. So that's a full wave rectifier. So this is a full wave rectifier. All right, full wave rectifier, right? So this is what you're going to need in front of a power supply. So typically this might be plugged in to a wall wart, and the wall wart might really look like a transformer, right? There would be the primary and there would be the secondary. These would of course be opened up, all right? So there would be the primary and there would be the secondary, and this would be your transformer. And this might be a 120 volts to 12 volts, right? So it might be a step down of 10, right? Transformer. And we've talked about transformers before, and we even did some experiments. We're going to talk about them again. All right, so 120 comes in, we get 12 volts out, but it's 12 volts AC, RMS, going up and down. So then we throw it through this full wave rectifier here. All right, now we get out this lobing DC. We throw that through a big giant capacitor to smooth out that ripple. Then we get this kind of situation here. We get this ripple here. All right, and then we could put that into our load if we wanted to. If this is a dirty circuit, that would be okay. But now what we really want to do is we want to take this output here and here, right? We want to take this, and now we want to regulate that. So this would be the front end. This is the front end to pretty much every single power supply, unless it's a switch mode power supply completely. So a transformer transforms the higher voltage down to a lower voltage, then it's rectified because this is AC, it's rectified to full wave rectified lobing DC, and then it's smoothed with a big capacitor, and then it goes into a voltage regulation block. So this is kind of, we're learning how these power supplies work. Okay, all right, so let's go back to the document here. All right, let's go back to our document, and let's talk about some other diode stuff here. Okay, so that was our full wave rectification. We went over that, so we know that. All right, and again, I really like you to read this section here in chapter 3, and which goes over this. But like I said, I don't want to keep doing all this math. I want to give you a break. All right, now, and then there's some examples here of using diodes as a voltage regulator. So let's take a quick look at that. So in this case right here, what's happening here is we have a voltage, and then if we apply a voltage to diodes in series, and we know that each one drops 0.7 once it forward conducts, if there's enough voltage to make these diodes conduct, we know that the voltage over here, no matter what the current is going to stay at 0.7 times 3, or 2.1 volts in this case, right? Roughly. As the current changes, the dynamic resistance of these diodes comes into play, and the voltage is going to vary. Maybe if the voltage is low here, we might get out 2 volts, and then if it's really high and there's a lot of current, maybe we get out 2.3 volts, but for more or less it's going to regulate, all right? And that's a quick and dirty voltage regulator. Now, you notice I have this resistor right here, and the reason why we have that is because we need something to limit this current right here. We can't just push it all through all these diodes here. So what happens here is we have a voltage here. So let's say that this voltage was 5 volts. 5 volts right here, and then we have a 100 ohm resistor right here, all right? And then we have these 3 diodes right here, and then we have a load resistor right here. So let's actually kind of run through this circuit and see what we got, all right? So what I'm going to do again is I'm going to put this over here so we can see it. But this is another application of diodes, right? Just a little homemade voltage regulator. So I'm going to erase all that. Okay, so let's go ahead and let's draw this again. So we just have something like this, and we've got a resistor here, all right, and then we've got 3 diodes. And so again, the whole point is we're learning how to use these devices as tools to get kind of what we want. All right, and then this is kind of the output here. And then in this case, we would put a load. All right, and this load might just be a resistor. All right, so I'm going to call this RL, and I'll call this R load. And I'm going to call this one RCL for current limiter. And I'm actually going to make this one equal to 100 ohms here. All right, and then we'll put this load equal to 1K and 10K. And we're going to kind of do some calculations. All right, now we're going to call this one D1, D2, D3. I'm going to tell you these are silicon diodes. All right. Silicon diodes, so we know that they're forward, they have to be forward biased like this, plus to minus, plus to minus, plus to minus, and we know that each one of their voltage drops is approximately 0.7 when they are conducting for the most part. Of course, this changes. It's not exactly always 0.7. It varies as the current goes from 0 to, say, an amp, right? So it might be 0.6, then it might be 0.7, 0.8, 0.9, and all the way up to 1.1 volts. Remember, the 4001, we looked at the data sheet, it's 1.1 volts if you push an amp through here, right? But we're going to call it 0.7 for now. All right, so now let's get our V in here. All right, so we're going to call this V in right here. All right, and then now the question is if we set V in at some voltage, so let's say that we have a 5-volt supply someplace, and that's what we're going to put V in at. So then we're going to get a current here. All right, so first let's pretend there's no load here. So let's do with a no load. So we'll say that here's the no load current. So we're going to get a current, and the current's going to flow down through here, right? Like this, down to ground. All right, and so the question is, so we're going to call this I. We'll call this INL for no load, INL. So what does that equal? All right, so here's the thing. We know we have 5 volts. So we've got 5 volts up here. So we definitely have enough to forward bias these diodes, all right? We got enough to forward bias them. So let's assume they're forward biased. This is how you have to kind of do diodes and transistors. You make an assumption based on your observations. So 5 volts, so we know that it's forward biased. So each one of these is going to be on, it's going to be conducting. That means each one's going to drop 0.7 volts. Okay, so if each one of these drops 0.7 volts, then we know that the total voltage drop over here is going to be 3 times 0.7, which is going to be equal to 2.1 volts. All right, so we got 2.1 volts. So this node right here is 2.1 volts. We all agree with that. If this node is 2.1 volts, we already know that this node is 5 volts. Therefore, what is the current going through this circuit? Well, current, remember V equals I times R. Therefore, I equals V over R. What is our V? Well, it's 5 volts minus 2.1 volts. That's going to be over this resistor, right? Divided by the resistor value, which is 100 ohms. All right, everyone get out their calculator. Let's do this. So 5 volts minus 2.1 volts equals, divided by 100 equals 29 milliamps. Okay, 29 milliamps. All right, so 29 milliamps. All right, so this current right here is 29 milliamps when there is no load, when we don't have a load connected. So the circuit is on, it's running, there's 29 milliamps flowing through it, everyone is happy. Okay, now let's go ahead and now we're going to add this resistor in, and now we're going to assume the resistor is now connected. Now, these kind of circuits here are actually very difficult to perfectly compute the calculations. It has to be done through iteration. All right, so that's why you would use simulation if you want to be exactly correct. But we kind of, what we do is we figure out the voltage drops over here, we kind of make some assumptions, and we can get pretty close with these assumptions. But to do this actually correctly, you'd have to do a simulation or build it and then look exactly what it is, because what's going to happen is as we change the current through here, these voltages are going to change. As the voltages change, the current's going to change. Get it? And so on and so forth. It's like a circular problem until it stabilizes, all right, and comes to equilibrium. All right, so anyway, so now we're going to add this load of 1K. Well, what's the voltage? We know what the voltage is. It's 2.1, right? Okay, so it's 2.1 volts. All right, great. So there's 2.1 volts there. Now forget about this 29 milliamperes. Let's just say it's 2.1 volts and forget about the 29 milliamps. So remember, all that 29 milliamps was going through here before. All of it was going through here, right? Because there was no current going in this direction. Now there is going to be a current going in this direction. What's that current going to be? Well, it's 2.1 volts over the resistance. So at the 1K and 10K, let's figure out what these two things would be. So again, we're going to take the voltage divided by the resistance, the voltage divided by the resistance in each one of these, and let's just calculate it. All right, so we got 2.1 divided by 1K equals, so in this case, we've got 2.1 volts divided by 1K, and that equals 2.1 milliamps. All right, and then by divided by 10K, 2.1 volts divided by 10 K ohms, and we know that's just going to be 0.21 milliamps, right? It's going to be 1/10 of that. Or we could move this decimal place over, 210 microamps, whichever way you want to do it. Okay, so let's look at the 1K case. The 1K case. So in the 1K case, about 2.1 milliamps, here comes 2.1 milliamps, is going to be redirected, milliamps, is going to be redirected through here. So we've got our 29 milliamps coming in. We got 2.1 coming down through this branch. Therefore, down in this branch right here, we're just going to have 29 minus 2.1 milliamps, which is going to equal 29 minus 2.1 equals 26.9. 26.9 milliamps. All right, coming down this branch. So we basically got a voltage regulator here. It's staying at 2.1 volts. All right, great. Okay, so we did the 2.1 milliamps. And so what did we do? We pulled, this is about 30 milliamps, we pulled 2 milliamps. We pulled a very little amount of current from the diodes, meaning that voltage is not going to change much, okay? So when we do the 0.21 milliamp, where we have a 10K load, even less current is going to be pulled away. So in that case, let's do that. So what do we have? We have 29 milliamps minus 0.21 milliamps, right? So obviously, we can do that on the calculator. 29 minus 0.21, of course, is 28.79, equals 28.79 milliamps. For all intent and purposes, it's the same. So instead of 2.1 milliamps, we're talking about, in this case, 0.21 milliamps. So then the current going down the main branch, instead, that turns down, drops down to slightly 28.79. So the point is, the smaller the load current, right, or the larger the load impedance, the smaller the load current, we modify this current going through the regulation chain even less so that the regulation stays accurate. It regulates. So this 2.1 volts doesn't change much. Now, what we just did was we didn't do any iteration. So now the whole point is that after we do this calculation and we see what this voltage is here, what the current is going down these, going through these diodes, then we go to the data sheet in the diodes and we would say, oh, at that current, oh, the voltage drop is only 0.62 volts. So then we would adjust 0.62 volts. That would also change what the voltage drop is here and this and that, and all of it would change, and that's why you have to use iteration. But for the most part, it's going to be pretty accurate if we do the analysis that we just did. The point is that you can make a voltage regulator just by putting diodes in series like this, all right? And so you could say if you had 9 volts coming in here instead of 5 and you needed 5 volts, you could just put a bunch of diodes in series and you could create 5 volts. There are better ways to do this, of course, but in a pinch, you can do this. For example, say like you had like, 5.9 volts, some battery or something, 5.9 volt battery, and you wanted to get, approximately a 5.0 volts out of that. Well, you would just go ahead and put one diode in there. Just so we would take the 5.9 volts, right? And that would be our in, and then we would take one diode here, right? And then so this would be V in, this would be V out. And as this circuit conducts and we put our load over here to the right, whatever our load might be, right? Here might be our load to ground, right? This thing is going to drop roughly 0.7 volts once this thing turns on. So we're going to get, 5.2 here. 5.2 volts, close enough to 5, better than 5.9, probably within the tolerance it would work. So this would work even with a digital circuit. So as the circuit, whatever this load is, now remember this is a representation, so it's like quotes around the load, right? It's just a black box. As this load draws more current, the current as it goes through this diode here is going to change the voltage drop over the diode, which is going to change this regulation here and this regulated voltage here. So this is going to vary up and down a little bit, right? But not too much, right? So that's how much regulation that you have. So you would call this load regulation. So that means how does the voltage vary as the load varies? All right, and that's one kind of regulation. Another kind of regulation is how does the regulation vary as the source of the circuit, the input voltage changes. All right. So anyway, so that's some things that we can do with diodes there. Okay, so. Uh, we've gone about an hour in this lecture. I don't like to get much over that. So why don't we let's stop here and let's come back again, and then let's talk about we're going to talk about more diodes. We're going to talk about Zener diodes and Schottky diodes, and some more regulation stuff with them. We'll talk about those two kinds, and then I think that we will be ready to go to the bench and build some stuff with this. All right. So let's pause here, take a break, come back to the next lecture, and we'll follow up with Zener and Schottky diodes. All right. All right. I'll see you there. Bye. Okay, welcome back. So we just took a little pause to kind of break up the diode material. So now we're going to talk about two other diodes that kind of have special properties. And we've talked about these before back in the semiconductor theory lectures, but now we're going to talk about them again and kind of more their applications. So the two diodes are the Zener diode, which you see here on the screen, and you can see its little symbol is kind of these angles. Instead of the normal straight, we just have a straight line and a triangle for a normal silicon diode. We have these kind of angles here at the ends of each one of those at this vertical bar. This is a Zener diode. Now, what's interesting about a Zener diode is that the way it operates is it's designed to operate in the reverse voltage direction. So basically, the theory behind the Zener diode, we're not going to talk about how it works at a semiconductor and atomic theory level. But I'm going to show you a couple of pages that I want you to read. But the whole idea is that Zener diodes have different voltages. So they might have 3.3 volts, 3.9 volts, 5.1. And typically Zener diodes are used to clamp a voltage to a specific voltage. So say if you have a voltage in a system of 12 volts, you can clamp it down to 5 volts with a Zener diode. All right, and we're going to see how you do that. All right, so inside of the book here, in chapter 3, roughly, Zener diodes, I want you to read this material here. And here's an example, and you can kind of go through this. We're gonna draw a circuit in a second. But what this is showing here is we've got kind of a Zener regulator. And so how this works is you take a Zener diode, and Zener diodes will have a voltage that is their Zener voltage, and you can basically select whatever you want, almost anything to anything, go from a few volts to hundreds of volts, actually, a couple hundred volts at least. So in this case, say that we have an input, maybe it's 12 volts or 15 volts, could be anything, anything high. And what you do is you set up a circuit where you have a resistor here. And so this resistor is a current limiter, and this sets up a minimum Zener current. So the whole idea is that you have this Zener diode, and then notice it's placed in the reverse bias direction. So it's going to work in the reverse direction or in the breakdown direction. And so what happens here is, say we had 12 volts here at this VN, all right? So we put the Zener in this direction, and the Zener starts flowing current in this opposite direction. But the interesting thing about it is, instead of having a normal semiconductor forward voltage of say 0.6 or 0.7, a semiconductor diode, it has this Zener voltage, and in this case it's 5.1 volts. So up here at this node, we're going to see a 5.1 volt. Now, as that Zener current increases or decreases, that 5.1 volts will slightly vary, all right? And that has to do with what's called the Zener resistance or dynamic resistance. So the Zener diode has a small resistance, and as that current changes, the current times that resistance modulates the voltage that you would see on the Zener diode. But nevertheless, it's used for voltage regulation. So all you need to have is a resistor, your Zener, then you put your load here off of the Zener, which is generating the voltage that you want, and you have a regulator. So this is really, really cool. The only requirements is that with the load or without the load, you have to have enough Zener current going through the Zener diode to maintain Zener regulation. All right, and you can look this up in the data sheet. And in a minute, we're going to take some parts here that I have on the bench. I've written them down. We're just going to look them up real quick because I want you to see that process again. But anyway, if you read through here, this kind of describes what's going on in detail, what I was just talking about. It's only a couple pages long, and explains this process. So that's a Zener diode. All right. So Zener diodes are used to clamp voltages, a larger voltage to a smaller voltage. But you have to keep the Zener diode operating, and you do that in its reverse direction, and you have to have a minimum what's called Zener current to maintain that voltage regulation, and there's what's called the dynamic resistance or the Zener resistance, and that small resistance, it might be 1 ohm, 2 ohm, 5 ohms, 10 ohms, as the current flows through the Zener. Very little current we want to flow. We want the minimum amount of current to flow through the Zener, as a matter of fact. In this circuit here, I don't want to waste current through the Zener, but we want to put as much current through the Zener as necessary to maintain regulation so we can use it as a voltage regulator. All right. So in any case, that's kind of the circuit we build. All right. So that's a Zener diode. The other diode that I want to talk about is called a Schottky diode. All right, and there's no material in this in my book on this, so I want to go over here to Wikipedia for you. And what I'd like you to do is two things. One, I'd like you to look up Zener diode. Zener underscore diode is the actual page here in Wikipedia, and just go ahead and scroll through this and take a look at this material here, because this has got some good information here. Oh, and in fact, there's the circuit that we just drew right there. It's showing the exact thing. We've got IR, we've got this Zener current, and then we've got this load current here. All right, and that's an example of a voltage regulator. All right. And anyway, it kind of goes through and gives you just some more technical material that explains the Zener. But the Zener is fairly complex, and it's based on quantum tunneling, or what's called avalanche breakdown. And quantum tunneling is, for example, remember, electrons can basically disintegrate and reintegrate in a different position, so they actually can move through space or move through an object without ever going through. That's called quantum tunneling, and a lot of semiconductor devices operate on that. So does the scanning electron microscope. Works by quantum tunneling. But anyway, you can read about this and how this works, but I didn't want to get into all that complexity. I just want you to know that it's used as a clamp, or we can use it as a regulator, and we're going to build circuits that use these, so that's why we're trying to keep the theory down to a minimum. Okay, now let's go talk about a Schottky diode. So, and we've talked about this before, the Schottky diode is named after Walter Schottky, and the difference in this is a normal silicon diode has a forward voltage of 600, 700 millivolts because it's got a P and an N junction. But the Schottky forward voltage is very small, 150 to 450 millivolts, depending on what device you find you purchase. But the interesting thing about it is, the reason why is because the junction is just one semiconductor and a metal. It's not two semiconductors, a P and an N. It's just one semiconductor, an N or a P type with metal. And so you get this lower voltage because that depletion zone is smaller, that voltage. So these are very, very useful in circuits where you want to make sure that current's only flowing in one direction, or power supply circuits where you want to make sure current's flowing in one direction, but you don't want to take that big 600, 700 millivolts drop. And they have lots of other properties as well. The symbol for it, as you can see over here, is the triangle again with a straight bar with kind of an upside down U and then a U at the bottom. So very similar to the Zener. Now, we use the Schottky just like we use the silicon diode. All right, except we use it where we want to have a very small forward voltage, and we can tolerate some of its other properties. Okay, so now those are the two diodes that we want to look at and play with, the Zener and the Schottky diode. And so let's take a look on DigiKey here and Newark at some of these devices and just look them up. So over here on the bench, we're going to use these in the actual experiment, but right now let's take a look at what we got. So one of them I have is a 1N47 4739A. So let's look that up. All right, so we find it and it's right here. All right, and we'll go to the product page here. So this is a Zener with 9.1 volts. All right, this package, this common package that you'll see like this is there's a few different names for it, but typically it's a DO41 package. All right, and it's plastic, and the line is always the cathode. All right, so current is going to flow from this direction down towards this direction. And in the reverse direction, it would flow in this direction towards this direction. All right, so now we look at some of the other properties of it. So it's a 9.1 volt Zener, and it can handle 1 watt of power going through it. So that means whatever the Zener current is, and then times the 9.1 volts, it can't exceed 1 watt. This ZZT, so this has to do with that Zener resistance we're talking about. This is the maximum. Now that Zener resistance actually is dynamic as well, but what this means is that it acts as 5 ohms. So as that current changes through the Zener, it gets multiplied by that 5 ohm, and that is what changes that voltage drop over it and modulates it from the 9.1. And then there's just some other parameters here, right? But the bottom line is it's a 9.1 volt Zener that can handle a watt of current going through it. And so say if we needed to make a 9 volt power supply real cheap, so say we had 12 volts or 14 volts or a higher voltage than 9 volts, then we could basically use that same circuit, and that circuit would be something like this. We would come in here, we've got Zener regulator, we'll say. So we come in, we have a resistor here, we've got our output here, then we've got to be careful. We want to put our Zener in backwards here. This is the key, this is the trick, all right? So there's the cathode and there's the anode right there. All right, so there's our R, there's our Z, not to be confused with impedance, it's just Z for Zener. And let's say that this was a 9.1 volt Zener. And then let's say off this node right here, we came down and we had a resistor, and let's say that this is a 1K resistor right here, right? So now let's say that this was, we could say that this is 100 ohms, and we could say that this is 12 volts right here. All right, so in this case, now let's say that we first have the case with no load connected to it. So this is a load side. Say there was no load, say that this line represents a break, or we could just draw the break in there, right? We just draw that, but just assume there's a break in there for the moment. So we've got 12 volts, and we've got this resistor here, and then we've got this Zener. So we're going to assume that we're going to break down the Zener, all right, and it's going to sit at 9.1 volts at this node, 9.1 volts at that node. Therefore, what's the current going through here? Well, the current is simply this voltage minus this voltage, right? So this is, call this V1, call that V2, right? So that would be V1 minus V2 over this 100 ohms, right? This would be this I, right? And we can call this I, all right? So that would be equal to 12 minus 9.1 over 100. So let's get out our calculators and do that calculation. So that's 12 minus 9.1 equals 2.9, obviously, divided by 100 equals 29 milliamperes. So 29 is a popular number today. So this is 29 milliamperes. All right, so now with no load, that means that all of that 29 milliamperes is going to go down in this direction, down this Zener path, right? And so then we need to look up what's the minimum current required to maintain Zener regulation for this device, all right? Now, if we go back to that DigiKey page, so we go back here, and this has got a number of these different Zeners. So we're looking at the 4739, which is the 9.1. So we open up this data sheet, and I haven't done this yet, so we may not be able to find it easily, but there's usually a table someplace. Yeah, so there's usually a table, and which one are we using? We were looking up the 1N4739. So we can take that, copy that, and then open this up and search for that. And there it is. All right, so in the table, we can kind of look across here, and these tables are sometimes very hard to decrypt, but in this case, so we've got our Zener, and let me make this a little bit bigger for you. All right, so this is saying the Zener voltage at IZT. So at some specific IZT, which is just the test current, the Zener voltage is 9.1. As that current goes up or goes down, this voltage changes a little bit based on the dynamic resistance, which is either called R dynamic or ZZT, that kind of thing. So this is tested under 28 milliamperes. So that's quite high. So in other words, you got to put 28 milliamperes to guarantee this 9.1 here. All right, and then let's see here. Then it's saying that, for example, at half a milliampere, it's got 5 ohms as the dynamic resistance, all right? And then some other values here, maximum reverse voltage and currents and things of that nature. So the point is that this requires, at 9.1, it requires quite a bit of current to maintain that regulation. So as we drop this current less and less and less, we're probably not going to get this regulation out of here. If we go higher, we'll probably be okay, but as we go less, we're going to start really losing that regulation with this particular model. So put a pin in that and just kind of remember that, that this kind of likes a lot of current to maintain that. So when we build this circuit, what we might do is we might set this up so that, say that 100 ohm right there, right? Say we put that as 1K ohm, right? And at 1K ohm, there's going to be very little Zener current to maintain this regulation, and we'll see what that 9.1 is. We'll see if it stays at 9.1 or where it actually goes. Now, the point is that once you maintain this Zener regulation, now we throw the load on, right? As we throw the load on, the load is going to drag current away from this, right? So assuming that the voltage here is 9.1 volts and we put a 1K on here, right? Then what's going to happen? We're going to get, so let's figure out what is the current that's going to end up going down this path. So I'll call this IL for I load. So that's simply going to be IL equals 9.1 volts divided by the 1K ohms, right? And so what is that? 9.1 divided by 1K. And remember, whenever you have volts divided by K, it's always milliamps, right? So it's 9.1 milliamps. We know that, right? But, you know, always use the calculator. It doesn't hurt. So 9.1 milliamps now is the current going through this branch right here. All right, so we got 9.1 milliamps going through this branch. And we had, where was it, 29 milliamperes going down through the Zener. Now we're going to pull away 9.1. So now we've got approximately, right, 29 milliamperes minus 9.1 milliamperes is now what is going to run through the Zener now. That's all it's going to be left to go through the Zener, right? So this current here is now what's going to go through the Zener because we're dragging away, we're pulling away 9.1. So 29 minus 9.1 is 20, it's 19.9, right? So now we're going to have 19.9 milliamps going through the Zener. Now, at this point, we are not going to have that test current, right? So this 9.1 is at this test current of 28 milliamps. We're not going to have that test current. We're going to have a smaller current, which is only 20 milliamps, roughly 19.9. So that Zener voltage is not going to stay the same. It's not going to be 9.1. It's going to be higher, actually. And because that voltage is higher, then everything else is going to change, right? And again, that's where that iteration comes in. But as a first shot at it, you kind of do the calculation like this, and it's close enough. If you want to get it exact, you have to do simulation or build it. All right, so that's how you make a Zener regulator, all right? And the Zener could have been any value that we want. So let's look up a couple other values. And the point that I want to get here is that depending on the vendor, these data sheets are all over the place. Let's look at 1N751. Here's another Zener that I have here. And let's take a look at this one. All right, so this is a Zener. It's 5.1 volts is its Zener voltage. And this one's got an impedance of 17 ohms. This one only can dissipate 500 milliwatts, half of it. All right, and again, we can go to its data sheet and pop open its data sheet, which I'll do here, and open this up. All right, and this is a central semiconductor part. and what was it, a 751A? Here it is here. All right, 751A. So Zener voltage, so it kind of varies between 4.8 and 5.3. They're calling the nominal at 5.1. This is at a 20 milliamp test current. So now as the current modulates from that 20, the Zener impedance here is a 17 ohms, all right? And then as that current varies from that, then we can compute what the actual voltage would be up and down. But they're kind of telling you these are the ranges here for their tests. And again, that's what these tables are for. Here is to kind of let you give you this information. All right, so this would be great if you want to do a 5-volt power supply. So you want to do a 5-volt regulator, right? All we have to do is take this circuit right here, and we would erase whatever that 9.1 guy was, Zener was, and we just put in a 1N751 in there. All right, and then now we would have a 5.1 volt regulator, and we'd see 5.1 volts at that node right there. So we could actually use that in a circuit. So one thing that we could do, so let's go ahead and let's erase this. Let's erase this stuff here. And so take a look here. What we can do is, so let's say for example that we came in and we had, and I'm just kind of doing this for fun. Let's say we had a 120 volt AC, all right, and then we come through here through a transformer. And remember, the transformer can step up or step down voltage and current. All right, so let's say that this is a 120 volt to a 12 volt, all right, and both of these are always root mean square, RMS values. 12 volt step down, all right, so this is basically stepping down 10 times, right? So it's a 10 to 1 step down, so it's a 10 to 1 step down. All right, so there's our transformer. Okay, and then now, so we've still got AC, right? So we got AC coming in here, and we've got AC coming in here, but smaller, right? So we can draw that smaller. All right. Now what we do is we put this through a bridge rectifier, right? So we put it through our bridge rectifier, and I'm just going to represent that with this diamond here. So represent with this diamond here like this, and then here would be, and let's draw it kind of like this, kind of like that. Okay. All right, and then assume that this is plus and this is minus. There's our bridge rectifier, so we'll call that bridge. All right, and we'll say that this is X-former, transformer. All right, and there's our bridge. And we just figure out how to draw those diodes. Now, let me show you something. Since bridge rectifiers are so common, instead of doing it discretely with 4 diodes, they have devices that are bridge rectifiers. And here's one right here. Put it up there. I don't know if it's focusing or not focusing. But anyway, there's a bridge rectifier, and you notice it has 4 leads. 2 of them for the AC, and then 2 of them are the plus and the minus. And they have different size bridge rectifiers. Some are really small, some are really big for high power and high voltage. So instead of doing it discretely, you just get a bridge rectifier, and we'll use that in the experiment. Okay, so now what we do is, let's put a big capacitor here, C, okay? And let's assume that this bridge rectifier, let's use 1N4001 diodes in each one of these little bridge locations, all right, and not use a bridge rectifier in this case. For our capacitor, let's just say that we have a 4700 microfarad capacitor, okay, and so we're going to have some good ripple protection, but not too much. Okay, and then let's call this ground here also. This is ground, going to ground. All right, and so we can call this ground here. All of this is ground now. All right, and now we can come through here and we can put a small resistor. So let's call this, we'll call this, 100 ohms. We won't be able to, so that'll limit our current here somewhat. So we got 100 ohms. All right, and then what did we have here? This is going to be 12 volts RMS at this node right here, right? So at this node right here, we're going to get 12 volts RMS, and it's going to charge that capacitor. So we got 12 volts coming into this part of the circuit. Now let's go ahead and right here we can put an output, and then here we can put a Zener, right, to ground. And let's put our little Zener symbol here like this. And let's say that this Zener is a 5.1. So let's say that this is a 5.1 volt Zener right there. So 5.1 volt Zener. All right, and then we put our load, whatever our load is here. And now I'm going to abstract this concept of load into a box. There's our load. All right, so there's our circuit right now. So let's use red here. So there's our circuit. So as current flows this way and then flows back this way, this transformer works, right? And a magnetic field is generated and collapsed, which then causes a current to flow this way, right, and back this way, and then vice versa. All right, then we've got this capacitor charging here, and then so we're getting this DC here that's kind of looking like this, not DC, but it's at least it's not AC, it's low being DC. Charges like this, charges like that, so we're getting this ripple up here, right? And then if we were to graph this, this right here might be at, this would be maybe at, say 11 volts, and then up here might be 12 volts across the top there, right? In this region inside of the middle here, this is kind of this ripple area, right? But that's all going to charge up this capacitor, and this rising and falling happens because we keep pulling charge off the capacitor. But now we've got this Zener circuit here. We've got this Zener regulator circuit here, which is basically this block right here. So now this Zener keeps this voltage clamped at 5.1. So even though at this node right here, this is going up and going down slightly and it's rippling as we're drawing charge away from it, this Zener really tries to maintain it at 5.1 volts. So now remember back in the other video, I talked about two things. I talked about load regulation, right? So at this end, we have load regulation, and that means how well does the regulation work as the load changes, right? So as this changes from, say, 100 ohms to 1K to 10K or whatever. But now there's, remember, the source regulation or line regulation. So that's this right here. So line regulation. And what that means is, let's not change the load, just leave the load exactly static, leave it at 1K or 10K, but this line regulation, this line is going to change as this AC system is working here and charging this capacitor. The voltage here is going to keep fluctuating. So as it fluctuates, we're going to see a slight fluctuation out here at the load. So that's called line regulation. How well does this voltage stay stable as a function of this changing? So this can change or the load can change, and no matter what, we want this voltage to stay at, in this case, 5.1 volts, end of story. That's called regulation. So I don't care what the current is we pull out of this, I want 5.1 volts. That's what a regulator is. So this is a very simple regulator, but we're starting to see that how we build them. We have a transformer, we got a bridge rectifier, we got a ripple capacitor. Then we have this crude regulator right now because we don't know how to make anything else. We're going to get to the point very shortly where we're going to learn about actual voltage regulators, which have lots of transistors and diodes and Zeners and all kinds of stuff inside of them and feedback loops so that they maintain their target voltage no matter what happens. All right. Okay. So this is another example of using the Zener. All right, and let's see, is there, oh yeah, one thing I want to show you. This is just a practical matter, and the practical matter is this. So on DigiKey, you can usually find everything, all right, DigiKey or Octopart, Mouser, but some parts you got to find on different sites. So for example, NTE, this is another manufacturer. So NTE, let's say, let's look at this one right here. 5116A, 5116A, which is another part I've got here on my bench. All right, weren't able to find anything based on your search entry. Well, the reason why is because DigiKey does not sell this part, all right? But another company that does is Newark, and Newark is out of the UK, and they have a lot of parts as well. And if it's not on DigiKey, it's going to be on Newark. All right, so we'll put 515116A, and sure enough, there it is on the Newark site. So Newark.com, another site, and there it is. And this is a Zener diode, 5.1, 5 watt. All right, so if it's 5 watt, it can handle 1 amp at 5.1 volts, so that's that. It's got a DO35, which is this package, just a little smaller glass passivated package than the other one. And that's it, through hole, and it can handle 200 degrees Celsius because it's glass, all right, 200 degrees Celsius. All right, so again, you can use Newark, and then let's see here, Octopart. which is this other database. So now if we type in NTE 516A, all right, now it shows you it's at Newark, it's at Master, Vetco, and MCM. So basically, it's at none of these are big distributors that you would normally have heard of, except for Newark. So you see, Newark is the only one that came up. DigiKey, Mouser, Future Electronics, Avnet, Arrow, none of those popped up. Only Newark did. And so a lot of times you can find things at Newark if you cannot find them on DigiKey or Mouser, Avnet or Arrow or whatever a distributor site you use. But I suggest that you always use DigiKey and Mouser or Octopart to find parts and find their data sheets quickly and find budgetary pricing. Okay? All right, so now let's go and talk about the Schottky diode a little bit. So again, the Schottky diode, the point of that is it's got a lower forward voltage. And a lot of times what you do is you'll use Schottky diodes where you want kind of an ideal diode and you might want a fast diode, for example, a very fast diode. So Schottky diodes are very fast. And the reason why they're very fast is because they don't have that P and N junction. They just have one semiconductor, P or N, and metal. So you don't have to push everything out of this depletion region anymore with a semiconductor action. So it's very, very fast. So they're used in switching circuits. They're used in current steering circuits and a lot of other things. One of the things that you'll see them used, they're also used in boost converters, buck converters, which we'll talk about in a lecture or two, which is another kind of voltage regulation. But you'll see them in one case that they're used a lot is this. So let's say, and you may have even done this, okay? So let's say that you have a power supply, and that power supply has a little 2.1 millimeter barrel connector on it, all right? So it's got a little female connector, and then what you do is you plug, and let's kind of, okay, God help me here, I'm gonna try and draw something in real time here. So we got this little barrel connector, that's not too bad. Got this little barrel connector, and it's got its wire coming out here, and then typically this is going to go to a wall wart, right? And then this would then plug into your AC line. All right. So so this might be 12 volts or 9 volts, something like that. And let me see if I've got one. So we're just talking about this thing, right? Just this thing, and then it's got this connector right here, and it plugs in. All right. That connector has a polarity. And if you look on the device, it'll say, it'll have a picture usually, and I don't think you're going to be able to see it there. I'll show it to you later, but it shows a little graphic, and it shows that the tip is positive and the ring is negative. So the tip here is positive, and this sheathing is negative. All right, so if you plug that into something that assumes it's the opposite direction, that would be very bad. All right, you short something out. So what we will do is this. So what I'm assuming is that this is going to be positive and this is going to be negative, right? The way that this connector works. But if, say, if it's flipped around, if you've got one of these connectors that's reversed, then you're going to put plus to minus and minus to plus. Very, very bad. So what we do is we just put a diode in here, right? And we put a diode in here. Now, we could just put a normal silicon diode. Nothing wrong with that, right? And then this would then could go on to other parts of the system, okay? The only problem is, let's say that whatever this connector was, we're assuming that we get 9 volts out. Well, we get 9 volts right here, but what do we get right here? Well, we're going to get like 8.2, 8.3 volts here. That is a lot to lose. 700 millivolts is a lot to lose. 700 millivolts is a lot to lose. So what we'll do instead is we will use a Schottky diode, plus they're also very fast, and the Schottky diode may only drop 150 to 300 millivolts. All right, so now instead of this 8.2 here, right, so instead of that 8.2, let's just erase that. Now out of here we get something a little bit better, 9 minus, let's call it an average of 200, we get 8.8 volts. And maybe our system can tolerate that a little bit better. So in this case, we use the Schottky diode, and let's just spell that, S-C-H-O-T-T-K-Y, Schottky diode. We've used the Schottky diode for polarity protection, so that this has always got to be positive and negative. So now here's the thing: if this is negative and this is positive, say if this connector is reversed, right? Doesn't matter. Now we don't forward bias this diode, and now no current can flow here. So we can call this I. C for current in system. It will equal 0 if this is reverse polarity. Only when this is the proper polarity, plus and minus, will this thing turn on and you'll get current flow, because we're going to forward bias this. All right. Now remember, this is a Schottky, not a Zener. Zener is used for regulation. So the Schottky is used very similar to how the silicon diode is. All right. Now here's another interesting use of the Schottky diode. So we're going to learn about digital electronics very soon. We're going to start getting into digital stuff, which is going to be nice, a nice change. But let's talk about a wire OR gate. So if you're a computer programmer or anything like that, you know what and OR and logical operations are, and OR, XOR, NOT, etc. So two very important ones. The three important operations are OR, and NOT. All right, and actually you can, as long as you have and NOT, you can derive everything from it. But OR, and NOT kind of are the mainstay. And let's take a look at these real quick. So here is logically the logic symbol for an OR gate. So this is a logical OR, all right, and then this is a logical AND. It's flat, looks like this. And then here's a NOT. All right, here's a NOT, which is just simply a triangle with a bubble. Bubble means not. So if I put a bubble here, this turns this into a NAND. If I put a bubble here, this turns this into a NOR. All right, so we can get rid of those. All right, so here's our three basic gates. Now, with diodes, there's actually a whole type of technology called diode logic or diode transistor logic. But very simply, if you want to kind of OR two signals together, you can do it just with a couple diodes. Now, you got to be careful here. So let's say that you had one signal, and say this was a digital signal. So let's say it's digital-ish. Maybe it's analog right now, but you want to make it digital. So it's going from, say, 0 to 5 volts. All right, so 0 is going to be your 0 and 5 volts going to be your 1. All right, so that's cool. And then say you had another digital signal. Again, it's digital-ish, right? You want to make it digital, and it's 0 or it's 5 volts. And that's going to be the 0 and 1. All right, so you got these two signals. All right, now, so here's the thing. So what would happen if you just tie these things together? All right, well, that would be bad, right? Because if you tie them together, let's say that this one is 0, and let's say that this one is 5. So 0 and 5, you just created a short, right? So you just created a short. The resistance is 0, so you're going to get an enormous amount of current, and you're going to blow the system up. Okay, so you can't do that. All right, so what's another thing you could do? Well, what you could do is you could put a resistor there. You could put a resistor there, and then you could tie them together. All right. So let's say that this is 1 k ohm, and let's say that this is 1 k ohm, all right? And then let's say that wherever this thing's going to end up is going to go into a 1 k ohm load, all right? So let's say there's the load there, all right? So this is one way you can do this. So if you have a 0 here, right? If you've got a 0 there, then there's 0 voltage here, all right? And then let's say that you had a 0 voltage, a 0 here, a 0 voltage here as well. So then basically both of these are tied together and they're tied to ground. So then virtually they're tied together and then tied to ground. All right. So then right now, as far as this load is concerned, it's just going to see 0 volts right there. Okay. All right. So a 0 and 0 made a 0. So that kind of worked out. Okay. All right. Now, what happens if we have a 5 volts here? So let's put a 5 volts here. So here's the 5 volt, and then let's use a different color so we can kind of see what's going on here. So let's say that we have 5 volts here, and let's put 0 volts here. All right. So we got 0 volts right here. So then that means that this is really connected to ground. All right. So this whole branch right here, right? This whole branch, really kind of think of it as just rotating around. and it's really another 1K resistor to ground, all right? Now we've got this 5 volts here, so I've got 5 volts here, all right, and then I've got this 1K and 1K here. All right, so let's do a little circuit analysis real quick. All right, so what's 1K in parallel with 1K? So 1K in parallel with 1K, do you remember that? What's that? So it's the product over the sum. So it's 1K ohm times 1K ohm over 1K ohm plus 1K ohm. All right, so it's a product over the sum. Get your calculators out. Do the math, and if you do the math, it's 1,000, right? 1,000 times 1,000 divided by 1 divided by, let's back this up a second here, okay? 1,000 plus 1,000. Now, all of us will know that that's 500. So if you put a resistor in parallel with itself, it's always going to be half of that, right? So 500 ohms. Okay, so this really looks, at this point, this whole thing looks like 500 ohms. Okay, so this is 500 ohms, this is 1K. Now here's where the problem kind of lies. So here's this 5 volts. So we got 5 volts and we got 500. So we really got a voltage divider. So what's the voltage that we're going to see at this node right here, which is going to kind of be the voltage at the load? Well, it's the voltage divider action. So it's going to be 500 divided by 500 plus the 1K equals times the input voltage, 5 volts, equals 1.6 volts. All right, so we're going to get 1.6 volts here. All right, will be 1.6 volts. All right, so let's do that again. So it's 500 divided by 500 plus 1,000 equals times 5 volts is 1.6 volts. So here's the problem. So when we have one of these on, like a digital circuit, we're looking for a digital OR. So I kind of want to get 5 volts out of this. So if either one of these is on, so the digital OR means either one is on or both are on. So here's the, I should have showed you the truth table. So let's call this X, let's call this Y, we'll call this Z. Here's X, here's Y, here's Z, here's X, here's Y. The truth table for the OR looks like this. Here's X, here's Y, here's Z. Looks like this. We got 0, 0, 0, 1, 1, 0, 1, 1. So when there's zeros, we get a 0 out. When either is 1, we get a 1 out, or they're both 1, we get a 1 out. For the AND, we've got X, we've got Y, we've got Z, and we got 0, 0, 0, 1, 1, 0. I'm just doing all the different permutations of the inputs. All right, an AND means both have to be high. So 0, 0, nope, both aren't high. 0, 1, nope, both aren't high. 1, 0, nope, both aren't high. 1, 1, that's it. And the NOT, it's just X and Y. So 0, 1, 1, 0. So those are little truth tables. And again, I'm getting ahead of myself here. That's why I'm rushing. We're going to go through this obviously in detail when we get through digital. Okay, so in this case, what did we put? We put a 1 in here, and then we put a 0 in here. All right, and our little digital system is 0 and 5 volts, so we're kind of expecting a 5 volts out, but we put in a 5 volts and we only got 1.6 volts out. So we got a high voltage, but not the full high voltage. Now, if we put 5 volts, but it did work as an OR gate, sort of. Now, if we flip this around and put the 5 volts here and the 0 here, obviously it's going to do the exact same thing because it's symmetrical. So the only other case would be if we put 5 volts on both of these, right? So if I put 5 volts here instead of the 0 volts and 5 volts here, right? So now what this really looks like is these two 5 volts are kind of like connected together. So now we got 1K and 1K. In parallel, what's that? That's our 500 ohms, all right? So we got 5 volts here through a virtual 500 ohm resistor to this node right here. So now our circuit looks like this. It looks like 5 volts, a resistor. Let's fix that resistor, all right, here. And then we've got our load, which is here, which is 1K. So the question is, we want to know what this V out is, all right? What's that V out right there? Okay, so we got 5 volts. We know that this is 500 ohms. And again, we've got another voltage divider. So all we need to do is compute, let's get red here, what is the voltage at this node right here, all right? So we got 1 and 1 coming in here in this case. So now here's a 1 and here's a 1. So let's erase this. This is a 1. This is a 1 here also. All right, in this case. All right, and this is kind of what the circuit now virtually looks like, because there's 5 here, so this really means both of these are in parallel. Okay, so let's do it. It's a voltage divider again. So it's a voltage divider, so it's going to be the voltage at V out. V out is going to equal V in times this resistor here, 1K, over the sum 1K plus 500. 1K plus 500 ohms, all right? So let's do it. So 1,000 divided by, here's where it's a good idea to use parentheses, so be careful when you're doing your divisions. I use a lot of parentheses, can't have too many parentheses. All right, so I just did that, so I get 0.666 times Vn times 5, all right? And now we get equals 3.3 volts. So now each one of these basically added 1.6 volts to it. Now we got 2 of them. So it's basically, it's summing this up for one thing. And this is how, so this is a kind of a digital analog converter also. It's summing it up. It's kind of acting as an OR gate. So it's acting as an OR gate, but here's the deal. 0, 0 gives us 0 volts out. 0, 1 gives us 1.6 volts out. 1, 0 gives us 1.6 volts out, but 1, 1 gives us 3.3 volts out, right? And with a bunch of decimal places. All right, so it's acting as a OR gate-ish, but what we would like is we would like this to act a little bit more digitally. So that's where these diodes can come in. So now take a look at this real quick, and then we're going to stop here. So we're going to do an OR with diodes here. Okay. So now watch this. So this is slick. So instead, we do this. We go here and we put a Schottky diode here. All right. And then we go here and we put a Schottky diode here. Okay. And then we tie these together like this. So here's our X and here's our Y and here's our Z out. And then here's where we put our load. All right. And then our question is, what's this V out here? And this load could be anything, could be 1K. All right, so now here's where this becomes interesting. So now watch this. So let's say that we put 0, 0 volts on both of them, 0 volt and 0 volt. If we put 0 volts on both of these, neither is forward biased. We're going to get a 0 volts out here. So let's erase this. All right. So for 0 and 0, we're going to get out 0 volts. All right, and actually, let's use a different color. Let's use a different color. Let's use red. Now let's use yellow. Okay. All right. So we've got yellow. So 0, 0 volts gives us 0 volts out. So that's correct. So 0, 0 gives us 0. All right. Now let's try and let's turn one of these on. So let's put one at 5 volts. So now one of these is at 5 volts. So this is, let's say that's this one, 1, 0. So we've got a 1 and a 0 here, right? So this is really a 1 and a 0. So now what happens? This diode is definitely not forward biased, so it's not on, so it's not part of the circuit. This one is on. It's forward biased. It's going to conduct. Current is going to conduct. What is the voltage? Well, it's going to plus to minus. We're going to get a forward voltage drop, of 0.2 volts, right? So at this node right here, what are we going to see? We're going to see about 4.8 volts. So look at that. So when one of them is on, we get 4.8 volts out. Cool. This one. 4.8 volts. All right. Similarly, when we flip this around and turn the other one on and this one off, we're going to get 4.8 here. And when we turn them both on, what's going to happen there? So now let's do that. So this one gets a little tricky if you want to figure it out exactly correctly. So both of them are on, so both are going to conduct. Both are going to drop about 0.2, 0.3 volts. And now both of them are going to want to be at 4.8 volts, but they won't both be exactly at 4.8. One will be 4.8, one will be 4.81, and then what's going to happen is they're going to fight a little bit, and there's going to be some, incompatibility or imbalance here. It's not going to hurt anything. One's going to flow a little bit more current than the other. So what's going to happen in this case is this. Let's call this, we'll call this Schottky 1, and we'll call this Schottky 2. There's a current that's going to end up finally going through here. We're going to call this IL. So IL will equal Schottky 1 plus Schottky 2. These are the currents through each one of these legs. right? Schottky 2 current and Schottky 1 current, they're going to sum up here and then become IL, except S1 will not equal S2. They'll be close, but they won't be equal, and they'll be unequal by the amount of basically imbalance between these two Schottky diodes, but it's not going to hurt anything. So now what are we going to get? We're again going to get about 4.8 volts. So basically we've created a digital system, right? That's almost perfect. You put in 5 volts, you get out 5 volts for the OR function, and you only lose a little bit, and that's the forward voltage drop of the Schottky to make it conduct, and that's it. So now this is called a it's a Schottky OR gate, and it's very cool. So in a pinch, if you just have a couple diodes or whatever, you can basically OR them together like this and connect the wires and then do this. You could do it with the wires and the resistors, but you saw what the problem is. It adds up as a current adder and more of a digital analog converter, which we're also going to talk to at some point. Let's talk about at some point. Okay, so I think that's it. And so we've talked about the Zeners, we've talked about the Schottkys, we've talked about some uses, we've talked about regulation, we've talked about actually even using the Schottky for digital, we've talked about using it for polarity protection on our circuits here, which is another thing. So Schottkys are good for current steering and a lot of other things, and like I said, for very high-speed uses. But for some simple things, if you want to make current go in one direction, use a Schottky. If you want to, rectify and you don't really care about the voltage getting dropped down too much, then go ahead and use your silicon diodes. If you want to regulate or clamp a voltage to a certain voltage, then use your Zeners. All right. So let's go back here to our document and let's see what's next here. So we are basically in the book here. It talks about transformers again. We've already talked about this a lot. Again, there's a transformer symbol. It's kind of a couple coils of wire, plus and minus. It's got a core, and then there's little dots sometimes which show the orientation. So instead of pluses and minuses, it'll have dots, which means as this goes positive, this side goes positive. If the dot is in the other direction on the bottom, then the other side goes positive, depending how those coils are round. All right, and then if here's the voltage in, and here's the number of turns here, and here's the number of turns here, and here's the voltage out here. Voltage out equals Vn times the turns ratio N2 over N1. All right, and we just want to use transformers when we need to transform voltage higher or lower or currents higher and lower. If the voltage goes up, then the current goes down. So this equation is the same for current. I out equals I in times N1 over N2. It's the opposite, just flipped around. All right. And so that is that. And then you can read through here. I want you to read through here. So we're not going to do another lecture on this. Okay. Now we're to power supplies, and this is a good time to stop. So we've actually been dabbling with power supplies so far. But now what we're going to do is, for the next lecture, we're going to actually go to the bench and work with the diodes and build some stuff with the diodes that we've been talking about with all the different things. Then we're going to come back for another lecture, and then we're going to formally talk about power supplies, and then we're going to build actual power supplies with regulators the right way. But first, we're going to do another lecture about diodes. But we're going to build it on the bench this time and not talk about it anymore. All right, so that's it. Our hour is up. So I will see you in the next lecture. Bye. All right, welcome back, everybody, and we are on the next lecture. This is the fun part. We're going to build the circuits we've been talking about. So I just left up on the drawing program what we were talking about last time. We were doing some digital implementation of an OR gate with the Schottky diodes, and we were kind of showing a power supply here, and so that we didn't have polarity protection problems and all that. So anyway, what I'm going to do is I'm going to go ahead and erase this for us here. And now what we're going to do is we're going to go over to the bench and we're going to do experiments kind of with all the different circuits that we've been talking about. So we'll do most of it on the bench, but we'll kind of come back up here as needed. All right, so let's see here. So first, why don't we, so we'll kind of put what we're going to do first. So why don't we do the, we'll do the half wave rectifier, and then we'll do like the full wave rectifier. And then if you recall, the half wave rectifier was pretty simple. We just have an input and then we have a diode here, right? And then we have our output. So we've got our V in or V out, and then we might have our load right here going to ground, and then plus to minus, and if we use silicon diodes, this would be 0.7 volts forward drop. So then we're getting kind of an output. So if we put an input in here that looks like this, all right, and that's 0 volts right there, and say that this is 0 volts right here, we're only going to get the positive half cycles, right? So we're going to get this kind of thing, and then flat, and then this kind of thing, right? Remember that? And then flat, and then this kind of thing, flat. All right, so that's a half wave rectifier. And then the full wave rectifier was something like this. We've got our input, and then we had this, and right now I'm just going to draw this as a black box. So we have this black box here, and we've got our V in, and we've got our plus and our minus here, which is going to switch back and forth. And then on the output here, we've got a plus and a minus, and this is ground right here, and this is always going to stay the same. So inside of here we had a bridge rectifier, right? And that bridge rectifier had 4 diodes, and those diodes are in a certain combination, and we can go look at those again. We can kind of figure it out, but we can look at them as well if we find our little drawing here. Back in the book material, there's our half wave. And so the bridge rectifier looks like that, right? So we've got diodes in those directions right there. So if we want to, we can draw those in exactly the same way. But the point is that when we have the full wave rectifier, we have our signal that comes here on our input, and then what we get is we get our wave, and then we reflect this wave like this. So we always get each one of the half waves out, and then remember we put a capacitor here for smoothing and all that. So we're just going to start playing with these. So let's do a half wave rectifier, we'll do a full wave rectifier. We're just going to do a bunch of experiments. We'll come back here and use the blackboard as needed, but let's just get right to it. All right, so let's get over to the bench and I'll meet you there. Okay, so we're here on the bench, and we've got our solderless breadboard, and let's go ahead and let's pull out a few things from whatever we were doing last. And this is a low-pass filter here. All right, I'll pull out those capacitors and pull out our little connector wires. All right, so now let's jump right into this. And what we're going to do is we're going to use the signal generator over here to my right, and we'll use the oscilloscope, and let's see if we can get rid of a little bit of, not really. We'll use the signal generator and the oscilloscope to look at our signals and generate our signals. So what we're going to do first is we're going to do the first experiment, which is just a diode and a load. All right, so let's use a silicon diode. So we use a 1N4001. All right, so I think, oops, these things are squirmy, and they're not that easy to get your hands on. So I think this is one right here. Let me take a close look at this 1N4001. Yep. Come here to the zoomed camera, and I'll zoom in on this for you so you can see it. And there it is right there. So 1N4001, 4001, all right? And the cathode is where that line is. See that line, that blue line? All right, so there we go. All right, so I'm going to just kind of bend that a little bit, and let's just zoom in a teeny tiny bit here for you. All right. Okay, so let's go ahead, and I'm going to cut this lead here with my cutters. Just cut a little bit off there because I want it to be nice and the same length. All right, and we're going to put this, say, right here. All right, so, and as a matter of fact, let's put it right here. We'll just use one side of this. All right. Okay, so we've got the anode here, we've got the cathode there. All right, so current is going to flow to the right, so left to the right. All right, okay, so we're going to put our input on the left side. Let's put a wire to put a little distance between us and the component. That way, if we have our alligator clips or probes or whatever, it makes it a little bit easier. So I'm just going to put that wire in there, nice and flat and short. All right, so there's that. And I'm going to put a little post there so I can get into that. These posts here on the bottom, these are just all in the ground rail, right? So I just put a few of those there so I can always get those ground signals. All right, there's our diode. And let's go ahead and let's put a resistor to ground. Let's just put something big right now. So let's put a 10K to ground. All right, so I'm going to put a 10K, so that's brown, black, orange, brown, black, orange. So take a look at that over there, brown, black, orange. On the zoom camera, there you go, black, brown, black, orange. All right, and we're going to put that straight to ground. So we're going to put this right here, straight to ground like that. Nice. Kind of move that over a little bit. Okay, so there's our circuit. I'll put it up on the side there for you. Let's see. I think we can zoom in a little bit more for you. Okay. All right, so far so good. So our inputs here goes to the diode, and there's our load. So on the right side, let's put the output. And so let's put the output. So we'll just put another piece of wire here, and we'll go like that, and we'll put another post there so we can get that signal. Okay, so this is looking like what we need for a half-wave rectifier. Okay, now, so here's the interesting thing. Let's first drive this with DC. All right, and then we'll drive it with a sinusoidal signal. All right, so what I'm going to do is I'm just going to go over to my bench power supply, and I am going to get a couple probes here. All right, and okay, that looks good. So what I want to show you is as a matter of fact, we'll use this model here because this one's easy, and I'm going to show this to you in a second, so I'm just setting it up, so bear with me. Okay, so we see one of my power supplies here, and so this is I think this one goes up to 30 volts. Yeah, 30 volts and maybe 1.5 amps. Yeah, 60 volts and 1.5 amps. All right. So anyway, we've got the fine and coarse adjustment here. So why don't we just set this, we'll set this at 0 volts with the fine. So it's at 0 and 0. And then this is how we turn it on. We enable the output. So I'm going to leave that off for now. And then what we're going to do is we're going to run the voltage up slowly here with just the fine adjustment. And then we're going to take a look at what happens. All right, so we've got the two cables coming out, ground and positive. So come back over here to our circuit, and hopefully they reach, barely. So there they are right there. They barely reach. So I'm going to slide this over just a little bit. Okay, so here's the ground right here, and here's the input right here. So we're going to put the positive there, and I'm going to put the ground right here. And matter of fact, it's just a little bit there. Get myself a little bit longer length there. All right, let me stop everything from moving. Okay. All right, and we're just going to hook this ground up right here. All right. Now, as I turn this voltage up here from the DC power supply, we're going to slowly forward bias this diode, and then we're going to get a signal out of the diode. Now, to look at the signal out of the diode, we can put it on the oscilloscope if we want, all right? But instead, what we're going to do is we're just going to use a simple multimeter this time, okay? And then we'll look at what the multimeter is doing as we do this, all right? So I'm going to get this multimeter right here. So what I'm going to do is I'm going to zoom out a bit, okay? Zooming out. And we will put our circuit up here. Now let's see, can we get our screen there? How's that? Okay, that's good. So I'm going to put this on voltage. So I'm going to put this on voltage, all right? And what we're going to do is we are going to hook the two probes up. And so let's get one of our connectors, one of our handy-dandy connectors. So one of these connectors right here, which is right out of a power supply from a PC, I cut them off and I make these connectors. So now, but what's nice is we're going to connect it right to our output, right here, and to ground, all right? So then I'm going to run another wire to ground, okay, right here. Okay, so now out of this cable here, we're going to plug in our multimeter. Okay, so we're going to do that. So here we go, I'm going to plug this in. Plus and minus, all right, so that's what's going on there. Now I'm going to put the multimeter here so you can see it. All right, so now we have a simple diode circuit, half-wave rectifier, but we're just going to run it DC right now just to see what it does, okay? So we're running it DC, so here we go. All right, so take a look here on the zoom camera here, and I'm going to turn this on. All right, so we've got nothing coming out of it. Now back to the bench camera here, we've got DC, nothing out of it, all right, which is what we should have. So now I'm going to slowly bring this up to like 0.5 volts. Very carefully. There we go, 0.2, 0.3, 0.4, 0.5. All right, so we got 0.5, you can see. Now, if you come over here and look at what's going on with this part of it, we've got that diode, right? And we're seeing a little bit out here. So we're seeing 100 millivolts or 0.1 volts, right? But not the 0.5. See, so we're forward biasing this diode, right? But it's not on yet, right? And that's why we're only seeing this 100 millivolts here. 100, you can see millivolts right there. And that's what we expect. So now as we turn this voltage up higher, 0.6, 0.7, and so forth, we're going to forward bias the silicon diode. And once that 1N4001 is forward biased, then we're going to start getting appreciable current, and it's going to stabilize at 0.7 volts. So watch this. So there's 0.5, 0.6, 0.7. There we are at 0.7. Now notice we're at 270 millivolts out. All right. So let's keep going. 0.8, 0.9. All right. So we got 1 volt here. 1 volt. And at 1 volt, now look, we've got 0.6 volts. So now the voltage on that diode is 0.6 volts. So we put in 1 volt over here on the left, and now this diode, we've got 0.6 volts. So what does that mean? The diode now is dropping 0.4 volts, right? So the diode is dropping 0.4 because we've got 0.6 right there. Okay, so let's keep going. Keep going, keep going, keep going. Let's put it up. 2 volts, all right? So we got 2 volts. So we got 2 volts right here on the left. We've got a diode, right? And now we're reading 1.5 volts here. So this diode is dropping 0.5 volts. So it's forward biased. It's dropping 0.5 volts. Remember, 0.7 is an average number when it's highly conducting. But it's not highly conducting, and the reason why is because we've got this 10K resistor here, right? So there's not a whole lot of current here, right? So if we do the math, what is 2 volts divided by 10K is 200 microamps. So we're only putting 200 microamps through here. And if we were to look at the chart, the data sheet for this diode, at 200 microamps, it'll say that the forward voltage is like 0.5, and it is. So right now we're putting 2 volts on the left side here. We're applying 2 volts. We're getting a 0.5 volt drop over the diode, and we're seeing 1.5 volts right here. All right. So now let's put this up higher. Let's put this up higher. Let's put it up to 5 volts. Let's put it up to the full 5 volts that we're talking about. There we go. We got 5 volts, and there we go. We got 4.46, right? So still, again, we've still got about 0.4, 0.5, 0.6, in this case, 0.5, 0.6 volts are dropping over that diode. We're starting to get a little bit of current, right? Because now we've got 5 volts divided by 10K. Right, which is 500 milliamps. So we got half of a milliamp, all right? Now, the interesting thing is, though, as we keep changing this current or putting a higher voltage in on the left, the voltage over the diode is not going to change much. It's going to sit and stay pretty stable, all right? So now, what we can do to show this is we can put the meter over the diode itself. We could do that, or we could switch the position of the diode and the resistor if we want to. So either way will work. So why don't we just, let's see if we can just put the meter right over the diode. All right, so put it right over the diode, and then of course the problem is the diode is 4 spaces and this thing is 3. So what I'm going to do is this. I'm going to put this up top there, and then I'm just going to run 2 wires to it. So this is a little bit long-winded of a way to get the signal, but it'll do. All right. So, and that's why when you design circuits, you design instrumentation into them to make measurements easy, because otherwise measurements are hard. Okay, good. Okay, so now what I'd like you to see is, so now look back at the power supply. We've got 5 volts. Now look here. We've got 0.5 volts. Let's call it 0.5, 0.6 dropping over the diode. Now, I'm going to drop the voltage of the whole system back down to 3 volts. And as I drop it back down to 3 volts, notice that not much is happening to the voltage over the diode. It's still staying at 0.5. That's pretty cool, right? So it's staying stable. There's 4 volts. It's going up a little. Here's 5 volts, going up a little bit more. Here's 6 volts, a little bit more. So, and now let's go course. We're going to go course adjustment, and here we go. So 6 volts, there's 7 volts, 8 volts, 9 volts, 10 volts, 11 volts, 12 volts, 13 volts, 15 volts, 16 volts, 17, 18, 19, 20 volts. So now I've got 20 volts on the left side of the circuit, but still, no matter what, all the way from 3 volts to 20 volts, the diode changed from about 0.3, 0.4 to 0.6 volts. So there you go. Now, how much current is flowing in the circuit? How much current is flowing in the circuit? Well, we've got, let's do the math. So we've got 20 volts coming in, and we're dropping 0.635. So let's do this exactly. So I've got it at 20.1 volts coming in. We're dropping 0.635 minus 0.635, right? Equals divided by our 10K resistor, right? And we've got 1.9465 milliamps, roughly 2 milliamps. We got 2 milliamps flowing in the circuit now, and that's it. So we got 2 milliamps, all right? So that is the diode, and that's the diode action. So it's not perfect. As the current through the diode changes, the voltage over the diode will change, right? But not a lot, all right? It's fairly stable over a large range. So we went all the way from 3 volts to 20 volts, and we can see we only changed a couple hundred millivolts there, and that's that kind of action that you want. But to get this thing going, you need to push enough current through it or have enough voltage to turn the thing on. That's why you need that 0.3, 0.2, 0.4 volts to turn the diode on and get it to start to conduct, right? And remember, that curve is exponential, so you gotta, it'll start conducting and then it'll just conduct a ton, all right? Once you get to like 0.6, 0.7 volts over it, then it's completely on. Okay, so that is that experiment right there. Now, let's go ahead and let's do another experiment. So now the experiment that we're going to do is this. So we've got 2 milliamps flowing through the circuit right now, right? So first I'm going to turn off the power supply, right? Just turn it off. I'm going to leave it at 20 volts. Matter of fact, I'm going to turn it all the way down from 20. Then I'm going to turn it off. Okay, now that it's off, now what I'm going to do is we've got this resistor, this 10K resistor right here. Instead of the 10K resistor, what I'm going to do is I'm going to put a 100 ohm resistor right after it. Okay, we're going to keep the meter measuring the voltage across the diode. Now what I'm going to do is I'm going to put an LED, a light emitting diode, to ground after that 100 ohm resistor, and show you something. As a matter of fact, let's do something else. What we really want here is a bidirectional LED. Let me see if I have one. Okay, because what I want to do is, if we have a bidirectional LED, no matter which way the current is flowing, we will turn on that LED. So that LED will turn on, all right? So let me try something real quick. And because I want to show you a cool experiment here. All right, so what I'm going to do is I'm going to turn the circuit back on. I'm going to put it on to about 5, let's do this. We'll put the LED right here to ground, okay? And let's turn this thing up to 5 volts. All right, so we're going to turn it up to 5 volts. Here we go. And we're at 5 volts and some change. There it is, 5.0 volts. And I'm turning the power on. Okay, did you see that LED turn on? Yeah, so there's green. Now let me flip it around. And that's not doing what I wanted it to do. What we're looking for is a bidirectional LED that'll turn on in both directions. And I have many of them here. I don't want to waste your time too much, but so I've got kind of a box here of them. And I want to find one that goes in both directions, but if I can't, what I'm going to do is I'll put 2 LEDs in opposite directions. So when we have current flowing one direction, we'll know it. Current flowing another direction, we'll know that. All right, so let's try this. So let me try this other LED here. We're just hunting for LEDs. Okay, that one's, okay, I think we're going to get lucky here. There it is. So it's red in this orientation, it's green in that orientation and red in this orientation. So this tells us which way the current is flowing, right? Okay, so either direction the current flows on this special LED, which is called a bicolor LED, super cool, right? So as a matter of fact, I think that's another one right there. I'm going to kind of keep these out. These are fun. No matter which way the current is flowing, this LED will turn on, all right? Now, this diode is the thing that's going to be blocking current and only allowing it to flow in one direction, right? It's only going to allow it to flow in one direction. So right now we've got 0.7 volts dropping over the diode, right? We've got a resistor there, and we've got this LED here, which is probably dropping about 3 volts. So we could sit here and figure out all the voltages and all the different what's going on, right? So we're putting in 5 volts. So we're putting in 5 volts. 0.738 volts is dropping over the diode, right? So if we take, 5 minus 0.738 volts, now we've got 4.262 volts, 4.262 volts. And that 4.262, where is that? That's right here, right there at the cathode at the resistor. So now we got 4.2 volts and some change, and then we got this LED. Now if we figure out what the voltage over the LED is, which I'll tell you right now, it's probably sitting around 3 volts or 3.2, then we can tell what the voltage over the resistor is, and we can figure out the current. So let's go ahead and let's just take the probes out of the multimeter for a second, and we're just going to measure. Let's see, can you still see that? Yeah. So let's just see what's happening over this LED right now. And the LED is 2.1. So we had 4.2 there, right, and some change. Now we got 2.1 here. So, right, so we got about 2.1 is dropping over that resistor right there. So we could compute the current, right? 2.1 volts. 2.1 volts divided by 100 ohms is 21 milliamps. So this just goes to show you need a lot of current to turn these LEDs on. They're current burners. Now, let's flip it around just for kicks here, all right? So we'll just leave the power on. We're only dealing with 20 milliamps, so it's not going to blow the world up. Okay, now it just turned red. And now the question is, what is the voltage dropping over the LED? It should be lower. Let's see. And it is a little bit, 1.9. So we had 4.2 before, now we got 1.9, right? Dropping over this. So we take our calculator, right? We'll do a 4.2 minus 1.9, right? And now we got 2.3. We'll divide 2.3 times divided by 100, right? And now we got 23 milliamperes is going through there. Okay, so that just is showing you what's going on and how we figure out the different values by knowing what the diode is dropping, then measuring what the LED is dropping. Now, because the LED and the diode are both diodes, we always know what they drop. So in general, that LED is going to drop about 1.9 volts, and the other one, when it's in green, like this, it's going to drop about 2.1 volts, right? It can drop a little bit more or a little bit less depending how much current we're punching through it. Same with the diode. But they're good starting points. So if you want to analyze a circuit, if everything's forward biased, if everything's on, just say, hey, it's a silicon diode. It's at about 0.7 volts. If it's an LED, it's at about, this particular LED is about at 2 volts. Okay, what are we ready to do right now? Okay, so now what we want to do is we are going to use, let's hook our meter back up here. Hook our meter back up. Okay, and so you can see everything again. All right, so we're just showing the voltage over the diode. All right, so I've got 5 volts, and when current is flowing in this direction, the LED is green and it's on. All right, so now what I'm going to do is I'm going to flip this around. I am going to flip the polarity around. All right, so I'm going to put negative here and I'm going to put positive here. Now, for $1 billion, will anybody tell me what's going to happen? All right, so if I flip it around, what's going to happen? So what does someone think? Nothing's going to happen. It's not going to turn on. All right, what's another thing that could happen? We think that the LED is going to be biased in the other direction, so it'll turn on red. That's another possibility. All right, well, let's just do it. Ready? Nothing happens. So nothing happens. Now, why does nothing happen? Well, the LED would be happy enough to turn on because it works in both directions. But this diode right here only gets forward biased in this direction. Positive on the left, negative on the right. We have to have a positive voltage, right? And we have to overcome its forward bias requirement, which is about 0.2, 0.3, 0.4 volts, and then at 0.7 it highly conducts. But current has to go in this direction. So no matter what we do, this is not going to work like this because that diode is blocking it, right? So it's blocking current in the wrong direction. Now this LED will operate in both directions. Okay, now, so here's something fun. So now let's try this. What if we remove the diode or short it with some wire? We could do that. Now we're just going to get a circuit that just has this LED and a resistor, and either way it'll turn on. So let's try that real quick. All right, so I got 5 volts, and I'm going to short it. All right, I'm going to short it live. All right, and I'm going to short right over. So we've got our meter plugged in right here, so I'm just going to pull the meter out, and then I'm going to short right there, right over it. Now be careful shorting things. All right, so now I've shorted it. So now I've taken the diode out of the circuit and just put wire there, and it's red as we expect. Now let's flip the polarity around. What should it be now? It will be green, right? Okay, that's good because that diode works in both directions. Okay, so now it's forward biased again. Now let's pull out the short. I'm going to pull the short out. What's going to happen? Boom. It stays on because it's forward biased. How cool is that? Now, here's something else interesting. What if I take another diode, all right, and I put it over this diode? All right, so I'm going to take another diode and I'm going to put it over this diode. This is an LED. Now this LED wants to be at 1 voltage. The other diode wants to be at a different voltage as well. All right, so now the circuit is still on. We've got this LED here, but no matter what, it does not turn on, right? So what is going on here? Well, the voltage drop over this diode right here is 0.7. And no matter what, it's not allowing this diode to turn on. The voltage drop is getting clamped over this, so this is never going to this 2.1 volts that it needs to turn that LED on, all right? So we pull it out, and there you go. Okay, so that's steering with that kind of circuit with one LED. Now let's go ahead and let's put our AC signal in. So I'm going to turn off the DC. All right, everything turns off. I'm going to remove our power here. All right, let's move this meter out of our way. Okay, so now what we're going to do now is we're going to take this same circuit. I'm going to kind of leave it how it is here. I'm going to leave it how it is, and let's do this for now. For now, I'm going to pull this LED out because I don't want to have that much of a load. And what I'm going to do is I'm going to put a 1K in the output here. I'm going to put a 1K in the output to ground. All right. All right, and so now what we're going to do, so I got a 1K, so let's zoom in so you can take a good look at that. Okay, so we've got our diode, we've got a 1K to ground, and now I'm going to put a sinusoidal signal in here, and I'm going to look at it out here. All right, so let's do that. Okay, so I'm going to get our signal generator. Here it is, and I'm going to hook this up. Here's ground. Good. Here is the signal itself. All right, so that's coming in there. Now let's get our oscilloscope. So I'm going to get channel 1 and fight with this cable. All right, so here's channel 1. All right, so here's channel 1 right there. It's on 1 times. Okay, so I'm going to hook this up to ground as well. And running out of places to hook things. So there we go. We'll put that right there. So hook this up to ground. And good enough. Come here. Everything is slippery. Okay, and then we'll put the probe right here. Let's put it up here so it sits in a nice place and doesn't pull this out. And you know, this is going to be a real frustrating thing for you, is when you start playing around and trying to connect everything. You got all these wires and they come all undone and they pull all the components. It's just horrible, but you'll get the hang of it. All right, now I'm going to take channel 2 here, and I'm going to put channel 2 on the output so we can see what the output is doing relative to the input. Okay, so there's channel 2, and I'm going to put that there. All right, so there is our circuit, nothing complicated. Okay, now let's go ahead and take a look on the camera at what we have going on here. So here's the signal generator, and we've seen this many times. And so what I'm going to do here is it's at 100 kilohertz, so I'm going to set it for 100 hertz, enter. And then what I'm going to do is I'm just going to create a sine wave here, and we need to offset this properly here. So we're going to have an amplitude of 2 volts peak to peak. Okay, that's good. All right, so that's going to give us 1 volt in each direction. So why don't we make that, let's make that 5 volts peak to peak. All right, we'll make it 5 volts peak to peak. All right, and then I'll just call that off as I manipulate it. So here's the oscilloscope. And so let's go start setting this up. So let's get channel 1 and channel 2 here so we can see them. So here's channel 1, here's channel 2. We'll turn off measurements. They're both, one of them is at 500 millivolts per division, the other one is at 50, 100, 200, all right, 500 millivolts per division. Let's put them both at 1 volt for now. 1 volt per division, and the sweep rate is at 2 microseconds, but we'll manipulate that as we turn this thing on. Okay, so we're ready to turn this on. We've got the oscilloscope. So what I'm going to do is I'm going to turn on the signal generator, and it's going to be at 100 hertz. So I'm just going to turn this thing on. And as a matter of fact, let's turn the amplitude down. I want to turn this down. So I'm going to turn this down to 100 millivolts. All right, here we go. So now I'm going to turn on the signal generator. All right, and so we've got to adjust it. So let me adjust the signal here, and we should start to see the signal. All right, there it is. And it's very little, so I'll amplify it for you a little bit so you can see it. All right, so the scale is 500 millivolts per division. You can see we've got this 100 millivolt peak-to-peak signal coming in on the left. All right, but we've got nothing coming out. See the blue? There's nothing. And the reason why is because we haven't forward biased this thing enough to turn it on. So now I'm going to start turning this voltage up of the overall sine wave. So 200 millivolts, 300 millivolts, 400, 500, 600, and 700, which we know is definitely enough to turn it on. All right. And now when we look at the blue signal, we're still not getting much out of here, right? So let's keep turning this thing on. So we're going to keep turning this thing up. All right. Okay, now we're starting to see something out of the blue signal there. So we're at 1 volt peak to peak. So remember, in the positive going transition, that's only 0.5 volts positive. In the negative going transition, it is negative 0.5. So it's not even the 0.7, which we know we want to turn this thing on. So we need to go all the way up to about 1.4 volts peak to peak, right? Which is right there. And I'm going to go to 1.5. I'm going to go to 2 volts peak to peak. All right, there we go. So now we're cooking. So check this out. This is awesome. So we've got 500 millivolts per division on the yellow signal, the input. We've got 500 millivolts on the blue signal. So they're at the same scale right now. So now I'm going to change the sweep rate. So now look what is happening here. So now this is really, really interesting. So in one case, right, we see the input. Here's the full input. But then we're only getting these half waves out. But at the same scale of 500 millivolts, we're not getting the whole thing out, right? So let's look here. Let's line this thing up. Matter of fact, let's line it up right here on the axis. And give me a moment here to kind of line these things up. Okay, now take a look at that. So there's no scaling. They're both at the same scale. And you can see what is going on here is very interesting. And what's going on is exactly what we expect. Because the conduction of the diode does not happen for a while, right? And then once it conducts, we basically pull off 0.7 volts of it, right? That gets removed. So then this entire transition up here, which is this is 1 volt going up and negative 1 volt, we basically only see about 0.3, 0.4 volts of our sine wave here because we had to wait to turn on the diode. And that turning on portion is right here. Let me scale this a little bit, actually. Let me scale a little bit, and let me pull this down, and let me pull this down so everything's lined up. So this is really cool right there. So now you can see our blue signal, which is our half wave rectified, it was turning on the diode, and finally, snap, the diode turns on, and then it starts tracking the signal, but we always lose that whatever it took to turn the thing on, and then again, then it turns off. And then so on and so forth it goes, right? So that is half wave rectification. So that's what a half wave rectified signal looks like, okay? So now, so you see it's not perfect. There's some distortion there. And now when we do the full wave rectified, you're going to see another kind of distortion, which is going to be interesting because what's going to happen is we're going to see these humps, but then we're going to see little gaps in them because the diodes have to, start to conduct and stop to conduct. So we're going to get these negatives flipped around and inverted, yes, but there's still going to be dead time inside of here because of the diode conduction. All right. So let's go ahead. Let's build our full wave rectifier now. So what I'm going to do is I'm going to turn this thing off. I'm going to turn off the signal generator. So we're going to lose our signal. All right. There it goes. All right. So now we're going to build our full wave rectifier. All right, with the diodes. All right, and I'm gonna put a little bit more light on here right now, just to help me as I do this, and then I'll move it away for the camera for you. Okay, so let's pull all this stuff away. And the first thing that we want to do when we're doing a bridge rectifier is we want to use diodes that are all the same if possible, or we want to use a bridge rectifier component. So see this right here, remember this, I told you about this. This is a bridge rectifier. You put the AC in the two middle, so there's the sinusoidal, and then you get plus and minus right out there. We could just put this right in here and just be done with this, all right? However, you know, I want to show you doing it with the diodes because it's painful, and then you'll never have to see it again, and then you can just use one of these bridge rectifiers, okay? But first, let's try and do it with the diodes, all right? So what I'm going to do is back on the screen here, let's put up what we're trying to mimic. Okay, so this is what we want to do. We want to basically draw this, build this circuit, okay, with the diodes in these directions right here. So I'm going to keep my eye on that. So you look at that also, and then I'm going to go back here to the bench and build this. Okay, so let's do that. All right, so the first thing we want is, let's see if we can get 4 diodes that are all the same here. So I got 1, I got 2, I got 3, I got 4. All right, and so I've got 4 of these diodes, these glass passivated 1N4 001. I'm going to make sure, I'm going to look at them real close here for a second here. Let me do that. So 1N4 001, yep. 1N4 001, yep. And 1N4 001, correct. And 1N4 001, good. All right, so I've got 4 of them. One thing I'm looking at when I looked at those is I wanted to make sure the glass isn't cracked or fractured or anything, right? So be careful of that. Okay, so now there's a lot of ways to do this. We could put the diodes nice and clean, right, in the board, or we can put them kind of more to reflect what the bridge rectifier looks like. Either way, first I'm going to bend these leads here. I'm going to bend these leads of each one of these, and I don't want these things sticking up too much. So what I'm going to do is I'm going to cut about half of that lead length off each one. All right, so I'm going to go over here, get our cutters, and a trick you want to do is hold on to everything when you make this cut, right? So nothing flips off into your eye. I'm wearing glasses right now, and these are magnifying glasses, and just to help see. So I have 20/20 vision, but you know, when you're doing electronics, you'll strain your eyes, and so it doesn't hurt to wear magnifying glasses, and you can get them on Amazon. You can get you know 1.25 or 1.75 or 2 or 3 times magnification. I think these are like 2.5, and that way everything's just closer and easier to see, and you don't strain your eyes. Okay. Okay, now as I cut these also, these are pretty thick wires. You can hear them getting cut. They're pretty blunt, right? Another little trick I want to show you is after you cut these, so see this right here? These are diamond files, So they file anything. They're very hard, right? Diamond is one of the hardest substances known to man. It's not the hardest anymore. And what you might do is just, you could file a little bit off these things. Now, be careful though, because I'm putting metal shavings all over everything here, which you don't want to do. So if you file this, do them someplace else, clean them off with alcohol, but that way when you try and push them in this board, you don't damage these little connectors, all right? So anyway, that's one thing. Now, as I cut them, I kind of cut them at an angle so they're not too blunt. Okay, so with these diodes, the black is the cathode. All right, so I'm just going to look. I'm looking at the circuit that I want to build here. All right, and let's see. The AC. All right, so what I'm going to do is I'm going to kind of draw. I'm going to kind of make it just like it looks. So here we go. So I'm going to do this kind of thing here. All right, so that one's going to go there, and then this one is going to go down like this. Okay, don't fight with me. There we go. All right, cool. I'm just making it, trying to make it just like the circuit. All right, and then now it's going to get kind of tricky here. The other two, this one's going to go here. We'll put it on this node here. Cool. All right, and then this one is going to go, this one should go up, if I recall. Yeah, when I was a little kid, I used to, like when I was 10 or 12 and did electronics, I memorized how to do these things because I didn't totally understand them. So I would memorize how to make a bridge rectifier because I didn't understand it. And but now, of course, I understand it, so I don't memorize it anymore. All right, so let's see. I think that's about, that kind of mimics what's up there. All right, and then the point is you put AC at the top and bottom. It doesn't matter what the orientation is because it's AC, right? So that's where our signal is going to come in. So what we're going to do is we will use, let's use longer wires this time. So the node is right here, and I'm going to put it right there. Okay, and let's get some more wires here. I'm just looking for some good wires. All right, this is too long. So here we go. This is better. Perfect. That one's nice. All right, here's one here. We'll put this one right there. Good. That one's nice. Okay, so that is where we're going to put our AC in, right? Or our our sinusoidal signal, not AC from the wall AC. Then the output is right there and right there. All right. So the output is, this one should be, yeah. So this one should be positive and this one should be negative. Okay. So now let's actually color code these for a little sanity. So I'm getting out some red wires right here, and I got some red ones. All right. So here's going to be our output right here. All righty. Cool, so there is positive out, okay? And then let's get a black one for our negative, all right? So I'm gonna get a black one here for our negative, all right? And now here is where the negative output is. So I'm gonna just put that right there. Now, what I could do is take that negative and put it straight to this ground right here, right? Because I know that's gonna be negative. Okay, so let's just do that, okay? So let's just do that, all right? Because we like having a ground reference. Okay, so I'm going to put that there, and I'm going to put this down here. Okay, now we're getting somewhere. Okay, let's back everything out here. Okay, all right, so we've got our bridge rectifier. We're going to put our signal in over here. We've got our positive output here. We got our negative output here, which we're going to throw to ground. We've got some probes here, some posts, so we can get signals in and out as usual. So let's put this, we'll put this one on one of our AC inputs. Let me find another post. They're all over the place. All right, put another one here. Good. And then here's our output. And I'm going to take our output, and on our output here again, I'm going to put a load. And why don't we put, let's put a 1K load. So brown, black, red we're looking for. Brown, black, red. Does anyone see the brown, black, red resistor? Here it is. All right, brown, black, red. Yep. Okay. So that's going to go to ground right here. All right. Now I'm doing this for you in real time and all that, but I would make this cleaner and clean this up if I was doing it for myself and flatten everything out. All right. So there's our circuit, and we're ready to go. So let's just do the exact same thing. All right. So let's just, with all haste, let's just turn this thing on. So what we're going to do is we're going to put the signal generator, and the signal generator is at 2 volts right now. So first thing I'm going to do is lower that back down to 0 volts. Or 100 millivolts. All right, it's at 100 hertz. We can put it at any frequency. That's not going to hurt us. So let's just put AC, the signal in here. Now, be careful. Notice I'm putting the signal in on these lines, but I'm not making the ground common with this ground. So it's completely separate. That's important. All right, now, and that is, where is my, oh, here we go. All right, so here's my oscilloscope here. All right. Okay, so, and we might have a little bit of a problem here because these grounds, but let's see. I can't remember if these are isolated or not. So I'm going to put this one here. So here's channel 1. All right, and then here's the output at channel 2. All right, and then I'm going to ground this. All right. And okay, so we've got our circuit, we've got our full wave rectifier, which we're hoping is going to be a full wave rectifier. All right, so let's give this a try. All right, so we're ready to go. And what I'm going to do now is, so take a look at the oscilloscope. So as you can see, we have nothing on there, right? We've got nothing on either wave. All right, so let's go ahead and let's turn on the signal generator. So the signal generator is on, and it's at 100 millivolts peak to peak. So you can see we got that signal on the input, right? And it's there. So let's go ahead and let's turn this up a little bit 200, 300, 400. All right, now it's stabilized. It's able to lock into it. And let's change the scale. We're at 500 millivolts, 500 millivolts. So let's make it a little smaller. So it scales it up a little bit bigger. There we go. All right, and now you see we don't have anything on the blue signal. And the reason why is we've got this big bridge rectifier here with these 0.7 volt drops everywhere, right? And we're only putting in 400 millivolts peak to peak or 200 millivolts in either direction. And right now we need to make sure that it exceeds, 0.5 or 0.6. So let's keep turning this up. So there's 400 millivolts, 500 millivolts, 600 millivolts, 700 millivolts, 800 millivolts, 900 millivolts. All right, now let me change the scales here. Okay, and now I'm at 2 volts right now. And we're not seeing the negative going wave here. We're not seeing the negative going wave right here. Okay, so we have the circuit set up. And so on channel 1, we can see on the oscilloscope. Let's go take a look at the oscilloscope. You can see the input signal. All right, and what's happened here is I've done an edit, and I found a problem, not with our rectifier, but with our instrumentation, which is a subtle problem that that happens. And if you haven't played with it in a while, you forget about it, and you're like, what is going on? But I want to show it to you so you can kind of see this problem. All right, so we've got channel 1 looking at the input. As you can see, we've got our sine wave, and it's about 6 volts peak to peak, and it's at 100 hertz. All right, now I'm going to now add channel 2 to look at the output of the full wave rectifier. So we've got our full wave rectifier. We've got our little load here of a 10K resistor. And why don't I zoom in just a little bit for you? Okay. And I've got channel 2 here of the oscilloscope, the blue channel. All right, so I'm going to go ahead, and the first thing I'm going to do is I'm going to connect the ground. All right, now, as I connect this ground, I want you to look at the oscilloscope. So take a look at the oscilloscope right now. So look at the yellow trace. It's this full sine wave. Now watch as I add the ground line. Look at what happened. I'm just adding the ground line. Now take a look at the circuit here. So I've just added the ground. And now the yellow trace is missing the bottom half. All right, now watch as I add the actual probe for the blue trace to the output. So now this is really interesting. So if you take a look here, what's happened, here's the input, right? There's our AC input, and somehow it's got clipped. And then here's our output, and we're getting half of the wave, so we're getting half wave rectification. It's getting clipped voltage-wise, as we would expect, but where's the other part? Where's the other half wave that should be reflected? And then also, what is going on with the top waveform, right? Well, let me tell you, this is what's going on, and this is a subtle problem. And it creeps up on you if you're not paying attention. So what's happening is this. So let me undo these 2 leads right here. All right. So we've got this signal generator coming here on this red and this black, right? So there's a signal generator coming in on the red and the black. And then we've got this oscilloscope here. And the oscilloscope has a ground line, right? And so the ground line, whatever we connect all these grounds to, they have to be the same voltage. In other words, if this black ground right here is at 0 volts, this needs to be at 0 volts. It can't be at a different voltage, a different potential, right? Because the problem is that this is a reference, and what happens is once we connect this other reference from the other lead, so for example, remember, voltage is all relative. So if this was at 1,000 volts right here, all right, and it was isolated from this black lead, and this black lead was at 2 volts, and I connect those 2 together, that's okay, because there's no way for current to flow back here yet. So what happens is this becomes a ground at 2 volts, this becomes a ground at 1,000 volts. That would be okay because there's no reference. It doesn't know there's 1,000 volts, all right? So you can have a different references to each other. That's okay. But the problem is that the moment that we connect the other end of the lead from the oscilloscope, right? Now the oscilloscope is expecting this to be ground. But if this is changing, like, if it's changing, right? So if this black one is changing or this red one is changing, then that ground is not staying stable. This ground, this black ground right here on the oscilloscope is actually to ground. It's actually to 0 volts. It's to, earth ground. So it expects that to be 0 volts. The ground from the signal generator is also because we're both connected to the AC lines of the house, this is actually at ground 0 also. So the red goes above 0 volts and then below 0 volts. All right, so we can connect this one and this one and still be okay. All right, and look back at the waveform on the oscilloscope, and you can see the yellow waveform, which is what we would expect. The problem becomes the moment that we connect the other line here. So we've got this bridge rectifier where we're creating this virtual ground right here that we're creating. And when we connect this here, what's happening is there's a connection between these two grounds. So this ground here, this ground line to this oscilloscope, this ground and this ground, these are all connected together. So now the problem is the moment that that I connect this to this line right here, we're trying to force two different voltages on the same pin, and it's not going to work on the same signals. It's not going to work. We need to isolate this. So now let me show you what happens. So the second I connect this ground here, now go look at the oscilloscope, see we lost it. I disconnect it, connect it. Now, what if I put this right here? What if we put it onto this input? Notice nothing happens to the yellow signal. Go look at the yellow signal and see it's okay. So that's okay, all right? And then now when we take the output, if we were to take the output on the output here, oops, we just lost focus. If we were to take the output using this as a ground, now take a look at what we have. So the input signal is okay, but then the output signal is not true. And the reason why is because this negative here is canceling out and we're not seeing it. So basically, the problem is with the test equipment, we need isolated test equipment so that they can have their own independent grounds, and we don't because they're both connected to the mains in the same ground. All right, so the problem is that we can't read the output voltage. We can't read the output voltage properly with this bridge rectifier from this virtual ground that it creates unless we have some kind of separate piece of equipment. So what we're going to do is we're going to get a separate piece of equipment. All right, now, so this is a common problem, and I want you to be aware of this. And this is what I was talking about when we're doing AC circuits. And if you have an AC circuit and you touch, one of these grounds of a piece of equipment and you accidentally touch it to hot instead of neutral, right, you're going to short something out, right? So you got to be very careful. And that's why it's good to use isolated equipment. So ideally, what we would like is to use isolated equipment where the oscilloscope, where the signal generator and the oscilloscope are both isolated from each other so that their grounds are not the same ground unless we tie them together and make them the same ground. That's what you want ideally, and I do not have that in this lab. All right, now, but what I do have that's isolated is this. So let me show you this really cool piece of equipment. And let's see here. This is, if I can get it in here, let me zoom out first. We'll zoom out a bit, okay. And let me just move this for a second here. All right, so this is let me zoom out some more. And you're seeing the camera there. All right, this is a portable oscilloscope. How cool is that? This is a portable oscilloscope. Very, very cool device. So this is completely isolated. All right, so with this, we're going to be able to read the values on this output of this full bridge rectifier without commenting the grounds, because this thing is completely floating because it's battery operated. All right, so I'm going to turn this on. I'm going to get the display working. All right, so let's move this over here again. So this thing is still on, right? So it's still on, it's still working. All right, so now what I'm going to do is I'm going to turn on the oscilloscope here. What we have now is I've actually got the signal coming out of the bridge rectifier, and we can see it here on our portable oscilloscope. All right. So now on this oscilloscope, this is the output signal, right? And on the other fixed desktop oscilloscope, we have the input, which is the full sine wave, right? So the full sine wave's there. I'm looking at it, and now this is the actual output, all right? And so what is interesting to notice here is that So if we look here, here's the output, and then the bottom waveform is just the zoomed version of it, so it has a zoom feature. So now you can see, so here's one wave, and then here is the other wave, and you can see it's inverted and reflected, so we're getting full wave rectification. Now, remember, what are these little dead zones here? These dead zones between each are where those diodes are getting pushed into forward conduction, right? So if you look here, and we were to kind of draw a vertical line here, this is where that diode is off, and then it's off, 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 and finally it snaps on, and then that forward drop of about 0.6, 0.7 volts happens, and then we get conduction. So we can see we're getting the entire waveform out of the device. All right, and again, the waveform that's going into the device, into the full wave bridge rectifier, is over here. So there it is right there. So that's the full wave. And so what's happening is we're taking all these negative halves and we're flipping them up, right? But because of the diode conduction, we're seeing just a portion of these waves not to get through the system because they've got to push those diodes into forward conduction. So let's take a look again one more time at the waveform. Okay, so here's our output waveform one more time. And so this is exactly what we want. So there's really nothing we can do about these little dead bands right here. And here's the magnify. There's nothing we can do about that. The only thing we can do about that is use diodes that have faster conduction, all right, or have a lower, a lower forward voltage drop. So we could use Schottky diodes in this case. We could use Schottky diodes, and then that would cause conduction to happen faster, and then these would close up, and we would just get that waveform looking like what we expect. Now, let me change the frequency just a little bit so we can kind of see that happen. We haven't done that. So there's 200. 400, 500, there's a kilohertz. All right, and then let me back off with this device so we can adjust this. All right, and now we can kind of see it. So now we're kind of seeing something that, let me take off this zoom feature, if I can figure out how to take off this zoom feature, which I believe is right here. Yeah, we'll take off this magnification. There we go. All right, and so now you can look at it, all right, and they're getting very, very tight. So now here's the interesting thing to pay attention to, though. This is completely been rectified. See, here's ground right here. See, there's the ground line right there. So this is all positive going. Everything's positive going. And ideally, you want this thing to hit here and go right straight back up, but there's that point where we have to go in and out of conduction on those diodes, okay? So now there's a full wave rectifier. So now let's go back to the bench. So we're back here on the bench, and the load that we have on this thing, what is the load that we have on this? If we zoom in there, here's our load, and our load is a 10K resistor, a little 10K resistor. So why don't let's increase that to 1K, all right, actually decrease it, which is going to increase the load itself, how much current is going to go through this. So let me find a 1K here. Okay, brown, black, red, so I've got that. So what I'm going to do is I'm just going to pull this load out while this thing is running. All right, and we've got 6 volts peak to peak going through here. So we keep that in mind. So, all right, now we go to a 1K. All right, and then as we go to 1K, let's go take a look at our waveform here again. So if you take a look, there's our waveform again. And so it looks the same. Now let me pull the 1K out as we're doing this. I'm going to pull the 1K out as I'm talking. So right now it's in, and now I'm going to pull it out. Now there's no load on this right now. So no load, all right? And because there's no load, this is what happens. These diodes, there's no current flow. All right, so let's put the 10K load back in. All right, so we've got the 10K load, and then what I'm going to do is I am going to take this 1K load, and I'm going to put it here. So this will be interesting. So let me show you what I'm going to do. I'm going to just keep talking here for a second, and then I'm going to show you something. Okay. All right. So let's come back to the design here. So here's our 10K load, and then here's our 1K. And then what I'm going to do is I'm going to put a switch. I'm going to put a little switch right here so I can switch the load in and out. All right, so in one case we'll just have 10K, and then in the other case we will have 10K in parallel with 1K, which will be a little less than the 1K. All right, so if you do 10 in parallel with 1K, that's 10 times 1 over 10 plus 1, so it's 10 elevenths. All right, so So let's do that exactly. All right. So 10x3 times 1x3 equals divided by 10x3 plus 1x3 equals 900. All right, so 900 ohms. So it's practically just 1K. Okay, so now let's connect. We're just making this little ad hoc circuit real quick to try this feature out. So, and this is what we got to do sometimes. Just got to build things and play around with them. All right, bear with me here. Okay. Okay, so now, all right, so that's what we want. So now we've got a switch, and as I push this switch, we're going to go from 10K. We're going to go from 10K to roughly 900 ohms, like 1K. All right. So now take a look at the oscilloscope again. So we've got our fully rectified waveform. Right now it's at 10K as the load. So we've got very little current in the system, very little current. So now we're going to drive more current through the system by putting that 1K load, that smaller load. Ready? All right. So I'm going to press the button. Oh, look what happens. See, isn't that interesting? So we lower the size of these waveforms because we're pulling more current. And really what's happening is that signal generator, the signal generator is we're putting too much of a load on it. The signal generator, remember, cannot take a very large load. All right, so we're actually causing it a problem because it cannot drive this. So we really need a power source and not a signal generator. All right, so that's fun. Let's do that. All right, and then now let's go ahead and let's put a 100 ohm load in there, all right, 100. So now when we connect the 100 via the switch, we are going to draw a lot of current, and we're probably going to cause the waveform to really die. All right, so here we go. Okay, so I've got the 100 in there. Take a look. Okay, and here we go. We're going to press the button. So we got 10K right now. When I press it, we're going to have 10K in parallel with 100, which I'll tell you is about 100. Here we go. And look at that. Whoa, we just kill it. So this is not the behavior we really want, right? So what's happening is the signal generator just can't drive the circuit enough, but we don't have the capacitor in the circuit. Remember the capacitor, the filtering capacitor inside of the circuit. We don't have that to smooth this out. So we're getting these waves like this, and what we really want is we just want something to sit across the top there. All right. So even with the 100 ohm, let's go back to the circuit. All right, so let's go back to the circuit here, and let's put a large capacitor across the output to smooth this out. All right, and then look at it with the oscilloscope. But I'm going to turn it off right now. I'm going to turn it off. All right, so that's off. So now let's get our large capacitor. All right, and by large I do mean large. So let's see what I got here that we can use. So I've got a 10 volt 2200 microfarad, and I've got a 4700 microfarad 16 volt. Okay, so when you're doing things with capacitors, they have a voltage on them, which is the voltage that they'll charge up to, the maximum voltage. And this one is 16 volts. Now, we know we're putting right here 6 volts peak to peak, but we could put more, 10 volts, 15 volts, whatever. And whatever capacitor you pick, try and pick one that's at least twice as much what you think the maximum voltage is going to be, because due to temperature variation, this and that, and spikes, you may overvoltage the capacitor. So I always at least go 2 times as much, and sometimes 3 times as much. All right, so this is electrolytic, so it's got a polarity. And there's the minus sign, so that's going to go to ground, and then the other side goes to positive. So the output is here at this red, at this point right here, right? So let's go ahead, and we're going to put this capacitor in here carefully to ground, all right? And because it's so big, we're going to kind of jiggle it in there, all right? It's jiggled, all right? So it's in there. We got our switch there still. Okay, so everything is good to go. So let's go ahead and turn everything back on. Okay, so the system's ready, so I'm going to turn the signal generator back on with a 6 volts peak to peak. Okay, so we're going to make it actually 10 volts, so I'm setting it to 10 volts. It's 10 volts right now, all right, and now I'm going to turn it on. All right, so we'll turn the system on. All right, nothing exploded. That's good. So we've got 10 volts, so that means we've got a peak value of 5 volts and negative 5 volts in both directions. So our waveform is 5 volts. After it's rectified, we should just get all 5 volt lobes out of it, right? And that's what we're looking for, minus the forward drops of these diodes. Okay, so we're not going to get 5 volts out. We're going to get less than 5 volts. We're going to get 2 diode drops less on that output. All right, so let's go over and take a look at our output. Here's the output, and here's ground of channel 1. So this is the output of the fully rectified wave. So there's ground, and then here's the waveform. But look at that, it's a straight flat line. So what is going on? Is this what we expect? Yeah, it's DC. So that capacitor is charging up every time. And as it charges up, it sits at that voltage. All right, so we're sitting here at this voltage, and we're at 1 volt per division. So it's 1, 2, 3, 3.5. And if we turn measurements on, and we'll turn measurements all on here if I dare, all right, and let's see here. So Vmax is 3.56 volts, okay, 3.56 volts. All right, let me turn measurements off. All right, I rarely use this oscilloscope. I use it when I have to do something like this or take it to another location. So, you forget how these things work. So anyway, so we've got DC. So now let's turn our load on. All right, so let's go back to the circuit board here, to the solderless circuit board. So remember, we've got a 10K load right now, and then when I press this button, we're going to switch in this 100 ohm load. So we're going to get ultimately about a 100 ohm load when we put the 10K and 100 ohm in parallel. All right, so what I want to do is I'm going to press it, but I want you to watch the DC. All right, so let's go back now. Watch this DC. And in fact, let's turn on that measurement again. All right, and we'll turn on measurement. And so you can see right here, just look at that Vmax. That's what we're looking for, is 3.56. 3.56. All right, so here we go. We're going to press a button, and what do we think is going to happen? It's going to lower, right? Let's see. And there it goes. It's lowering. So because we're drawing a lot of current, all right, and then two things is happening here. So one, we're drawing current from this signal generator that just can't do it. And two, we're simply drawing a lot of current from that capacitor, so we're getting this lower average voltage here. So now instead of the 10K, let's put back the 1K, because we're drawing too much current out of the system. All right, so all I'm going to do, come back here to the circuit. All right, is I'm just going to remove the 100 ohm, and I'm going to put the 1K back in. All right, so I've got the 1K, so there we go. All right, so now we're gonna, when we push this button, we're gonna put more of a load, but we're gonna put 10 times more load, a 1K instead of a 10K, but not 100 ohms. That was just too much, right? Okay, so now let's go back to our oscilloscope here. We see we're back at the 3.5 volts for the Vmax, and I'm getting ready to press the button here. So watch what happens. So I'm pressing the button. And there it goes. It drops down, but not too much. So see what's happening here? We're getting DC out of this thing, and we're getting regulation. Now, so now how much regulation are we getting? So when we've got a 10K load, so we've got basically 3.5 volts out divided by 10K. That's the current that we're pulling. Then when we put the 1K load, which is 10 times more load, right, the voltage drops down to roughly 3. So we lose half a volt, basically, half a volt and some change. All right, and so it can't maintain regulation and keep it at the 3.5 volts the entire time, but it's not bad. So if we didn't put that big of a load, we would be okay. So what if we put another 10K instead of the 1K? All right, so 10K in parallel with 10K, the rule is when two resistors of the same value are in parallel, the resistance is just 1/2, all right? And you could think of that because you have current now that's going to equally go between two branches. So anyway, if you do the voltage divider product over the sum, you'll get half. So I've got 10K and 10K in parallel, all right? So now let's take a look at the oscilloscope again. So now we're back to our 3.56. So when I press this, instead of 10K, I'm going to have a 5K load. So I'm going to have twice the amount of current, roughly. And let's see what the voltage drops down to. So it's 3.56. Here we go. And I pressed it. And there it is. It dropped only to 3.4. I'll let it back up. All right. And see it's slowly charging back up. 3.5, 3.53. I'll press it again, and it drops down. Very little. So as long as the load does not change too much, right? We don't pull too much current. We're maintaining some form of regulation here, and we're not causing too much grief to the signal generator. All right, so a couple things we need to do. One, if we want to turn this into more of a power supply, right, we're going to have to power it obviously from not a signal generator, right? So we can't power it from a signal generator. And the other thing is we're going to, so we'll need a transformer over here on the left side. So remember we talked about that. So we need some DC in here, and so we would use something like this, one of these transformers, right? A wall wart, and then this is going to put DC out. Now inside of here is just a transformer and a capacitor. If you're lucky, many times it's just a transformer and a bridge rectifier, so you get DC out and maybe a small capacitor. So this is not regulated. So basically then we would put this is what would feed the circuit, and now we would have a lot of drive. So the transformer has a lot of drive and a lot of current. Now, when we put a load on it, we're not going to see that voltage dip down. We're not going to do this right now because we're going to continue on playing with diodes in other ways, but we're actually going to come back to this and talk about power supplies more. We're going to rebuild this same circuit, and then we're going to use the wall wart, something just like this, to power it. All right. So anyway, but now, an interesting thing is this capacitor is now charged. So if I were to pull this capacitor out while the circuit is on, it's actually charged, all right? So let's actually do that. So I'm going to pull, and as a matter of fact, on the oscilloscope, so if you go look at the oscilloscope, we've got our DC there because we've got our capacitor in the circuit. Now I'm going to press the button again, and you can see it ever so slightly drops down. You can barely even see it. I'm pressing it and letting it go. You can barely see it. It's just so little. So it's regulating pretty good with that other 10K resistor coming in and out of the circuit. All right. But the point is, I'm going to pull this capacitor out. And now what is going to happen? All right. And you don't want to do this with active circuits, but we're going to do it anyway. So now look at the oscilloscope. All right. There's our DC line. So ready? I'm going to pull this out. And what's going to happen? We go back to our full wave rectified signal because now we don't have this capacitor to smooth it out. So it's gone, right? Now, what's interesting is that capacitor has still got a charge on it, all right? So what I'd like to do now is let's go back here to this bench, and very carefully, I don't want to touch it. It's only got 5 volts on it, all right? But let's see if we can get the voltage off of it. So I'm going to get a meter here, all right? I'm going to get the meter, and I'm going to put the meter on voltage. All right, I'm going to zoom out a little bit here for you. So let me zoom out so you can kind of see what's going on. All right, cool. Okay, so there's our meter. Can you see that? Yeah. All right, so I'm going to be real careful because remember, I'm resistant. So I'm like, a meg or something like that, a megohm. So I don't want to touch this with my fingers because I'll discharge it. All right, and so I'm just going to touch the probes here, and we're going to try and get a reading off of this capacitor here without discharging it. All right, 3.6 volts. Flip it around to the right polarity here. All right. Nothing wants to work in front of the camera. There we go, 3.6 volts. So it's actually charged to exactly what it should be. Remember, it was at 3.6 volts on the oscilloscope. Because the 2 diode drops, that's the highest the voltage got up to. So that capacitor is actually charged right now. So if I were to touch this to metal, an enormous amount of current would come out of it, all right? So what I want to show you is what not to do. So don't touch that on metal. So this is anti-static foam here, anti-static foam. And all that means is it's conductive. And it's very slightly conductive. So if you put something that's charged into it, right, the current will discharge, all right? So it won't hold static electricity. And so let me put this on resistance really quick. And I'm actually going to measure, that's about 1 inch. Look at the meter, I'm measuring about 1 inch, and look what it says, 3.82 kiloohms. So this is actually resistance. So this is, if I put this in here, it's going to discharge. So it's 3.82 kiloohms over 1 inch. These are about, the leads are about 1/2 inch apart. So it's going to be about maybe 2K, all right? So I put it in there, and nothing happens. It actually just discharged. It's discharged by now through that 2K, and we could figure out what the RC time constant is, right? It's just R times C. That's the time constant, right? So let's just, for fun, What is the capacitor? It's 4,700 microfarads times, we figured out maybe 2K of resistance. The time constant is 9.4 seconds. 9.4 seconds. Let's do that again. 4,700 microfarads times R, which is 2K. All right. Yeah, 9.4. So this will be discharged in like, a minute. So it's not very quick. So it's actually still discharging. I bet you if we pulled it off here, all right, I bet you if we pulled it off, and I'm just going to hold one finger on one of these leads here and hold the other one on the other one. Look at that. There's still 1.4 volts on it, right? It's been discharging. So we'll just let that keep discharging, all right? Okay, so that's that. So now what I'd like to do is let's do another experiment with our diodes here, okay? So the next one let's do is let's take a look at our list of things here we wanted to kind of do here. So why don't we try doing something with the Zener diodes. So let's build a circuit that's basically a Zener regulator, all right? And let's take a look again. So let's go back to the big screen. Let's go back to the big drawing board there and draw real quick what we're going to do. Let's take a look at our list of things here we wanted to kind of do here. So why don't we try doing something with the Zener diodes. So let's build a circuit that's basically a Zener regulator, all right? And let's take a look again. So let's go back to the big screen. Let's go back to the big drawing board there and draw real quick what we're going to do. Okay, so all we're going to do is remember the Zener regulator circuit we talked about, regulator. All right, so we're going to have a V in here. We're going to have a resistor here, and then an output here, and then we're going to put a Zener right here, okay, like this, to ground, and then this is R, and then this is V in, and then this is V out, and then we're going to have a load here, which we just connect to V out, like this, to ground, and this is our load, and this is our Zener, Zener 1. And then remember, whatever the voltage, the Zener voltage is, whether it's 5 volts or 3.9 volts or whatever, let's say that it's a 5.1 volt Zener, that is what voltage is going to be here, as long as we maintain enough current to maintain the Zener regulation. So we can call that like, I Zener. And then the remaining current will go through here, and we could call this current right here, we could call this IL going through this branch. So anyway, this is the circuit that we're going to build right now, and we'll put a couple different Zeners and see if that maintains that regulation. So let's go do that right now. Okay, so we're back here on the bench, and what we're going to do is we're going to build the circuit that we just looked at. So I've got all my components and whatnot as usual. So let me go ahead and let me zoom in here so you can see what I'm doing. All right, so the first thing is what we're going to do is we're going to find our Zener. And here is the 1N751. Let me show you the zoomed camera. So here's the 1N751, and let me rotate this around. There it is, 1N751. All right, and this is a 5.1 volt Zener. Okay, and remember there's the cathode right there, the line. Okay, all right, so we come back here and let's get a resistor that we're going to use. So we're going to use this red, brown. So that's a 220 ohms. This is going to set up our maximum current. So this is our current limiter. So we're going to put this right here. Matter of fact, let's put it right here. Okay, so there's our resistor. And then to ground, we're going to put our Zener. But we got to be careful of the orientation that we put the Zener. We put the cathode up. All right, so the cathode's going to go up towards this node right here. All right, so that's what we want right there. We want that situation. All right, then we're going to put our input in, and let's just put a wire here to kind of separate these things a little bit so they're clean. All right, and then the output is right there, so we'll put another wire. There's our output. Okay, So this is what we have now, right? And then now, so that's it. So this will create a Zener regulator. Now, we've got our output right here. So let's start off with, we're going to put no load on here. We're just going to have this resistor and the Zener. And then let's put some probes here so we can kind of measure things. So we'll put that one there, and then we'll put another one on the input. And in this case, we are going to not use the oscilloscope. We're going to use a meter to kind of see what's going on here. All right. And so we got those there. And so now what we need is we need an input here. We need a power input. So we're not going to use the signal generator. We're going to use a DC supply. So I'm going to go over here to my DC supply, and I'm going to bring it over. All right, so got the DC supply, and I'm going to connect the two leads, ground and +5. So there they are. We got the ground and the +5 lead. And I'm going to set the DC supply right now. I'm going to set it for, as a matter of fact, for fun, let's put it all the way down to 0. So it's all the way down to 0. We don't need to look at that this time. Let's get a meter out. So we're going to get a meter out. All right, and we're going to take the meter, and I'll tell you what the, as a matter, you know what, let's go ahead, let's do 2 meters. Let's do 2 meters. Let's do 2 meters for fun here. Let's see what we got here that we can fit on the screen good. How about this one? All right, let's do 2 meters. All right, so what we're going to do is 1 meter on the left is going to show the voltage coming in, and 1 meter on the right is going to show the voltage out. All right, okay, so let me get this all situated for you here. All right, that's good. All right, so we got 1 meter right here. Okay, we got a lot of room. We got 1 meter right there, and we're gonna have another meter right here. All right, so the one on the left, put that at 40 volts. The one on the left will be the voltage in. The one on the right will be the voltage out. Okay, so now what we need is we need a couple probes, connectors to get these voltages, right? And again, this is all about fabrication. So we're gonna connect these clips here. All right, so I'll connect this clip here to this output. All right, that'll be our output voltage, and then I'll connect this clip here, and this will be our input voltage, and then we need a couple ground wires to ground these so that we have them grounded for reference. All right, so here's this one right here. And again, I could build these things and just video it, right? But I'd like you to see the process, so you see me make mistakes. You see my the thinking process, the thought process, and all that. It's important because when you start doing this, you're gonna, just kind of be lost at first when you start building circuits because you just haven't done it. And so it's really good to see someone make a lot of mistakes in front of you, so you can kind of see what not to do also. All right, good. So we have everything hooked up. So we got our power, everything's grounded. So now all I'm going to do is connect the left meter to this one and the right meter to this one in voltage mode here. So let me get these cables. So here they go. And I'm connecting this up. Good to go. All right, and then the right meter, which is the output. And there's never enough room on your desk, so that's one thing. Get a really big area to work on or you're going to get real frustrated. I know I do. All right, so there's our meters. Okay, and let me zoom in just a teeny tiny bit more. All right, so everything's good. Don't worry that the meters are showing some random numbers on them right now. It's just noise. Okay, so now the system is off. I'm going to turn it on, and the Zener should start regulating and forcing this to be 5.1 volts at some point. So I'm going to turn on the DC power supply. The DC power supply is on, and right now I'm going to put it up to 3 volts. All right, so it's at 3 volts, and okay, the first thing that we notice is we see nothing on the input here. So let's see what's happening here. We got a good connection here. We've got this on voltage. Oh, we are not seeing it. So we're seeing, so there's 3 volts on the output, which is what should happen, but we're not seeing the input. So it's possible these leads are bad. So let me fix this. Okay, so there was actually something wrong with the leads. They weren't engaging this meter all the way, so I had to change the leads out. So now these leads are good, and we've got a good connection right there. So now we're seeing the input and output. All right, so what is going on here? So I've got the power supply set at 3 volts. We're seeing 3 volts in and 3 volts out. And the reason why is because we haven't reached the minimum Zener regulation. So we're seeing no regulation. We're just seeing the input and output match each other. All right, so let's bring it up. 4 volts. There's 4 volts. All right. And let's bring it up to 5 volts. All right, 5 volts, give it a second. Okay, so now we see we've got 5 volts on the input, but on the output we've got 4.5. All right, so now we're starting to see this Zener regulation occur. Now let's put this up to 6 volts. So 6 volts. So we've got 6 volts on the input, as you see, and then now we've got this 4.7. All right, now let's put it up higher. 7 volts, 8 volts, 9 volts. Drop it back down to 9 volts. Okay, 9 volts. And now you can see we've got almost a perfect 5 volts out of here. So again, depending on how much current, remember we looked at what was called the Zener current, right, and the Zener resistance. It's not exactly 5.1 volts, right, is the Zener voltage. That's only at one specific current, right, and until we hit that current, we're not going to see that. But we're going around that range. So here's the point. So right now, with no load on this, as we vary the voltage from, so let's drop this back down. So here is, there's 6 volts. So 6 volts, we've got about 4.8 volts out of our regulator. At 6 volts, we got 4.8. Now we go all the way up to 10 volts and some change, 10.5, and look, we got 5 volts out. So this is staying very close to 5 volts, right? Which is exactly what we want. Let's bring it a little bit higher. There's 12 volts, 13 volts, 14 volts, and again, it's staying right at 5 volts, and you can see it's about to hit 5.1 volts, right? So we need to get enough Zener current for it to hit that 5.1 sweet spot if we want it to, but even at lower voltages and lower currents, it's about 4.6, 4.8 volts and so forth. All right, now, so that's showing you the line regulation, right? So as we change the power coming into the system, we see that the output voltage is varying, but not a whole lot. Now let's play with the load regulation, all right? So right now, let's just set this at a voltage that we might get out of a wall wart. All right, so we'll set it at about 10. Say if you had a 9 volt wall wart, right, it'd be about 9, 10, 11, 12 volts actually would come out of it unloaded. So you can see we've got 5 volts out of our regulator. Okay, this is cool. So now all I'm going to do is I'm going to put a load in here that we can switch in and switch out. So I'm just going to move these down and give myself some room. I'm going to turn the power off because we don't want to damage anything. All right, so now let's go ahead and let's find our load. So this time, let's do something a little bit more interesting. So let's take the output. Let's take the output here, so you can see this. And let me zoom in while I do this work. All right, so what we're going to do is we're going to take the output here. And the output is right here. And what I'm going to do is I'm going to switch in 2 different values. So I'm going to switch in a 1K and a 10K and where's our 100? There's 1K, there's 10K, and let's see, where'd our 100 go? Where'd our 100 ohm go? There it is. All right, so we're going to have 3 different loads here. So we're going to have 3 different loads, and we're going to switch them in based on some little buttons, all right? And then we'll look at what the load regulation is as we do that, all right? So that'll be cool. So let's just pop this out for now so I can kind of see what I'm doing here. All right, so we're just popping that out. And in fact, what we're going to do is we're just going to move it. I'm just going to move it right here. So we will put this voltage meter right there on that node, all right, when we get to that. So here's the output right here on this wire right here, all right? So here's the output right here. So now what we're going to do is let's get 3 different loads going to ground, all right? So first let's get our largest value, which will be our smallest load, All right, so we'll get our largest value, which will be our smallest load, and that's going to be the 10K. So there's the 10K resistor. And then let's take, here's our 1K resistor, and we'll put the 1K resistor over here, give ourselves some room to work. Okay, there's our 1K resistor. All right, and then here is our 100 ohm resistor, the smallest resistor but the largest load, right? Okay, so we got all that set up. Then what we're going to do is we're going to see if we can we find 3 of these little push button switches, which I have many, many of them. Okay, so I found 3 of the little switches, and then all I'm going to do is I'm going to take these switches and I'm going to put them right next to, we could put them across, but I'm going to put them right next to each one of these resistors, and then they'll be able to switch in the values if we connect a wire to the other side. All right, so here we go. All right, so now, so take a look at, what we have here. All right, so now we're going to hook a wire to the other side of the switch, each one of them to power. All right, each one power, so we need 3 little wires, no problem. All right, 3 little wires. Here we go. All right, so this one, so here's one. Let's move this so I don't impale myself, which I already did. I don't know if you can see, but my thumb's got, I can split it. All right, here is the next one, right there, for our 1K, and then we need one more wire, a little bit longer, a little bit longer. I can use this one. Okay, all right, so there's our circuit. All right, so we've got a Zener regulator right here. We've got a Zener regulation circuit. We got this 220 ohm. Then we've got a 10K, a 1K, and a 100 ohm. And we are going to look at the voltage, the Zener voltage out, as we go from no load, right? Just this thing just running. And then we're going to add the 10K load by pressing the button. Then we'll put the 1K load, and then we'll put the 100 load. And this is load regulation we're looking at. We want to see how does the voltage vary as we change the load. All right, that is the experiment, just to get a feel for this. All right, so here we go. So I'm going to push these back into view. Let me open up the zoom here. All right, let's get it all nice and neat. Okay, so the power supply is off. All right, so let's go ahead and let's turn the power supply on. It's at let's put it at 9 volts. All right, 9 volts, good enough, and there it is, and it's on. So on the left side here, we see, let's get this exactly, 9 volts. There we go. All right, so we got 9 volts, and now we want to look at our output, right? So we're just going to put our probe back in here, and we've got a little spot for it right there. There we go. And now look, we've got 5 volts out. How perfect is that? That's awesome. So this is a no-load system. We've just got the Zener diode in there. We got 9 volts in, we got 5 volts out. So here's our little poor man's voltage regulator. Okay, let's go ahead and let's say we add a 10K load. So if we add a 10K load, where's our calculator? Someone compute what would be the current. That would be 5 volts divided by 10K, right? Which would be 500 microamps. So right now we're going to kind of draw about 500 microamps, and then the question is, how does the voltage vary? Ready? Here we go. All right. Wow, look at that. Nothing. Barely. See that? See that 0.01 volt variance? So that's pretty cool. So at 500 microamps, or half a milliamp, right, we don't see any voltage variance at all. So we've got very good load regulation. Okay. Let's put the 1K in. Let's do the 1K. With the 1K, instead of 500 or 0.5 milliamps, we're going to have 5 milliamps, right? Let's do it on the calculator. 5 divided by 1K, right, equals 5 milliamps, right? So now we're going to go 5 milliamps, or 10 times as much current. So let's see, can we maintain regulation? So we're at 5 volts here, almost perfectly, 4.99. Here we go. And look at that. How awesome is that? So we only lost, like, 0.05 volts, and we increase the current 10 times. So now we're doing 5 milliamps of current. So right now, this little poor man's Zener regulator is definitely good to 5 milliamps, no problem, right? But let's do the 100 ohm. So now, instead of 5 milliamps, we're going to draw 50 milliamps out of it, all right? So we're going to draw 50 milliamps. The problem is going to be we're going to draw a lot of the Zener current away, right, to maintain that regulation. Now, Through this 220 ohm resistor, right, we've got 9 volts. So we got 9 divided by 220. So that means that at most only 40 milliamps can flow through this current limiting resistor. So when we try to draw this current with this 100 ohm, watch what happens. 2.7, because we've lost Zener regulation. So either we need more voltage coming in, or we need more current so that we can maintain Zener regulation and supply the current we need to our load. So let's go ahead and double that current. All right, so we got 220, so let's make that a 100. We'll make that a 100. All right, if we make it a 100, then we'll have 90 milliamps of current to supply to the system. So I'm going to turn off the power supply for a second, and we're going to find a 100 ohm resistor. Okay, I've got my 100 ohm resistor. I'm going to replace this 220. Now this is going to get a little bit hot, so I'd prefer to have a higher wattage resistor, but we're not going to do it for very long. We're just going to press the button. Okay, so let's go ahead and let's turn the circuit on. So I've applied power. There we go. We see our 9 volts on the left. We're back at our 5 volts, but notice we're a little bit higher voltage than our normal no load voltage of 4.99. The reason why is because the new current limiting resistor here is letting a lot more current, so we're getting more Zener regulation there, and that it's able to maintain that voltage a little bit higher. All right, so I'm just trying to get it to 9 volts perfectly, which is probably a waste of time. All right, so we've got 9 volts coming in. We got about 5.1, the exact Zener voltage that we should. All right, let's go ahead. Let's do our 10K again. All right, notice doesn't even touch it. The output voltage is still 5 as I put the 10K in. All right, I put the 1K in. We drop 0.02, 0.01, 0.02, and now here we go. Here's the big question. So we know we can get 5 milliamps. The question is, can we get 50 milliamps out of this thing? And if so, how bad does the regulation drop down to? Ready? Here we go. Boom. Not bad, not bad. So we lost, 600 millivolts. We lost 0.6 volts. So that's not bad. So if you draw 50 milliamps out of this thing, that's quite a bit. It's 4.43. So if this is a digital system, it would continue to work. It would continue to work. All right. Now, what's something else we could do here? Well, we can also put a capacitor on the output of the voltage regulator, right, to smooth it out so that when we draw this current, it doesn't draw it very quickly, right? It doesn't change it very quickly. The capacitor will smooth it, and we can pull from the capacitor. So let's try that. Let's throw back in. Where did our 4,700 microfarad giant capacitor go? 4,700 microfarad. Where did it go? Where did it go? Ah, here it is over here. Okay, so let's go ahead. Let's turn the power off. So see how cool this is? All right, so now what we're going to do is we're going to put this big capacitor in the output, and this is going to smooth the voltage. So now what's going to happen is as this capacitor charges up to the 5 volts, it'll be charged. So then when we drag the current out with this big load, instead of it instantaneously dropping down to 4.5 or 4.6 volts, first it's going to pull charge off of this big capacitor, and this capacitor will discharge, and as it discharges, it'll maintain that voltage better. So this is a smoothing capacitor. So we're going to put it directly on the output to ground. All right, so let me do that right now. Let me move this out of the way. We're going to put it to the output to ground. And let me give myself some room here. All right, so here's our output right here, and we're going to put it straight to ground. Okay, and there we go. Okay, all right, so that's what we have now. So at the output of the Zener regulator, we've put this capacitor, and now this is going to smooth things out for us. Okay, so this is going to be cool. All right, so let me get these cables up here. Here we go. All right, so I'm going to turn the power back on. Power's on. All right, notice we're at our 5.07 volts. We're at our 9 volts on the input. Everybody is happy. Now let's go ahead and let's switch in our 10K load. Ready? 1, 2, 3. Notice the voltage doesn't even flinch. All right. Doesn't even flinch. My finger's off it. It's 5.8, 0.08, 0.09. It's just kind of flubbling around there. Now let's put the 1K load in there. Ready? Pushing. So there we go, 0.07. So we, dropped 0.01, 0.02, very, very little. All right, and then here is the big one. So now, again, we're not going to get anything for free. This capacitor is going to discharge, but it's going to take it a little bit to discharge, and we could figure it out because we know what this resistor is, we know what the capacitor is charged to, we know what the value of the capacitor is. We could figure that out, but it's not going to be 0 time. It's going to be some time, all right? And hopefully it's semi-slow, so we get a minute to look at this. All right, so we're at 5.09. Let's put in the 100 ohm load, which is going to try and draw about 50 milliamps. Ready? And go. And then look, see? So we got some time. So instead of that instantaneous pulling down, it goes down, slower. All right. Now, the meter is not a really good view of this because we're looking at something that's changing as a function of time. What we really want to do is look at this on the oscilloscope to see this DC kind of go decrease smoothly. All right. So let's go hook this up to the oscilloscope, just the output, and let's take a look at what that looks like. All right. So give me a minute and let's do that. Okay, we've got our oscilloscope hooked up to the circuit here, right? So we've got the lead, the channel 1 right to the output of the Zener, and then we've got a ground here kind of weaseled around, right? So, there's never enough room to do anything here, of course, so that's always a problem, all right? And so now let's go ahead and let's turn the power back on, and then we'll go take a look at the oscilloscope, right? So I'm going to turn the power back on. So we're going to get our 9 volts in, and we got our 5 volts out. And again, when I hit the button here, we're seeing the drain. All right. So now what I'd like to do is, so now let's go look at the oscilloscope. All right. So the yellow line is channel 1, all right? And right now we're at 2 volts per division and we're putting out 5 volts. So let's put it to 1 volt per division so you can see a lot of change. I'm going to slide the channel down all the way to the bottom here, all right? And so we've got 1, 2, 3, 4, 5 volts. So it's exactly correct. Let's turn measure on here. We'll turn measure on. And you can see that the average voltage, the mean here is 5.16 volts. So everything is as it should be, all right? So now what I'm going to do is I am going to, and keep your eye on this mean, all right? I'm going to press the 1K button, and notice it drops down just a hair, all right? But you can't even see it, okay? And now I'm going to press the 100 ohm, and we're going to draw 50 milliamps. And notice how it changes. It drops down as a function of time. We can actually see this event, all right? So now if we change the sweep rate, all right, so I'm slowing it down. Now watch this. As I press it, oh, did you see that? Did you see that curve? Let me do it again. I'll lower it even more, all right? And watch this. There we go. And let it charge back up. And now, look at that. See that curve? And again, I'll do it. So what does that look like? That is a RC discharge curve. There it is. All right, so as I hit the button, there's the discharge, I let go, there's the charge. There's the discharge, there's the charge. So it's regulating, but that big capacitor is acting like an RC circuit, which is good. It's giving us a smoother transition so we don't just jerk down, right? And we can scale this some more if we want. I can put this at 500 millivolts, and then I can scale. There we go, right there. Okay. So now when I hit it, there we go. Isn't that cool? And then we'll let it up. There, charge, discharge, charge, discharge, charge, discharge. Could do that all day. So that's cool. Now, if we had a bigger capacitor, we would, again, discharge slower. So if we had a bigger capacitor, we would discharge much slower, all right? And we would have more time. So as long as our load, so come back to our project board here. As long as our load is not too big, we could tolerate pulses of 50 milliamps because this capacitor